और बाहर पोस्टर लगा दिया। और बाहर पोस्टर लगा दिया।
go on with that. This one. Okay, yeah. Okay, so 2017 is what I call the year of multi-messenger events because of the biggest buzz that was created by the big event of gravitational waves and the finding of its electromagnetic counterpart. But this, there was another small thing which happened during the same time, which got a little bit overshadowed, was these two astronomers' telegrams, which came up around September, October of 2017, where there was reports of detection of high energy gamma rays by Fermilab located inside the error region of an event, neutrino event, which was detected by IceCube. And a little few days later, the first time detection of very high energy gamma rays from the Cherenkov telescope MAGIC from a direction which is again consistent with the direction of the neutrino event, the IceCube, which is designated as, like the gamma ray burst designation, we designate it as 170922A. So it happened in the 2017, 22nd of September. Okay, so that kind of ushered in the field of multi-messenger astrophysics using neutrinos and photons. And this is what I'm going to concentrate on in today's talk. But this topic is not very new. It is a very old age topic which looks into the origin of cosmic rays, which was discovered by Victor Hess 100 years back, more than 100 years back. But only because the telescopes and the detectors that were being built over the years were not sensitive enough to go and find these neutrinos, astrophysical neutrinos, or go and find these high energy gamma rays coincident with these astrophysical neutrinos. But that would be the main topic of today's. Now, why would you do neutrino and gamma ray astronomy as opposed to not doing just looking at the cosmic rays, which are charged particles, specifically because these charged particles get deflected in the magnetic field when they are traveling from the source towards the detector, where you have put a detector on the Earth, and hence the apparent source direction would be completely, the sense of the direction is completely lost because you are scrambling all the charged particles in the magnetic field. So you would never be able to point to the origin of the source. However, if these charged particles would produce gamma rays and neutrinos through interactions of matter, ambient matter around these sources, then you would easily produce gamma rays and neutrinos. For example, here through proton p-gamma interaction or proton-proton collisions, you would produce the pions, and then these pions, neutral pions, would decay into photons, whereas the charged pions would decay into neutrinos and muons and other charged particles. And hence, they would directly point back you to the source. And through that, you can start to do basically astronomy. In astronomy, if you want to do astronomy, you have to know from where your charged particles or photons came from. So importantly, the most important takeaway message of this slide is that the spatial and temporal correlations between neutrinos and gamma rays can trace cosmic ray acceleration sites. So, and what is the connection between gamma ray astrophysics and cosmic rays? So in order to study, you would have to search for study cosmic rays. You would have to search for gamma rays produced by cosmic rays close to the source. There are two types of charged particles, mainly, which are prevalent in cosmic rays. These are electrons and hadrons, primarily protons, and they undergo two types of acceleration mechanism. The one is what is traditionally called the leptonic acceleration mechanism, which most of you have been discussing in the last days, where the electrons would produce synchrotron photons, which are low energy photons between optical to all the way up to X-rays. But these low energy photons will be upscattered by inverse Compton process to very high energy gamma rays through the inverse Compton interaction with the charged particles present in your system. On the other hand, if protons would interact with the matter, they would produce, as I say, pi zeros and pi plus and pi minus, the neutral and the charged pions, and then they would decay into photons. Now, how would you distinguish that? There is a cartoon that the lower energy bump is, as you know, in most sources, you would have two humps. The low energy hump is due to the synchrotron photons coming from the charged particles. The high energy part, this is the typical inverse Compton spectrum that you would look at, and the pion spectrum, the neutral pion decay spectrum would look like, because pions produce two photons of the similar energies. 130 MeV pions would produce 65 MeV gamma rays in the rest mass, and then so you would see kind of a more flatter bump here. And our hope is that if you have data in all of these bands, then you would be able to distinguish between the different acceleration models. One thing I should mention is that this is not so easy, because these pions will also start to produce cascades in the lower and produce cascades in lower energies. So in principle, they start to get merged even at low energies. So it's not so easy to distinguish so directly. This is just a cartoon, and the whole thing becomes extremely model dependent in the end. So let's come to a bit of the detectors that one uses to do this work. The IceCube detector, the IceCube neutrino telescope, as they call it, at the South Pole. So neutrinos, as you know, are very weakly interacting particles. So you would need large volumes of matter for one neutrino to really go and interact and then produce something which you would want to detect. So the most prevalent ones are, you have to go to the South Pole in the ice, or you can build your detectors deep in the water in the Mediterranean Sea, which is currently being built, the AIM-3net. But I would focus mostly on the IceCube part, which is already commissioned and running since several years now. So they have optical modules deep inside the ice, goes around up to 2 kilometers, more than 2 kilometers deep inside the ice. And at every stage of these are strings, and you hold optical modules which would actually detect. And what would be the detection mechanism? I'll come to the next slide itself. So what happens, a cosmic neutrino, let's say it crashes into the atom or in the ice and produces a nuclear reaction. And what it produces are muons, and these muons can travel kilometers in the ice. And if these muons are traveling with a speed greater than the speed of light in that medium, they would produce Cherenkov radiation. And this Cherenkov radiation is the one which is mapped by these optical modules. So the Cherenkov light produced by the muons, which moves with relativistic speeds, the optical sensors capture and map the light. And from that, you can go back and reconstruct the direction and the direction from where actually the neutrinos came from. That's the whole game. Okay. So now IceCube, once it started looking for such neutrinos, let me also tell you what is the background, which is the huge background that you have to deal with. They are neutrinos which are produced in the atmosphere. So cosmic rays which come and hit the atmosphere also would produce these neutrinos. And these neutrinos become your huge background. That is the main reason that you cannot go very much in low in energy, because this atmospheric neutrino spectrum has a very steep spectrum with a minus 3.7 slope. And hence, they start to become non-dominate as you go to hundreds of, used to very few tens of TeV, or at least up to 100 TeV or so. So most of this astronomy can be done with hundreds of TeV neutrinos or PeV neutrinos. Now, IceCube has been looking for such neutrinos over several years now, and they have been also giving out real-time alerts. So whenever they have a certain threshold above which you have seen a bunch of neutrinos within a small time window, and then they start to give out alerts. All these are called real-time alerts from the South Pole, from the online analysis system for neutrinos of energies greater than 100 TeV. And then the electromagnetic telescopes can now, once they have received these alerts, can try to start to follow up. Now you can see the list of alerts that they were sending out over the several years. I've just listed a few of them. And one thing is note is that in the early days, this has been happening around 2016. In the very early days, there have been sporadic claims of what you called orphan flares. That means the flares in which, so traditionally what we believe is that if you have a leptonic acceleration mechanism at play, what you would get is that you would get correlated emission in both X-rays and high energy gamma rays. Now, if you see high energy gamma rays without having any counterpart in X-rays, either a flare or something, you call them orphan flares. And these are the ones which are signatures that may, if you could get detection of neutrinos from them, these are kind of signatures that hadronic acceleration is mainly at play. So there have been some sporadic claims in the early days from the predecessor prototype IceCube experiment like Amanda, but there was no conclusive result in 2017. There was no detection of a neutrino event with any other wavelengths. Okay. So let me just briefly describe the IceCube alert streams to you so that you can understand what you have to, which are the events that you would like to really follow up and which are the events which are not so interesting for you. So IceCube kind of gives you so every neutrino event that IceCube detects has a probability associated with it, whether what is the probability that this is of astrophysical origin. If it is a 30% probability, they call it a bronze type of an event. And if it is a 50 or greater than 50% probability, they call it a gold type of an event. So this is an event which has a very high probability of being an astrophysical origin. And these are the ones which they would ask the electromagnetic telescopes to really follow up. These are publicly distributed via GCNs, and then they can be followed up by all the other electromagnetic telescopes. And the aim is to identify a plausible electromagnetic counterpart to this neutrino event. So you can see the direction in the sky that they were giving out these types of alerts. They are of different types. They're bronze and gold, and in the earlier days, they used to also describe them as extremely high energy neutrino based on what is the energy of the neutrino, or slightly lower energy neutrino, but nowadays they only classify them in terms of bronze and gold alerts. Okay, so this program so you can now develop a program which is called the Neutrino Target of Opportunity Program, and this was a pioneering effort by MAGIC, which was started in 2000, as early as in 2007. But since there were no neutrinos being detected, high energy neutrinos being detected at that time, what we were only doing during that time were we were implementing the program, we were computing what would be the alert rate from the numerous background neutrinos that you see, and these were being tested and we were discussing at what threshold that we would start to point our electromagnetic telescopes towards this region in the sky from where the IceCube neutrinos came. All these things were being done over several years and being discussed. There is another very important thing that you would want to keep in mind, that what are the types of neutrinos that you would like to also follow up. The neutrino interactions happen in different ways. One of the ways is called the charge current neutrino interactions or neutral current neutrino interactions, which produce tau neutrinos or electron neutrinos, which are carried out by tau neutrinos or electron neutrinos, but they produce something which is called a cascade or a shower of events in your detector, But since it is a shower, it looks like a spherical geometry in the detector, and hence the angular resolution is very, very poor. The angular resolution of such cascade events is of the order of 10 to 15 degrees. So it's almost impossible to do any electromagnetic follow-up with these type of neutrinos. So those are kind of not to be are kind of kept aside and not generally followed by electromagnetic telescopes. Whereas if they are of charge current interactions by muon neutrinos, they produce those muon tracks, which are very, very nice muon tracks in the ice, and they have an angular resolution of the order of a degree or even less than a degree. So these are the ones which the electromagnetic telescopes are going to follow up, because you see the type of the electromagnetic telescopes are from the ground, let's say the high energy gamma ray telescopes have a field of view which are very narrow, like 3 degrees or 4 degrees or 5 degree field of view with an angular resolution of about 0.1 degree or so. So the muon ones are the ones which you would want to follow up. So now let's come to the real story of this extremely high energy event, which happened on 22nd of September, 2017. IceCube sent out an ATEL, as I was saying, a GCN notice, and then Fermilat, being an all-sky monitor, kind of has a large field of view, detected after a few days, it reported in the ATEL that they found the brightening of a source which lay in the error circle of IceCube, a blazar which is TXS0506, which became very famous, or you know. And then, since these ATELs come to all the electromagnetic telescopes on the ground, MAGIC telescope in the very high energy gamma rays also started to follow up once they got the news that there has been a brightening in the Fermilat also happening. Initially, weather played a little bit of a spoil sport, and we could not observe because there were lots of clouds in the sky, but finally we managed to take data over the next few days, and then on 4th of October, and a few more days later, one saw a clear signal from of a flare detected by MAGIC in very high energy gamma rays. And then several other observatories were also alerted. And so then became a flurry of ATLs in the next days. And you can see here from optical all the way to infrared, X-rays, everybody started to report about a flaring event from the direction coincident with the ice cube event and coincident with the blazar TXS0506. So here is a kind of a light curve in very high energy gamma rays. The other gamma ray observatories like HESS or Veritas also took data and they also found the signal. And then slowly, since Veritas started much later, after the alert was sent, they did not see the signal initially, and this only reported upper limits from the source. So this is a nice comparison of the light curve. What you can see, this is a kind of a long-term light curve. This is where the ice cube trigger was sent. Actually, when you go back into the archival data and look at it, the brightening in the Fermi was already happening right before the ice cube event was reported. And here you see MAGIC looked at the ice cube. So here was the ice cube event. Initially, we could not take some data because of weather, and then we started taking data, and afterwards we also clearly saw a flare from that. And then long-term light curve, we followed up the source later on. There were some other smaller flares detected also, but the source was being detected at a high state and low state and various other states. So an analysis, a joint analysis between ice cube Fermilat and MAGIC events showed that the events were coming from the direction of the source TXS0506. The redshift of the source is about moderately high, it's about 0.34, so which translates into a distance of about 1.7 gigaparsec. And one would, so now, since this was the first time this kind of an event was detected, one has to calculate what would be the chance probability that an event has been detected from a particular source. So you have to take into account all the sources in the sky which emit very high energy gamma rays and plausible emitters of neutrinos, and then you calculate this chance coincidence probability through a likelihood ratio test, and then you disfavor this, that it is a fluctuation at greater than 3 sigma. So that gave the first indication that high energy neutrinos and high energy gamma rays and very high energy gamma rays have come from a source from the same direction. The energy of the neutrino was measured, the most probable energy was measured to be about 300 TeV, and the upper limit was few PeV, depending upon what sort of spectrum that you assume in your simulations. And then there was, then spectral shapes were studied. There was no clear spectral variability found in the low state and the high state in the electromagnetic telescopes. There was a strong curvature seen at greater than 50 GeV, which you expect because the source is at moderately high redshift. So, and most of the high energy photons would get attenuated because of the presence of the extragalactic background light. So all these fits in well with the conventional stories. And then you can build up the large multi-wavelength light curve, as you can see here. I'm not going into very details, but we can come back to that if you have questions. There were observations undertaken in radio, X-rays, and optical. During the ice cube trigger, also there were it was found in Ovro, the 40-meter telescope in Ovro at 15 gigahertz. It was also found in an elevated state. And sorry, let me just go back and say that there were only marginal spectral variations seen in X-rays. And when compared with the historical flux, it was also reported that there was an enhancement of the flux, but the spectral variations were not that much. So a plethora of models, the model builders were already ready there. And within a couple of months, as you can see, within a month of all these, a plethora of models came out. People were hooking up all sorts of their models in order to fit the spectral energy distribution. And there was, as I said, there was an explosion of theoretical papers in the archive in the next days. And so I just show you one or two of these such cases. One could actually show that if you, let's say you did not detect the neutrinos at all, you had only the electromagnetic spectrum, one could show a pure leptonic model would also fit all these data quite nicely. So there was no big problem. So that had actually raised the question that whether these were really correlated or not. These ones were really. Spatial correlation is absolutely fine. However, there was no guarantee that these are temporally correlated or not, because you could show this that with electronic acceleration mechanism, you could fit the data. So for example, here one could see that the electronic acceleration mechanism could fit the data, but however, if you add hadrons to it, so a leptohadronic model, you could also fit the data quite well, reasonably well. We had also done some work. So most of the people at that time were working on the assumption that the protons are interacting with the photons. So there is a p-gamma interaction. However, with Ritanjali and her student, we also looked at it using the proton synchrotron model. So the protons would produce very high energy gamma rays, and the pp collision would produce the neutrinos. And there also we showed that it can relatively reasonably well, it can fit the data. However, it has some problems in the sense that the maximum energy of the proton that you would get from the energy of the neutrinos is somewhat higher than the most probable energy that the ice cube neutrino was reported. However, it still falls within the distribution of the more probable energies that one could have. So that's also another plausible way of looking at the whole
There's
thing.
no point in asking this question, but
Yeah.
still go back. So is there, I mean, this is a modeling you did with, you yourself were involved, right?
Yeah.
So you see that, okay, the upper limit of this green.
Yeah, we do
points
not
are
consider
fine.
that. Yeah.
But even the reds are actually have a tail which is not matching this.
Which reds? These ones you are saying?
Yes.
These one. No, so these part, so this one is the one which you would use if you had only a leptonic model.
Okay.
Okay, so you would have a leptonic model. These ones are the ones if you have gamma rays coming from proton synchrotron radiation. And then this is the neutrino that you would see, the neutrino flux that you would see due to the proton synchrotron model.
Okay.
So there is no way to discount that there are electrons in the system. There are electrons. So there are electrons for which you produce the synchrotron radiation, you have the inverse compton, so all these can fit it nicely. However, then you have to explain whether there is a way to do the temporal correlation or not. And for that, you use different types of models, either a p-gamma model or a pp model. That's what we try to do. Okay, something extremely interesting which came from when IceCube went and looked back at their archival data is that they found out that there was an evidence of a neutrino flare of about 3.5 sigma significance in their data in 2014-15, which had completely got unnoticed in their analysis. And so this is the neutrino flare, so which was even a bigger flare than the neutrino flare which when they sent out the alert, simply because their analysis system was not really fully developed to search for that at that moment. In 2014-15, they were still building the whole detector still and were just about to analyze the data. So when they found that out, they analyzed data. So during the same time, they looked at what was going on in the source in Fermi. Very interesting, there was no flare in Fermi. The Fermi, in high energy gamma rays, the source was pretty quiet. And then there were very little spectral shape changes during the flaring time in Fermi and during this time when the flare was low. So let me go a little bit fast, because then after that, there were many more plausible neutrinos. IceCube was sending out ATELs, and then there were many more plausible associations being discussed. He has been one of the people who have been involved in all this work quite substantially over the last few years, doing multi-wavelength analysis of the plausible neutrino candidate events. And then there was another type of system stream which IceCube has been doing for the last few years, is a gamma ray follow. So instead of looking for an all sky search, you would pre-select sources based on whether they are plausible emitters of neutrinos or not. But these are not publicly announced. These are only given privately to the electromagnetic telescopes if you have an MOU with IceCube. So Magic and Magic Veritas and other telescopes and also Fermi have an MOU with IceCube, for which private alerts would come from certain predefined direct targets in the sky, and then you would and the alerts will be distributed under MOU, and then you would strive to look at them. And based on that, so this was what Stalin had been discussing over the yesterday. So there was this alert, very interesting alert coming from the source PKS07. So, but this is not a private alert. This was coming from a public alert on this PKS0735, which was a question which is if it is associated with 211208A. You see the long-term light curve which Stalin has showed yesterday, and the total energy of the event is about 170 TeV. It was seen in an elevated state in optical to gamma rays, the whole source. But however, there was no detection in very high energy gamma rays by Veritas or Hess from this source. And so people have done some broadband modeling. The Veritas people and the Hess people have done some broadband modeling where they showed that SSC plus the external component provides a strong curvature. And the question being asked is that whether there is an intrinsic cutoff in the source at greater than 100 GeV, or there is also a hint that the redshift may be higher. The redshift of this source is not 0.4 but higher, and so EBL would attenuate the very high energy gamma rays, and that you would not see them. And there are we have also been looking at this data recently, and I've been doing some work on it. So let me go a little bit faster. So I'm coming close to the end. So more recent news on neutrinos and gamma rays. An all-sky search of 9-year search had yielded 2 interesting sources, completely different type of a source, an NGC 1068, which was the most significant one. And then the next significant one is another blazar PKS 1424, which was already discovered and detected by Veritas and Fermi and other telescopes before. And these are, but however, these are just non-simultaneous multi-frequency observations that I'm putting out here in order to understand how the electromagnetic, whether there would be a correlation between neutrinos and gamma rays from NGC 1068, which is a Seyfert-2 galaxy and has a vigorous starburst activity. Okay, and let me go just last couple of slides to the future. So as you understand that we are dealing with very few events here. So now you need to go from the detection phase to the gamma neutrino astronomy phase. So what we have in future is that the KM3Net, the multi-kilometer cube neutrino telescope in the Mediterranean, which is going to come up soon. The first strings have been deployed in 2017. IceCube is also expanding. The extension of IceCube is already about to start in 2025 by IceCube Gen 2, what they call. And then in the high energy gamma rays, there will be Cherenkov telescope array. Instead of just 4 or 5 telescopes like MAGIC or HESS, you will have now 100. We are planning to have at least 50 to 60 telescopes of different types. And then the prototype CTA telescopes one of the prototype CTA telescopes have already got ready by 2023 and are starting to do some observations with that. So I conclude that I hope I have sufficiently tried to convince you that blazars are plausible sources of very high energy cosmic rays beyond several tens of PeV. About 10 to the power of 15 to 10 to the power of 17 electron volt. Definitely not yet we have seen any ultra high energy cosmic rays from there, which are of the order of 10 to the power 20 electron volt. But the detection of a blazar in flaring state in gamma rays in connection with a high energy neutrino event has raised more questions, I believe, than it has answered really. Are they happening only during the flares? Is there any temporal correlation that we have been able to establish? We have not been able to do that. However, we have now quite a few multi-messenger SEDs to start to play with, but we need many more such events. In the last years, we have been performing regular electromagnetic observations of these events. We need much tighter cooperations between these observatories to carry out these observations. And just to end, this is the news from yesterday. So on 27th of October, IceCube had sent an alert on a very high energy neutrino event of about 200 TeV or so. And yesterday only, there has been an ATEL from Fermilab gamma ray, Fermilab that gamma rays have been observed from, but in the IceCube error region, there are 2 high energy gamma ray sources, and both have been seen in elevated state and over the last few months or so. So that raises even more intriguing questions. And I was up till 2 a.m. in the morning yesterday, scheduling observations of the MAGIC telescopes with this, discussing with the schedulers of this. So I just put it up for your, for a conference as a fun part of it. Thank you very much.
Okay, thanks a lot, Pradeep. Any questions?
Yeah.
So this is about 2015 observation, right? So that was a bunch of neutrinos most likely. There was a kind of a stream. That's what we call
There was
it.
a bunch of neutrinos.
Yes. So now this apparently, I was kind of talking to you about this possible binary black hole because it's kind of a repeating argument.
Yeah.
So then I had the impression that there was something happening, last year about the TKS.
This TXS 0506. See, TXS 0506 has been regularly been seen in low and high state in Fermi and in high energy gamma rays. However, after the 2017 event, we have not yet detected any bunch of neutrinos from there.
Even the background fluctuations are
they are fine. We have seen from other blazars, but with the current sensitivity of ice cube, you are really just at the tip of the iceberg. You are just scratching the first part of it.
It's
so
like
you
the
really need
PTA.
to build larger detector to go and have handful of neutrinos.
That way very similar to PTA. So that's
Yeah. We are just at the scratching the first part of it. Of the whole
Great. Yeah. Thanks.
So, in your conclusion, you are saying that blazars are a source of cosmic
neutrinos
rays.
are, which means
No,
also
neutrinos is
cosmic
fine,
rays.
but cosmic rays, right?
Yeah.
So therefore, cosmic rays are alpha particles. So the blazar jets, therefore, you are suggesting that it's not electron positron; it has a lot of protons.
Yes,
Right.
because you see, this is the first instance when we try to say that we have seen
I'm not
extragalactic
finishing the
cosmic
question.
rays.
I have not finished the question.
Extragalactic. Yeah, that's the
So,
suggestion. Yeah.
That's number one.
That's
But you also there was
But I'm
also one.
saying that electrons or positrons are not present.
No, of course there has to
There
be.
has
I
to
mean,
be
for
present.
charge.
Of course, they have to be present.
So I'm not saying that they are not.
Yeah.
So now you also said that Ice Cube a few months ago, I don't remember, maybe during our private conversation.
Yeah.
So you said that it detected neutrino, but it is not coming from the blazar jet, but it's coming from the core. Something like that you
So
said.
they had put out a paper on that. So what they had done is that they had tried to find out what is the fraction of sources from where you see ice cube high energy events, and they put an upper limit that 27% of these events are coming from blazar jets. And the rest are coming from different types of sources, out of which they could also be coming from some from the core.
Okay.
That's what they had put out in that paper. So they had put out a thing is that what is the fraction of high energy neutrinos coming from jets, coming from other types of sources, or from the cores of AGNs and this kind, and then they claim that it's about 27 or at most 30% of these are from the jets. So
that is an estimation.
That's an estimation.
That's an estimation. What I'm trying to say is, if the cosmic rays are coming from the blazars, probably from the jets of the blazars, and therefore we should expect neutrinos from the jets as well. Okay, that was the expectation.
Yeah.
But Ice Cube did not detect that. They detected in the core, right?
That was only one or two events they had been saying. Most of the events they are detecting are from the jets till now. Till now, what we have seen are from the jets. Not the majority of the events they have not yet been established from the cores. Yeah, that's only one or two.
So, very nice talk. I have a related question. I mean, when you talked about this Texas source, you had fitted with a leptonic and then a leptohadronic. Now, could you decipher what is the source of the protons? Would it come from the jet itself, that is inherent in the jet itself, or due to the contamination when the jet interacts with the ambient proton-rich source?
Okay. I don't think we are at a stage to differentiate.
So then what would you need to do that?
I think what you would need to do that is to have much better angular resolution in both the high energy gamma ray telescopes. These are of the order of few arc minutes now. You need to go back to 1 or 2 arc minute kind of places. And also, which is almost at the limit of gamma rays. And that is why, to some extent, I believe that X-rays are going to be far more important. So let me go back to this slide here. Because due to the cascade emission, there would be abundant of X-rays produced at the lower energy because of the cascades of the muons, right? And that would, so let me go back to here. this plot. That's what our main thing in this paper has been, that you could strongly constrain by looking at hard X-rays because of the cascade emission, instead of looking more in the gamma rays. Because you would be limited by angular resolution, the very fact that of the Cherenkov light, you can only go up to a 1 arc-minute and not go better than that. The technique itself stops there. And also ice cube has to become more better, because it's still about half a degree or so in neon cracks resolution. With ice cube Gen 2, probably with many more events, we would have go to maybe about a few arc-minutes resolution.
Okay, the last question from Amit.
That is a very interesting talk. The recent ice cube papers are suggesting that excess source is losing significance. And actually, it's a below 3 now. So, if we don't detect it in future, how we go about it? And the two other sources are gaining. No. So actually, they have changed their analysis technique, and then excess lost their significance.
Yes.
So,
I think I am not in a position right now to say this, unless and until we start to detect many more types of things. It's really, that's why I say that a large number of people in the community believe that spatial correlation is fine, but there was really no temporal correlation between the Texas source and the neutrinos detected from the Texas source and the. But then the important question that comes up also is that with what would you start to hook into the ice cube events? See, most of us who do electromagnetic astronomy, we always look for counterparts in different wavelengths and decide whether I want to issue a TOO or not. So when I have a neutrino event, and then I say that, okay, let's say the high energy gamma ray telescope should observe, people start asking, oh, is it doing anything in X-rays? Is it doing anything in Fermi? But we have also seen that that's not always the case, because you have seen a bunch of neutrinos in Fermi. That's because the ambient medium around these sources could actually become, the gamma rays are opaque, could become opaque to that. So maybe gamma rays are not good indicators also. We are just trying to find out what would be the good indicators. Neutrinos will pass through that. Gamma rays will get absorbed in this environment. So you would see many of them probably at a low state of gamma rays or no gamma rays being emitted.
Or it can come later after kind of getting out of the cocoon.
Yeah. That's another possibility. That's another possibility. So as I said, that we are just starting to scratch the very top. The possibilities are right now enormous.
Okay, so we are getting late. So that case, in that case, what is the chance that the emission that we get will be in the thermal because if the gamma rays are trapped,
X-rays going to be.
Yeah, that is what our prediction has been in this paper, that X-rays will be very important.
Yeah, but then there's a problem. There's better X-ray telescopes will be required.
And it is even more
back. I mean,
let me also point it out. It's even more difficult to convince an X-ray astronomer to look for neutrino events. Forget it. Ritovan and I have tried to with the AstroSat people time and again.
What is Ritovan? Is it X-ray astronomer or
we have tried this time and again, and we have failed miserably to convince X-ray astronomers.
Then it's fine.
Yeah.
It's not supposed to do everything.
okay, so we'll move on. This AstroSat begin. Okay, so let's thank the speaker again. We will now move on to the next speaker. Is Vidushi Sharma. She will be talking about multi-messenger astronomy with general coordinate network and short GRBs.
So, hi everyone. It's on. Okay, so good morning, everyone. I'm Vidushi Sharma. I'm postdoc associate in GCN team. So I will first start with multi-messenger astronomy with a alert system GCN, and then I will move to my research topic GRBs. So, GCN, starting with what is GCN? GCN is So GCN is a public platform facilitated by NASA for sharing the information about the transient events among the space and ground-based observatory and thousands of astronomers worldwide. And it has interesting history. So GCN started as an innovative idea of failure of CGRO tape recorder in 1992. To save the CGRO, NASA started real-time data transmission, and for this, the young scientists at that time, used that opportunity to go ahead to build real-time alert system, Decodile, which has new name now GCN. So GCN over the time gained different distribution mechanism. So it started with phone calls among the batches scientists, then emails, and then pagers at some point, and computer socket connection. But the popular way is email alerts. So in 1997, other instruments also joined the GCN, this BATSE group, and they formed the Gamma Ray Coordinates Network. So GCN initially enabled the seminal discoveries in the field of late 90s transient GRBs. So it is starting with first detection of redshift from the afterglow to the recent detection of EM counterparts in GW detection, GW events such as GRB 17.17a or kilonova are reported by GCN. So those who are not aware, GCN has two data products. One of the products already talked about the GCN notices. And here as an example, GCN notice for Fermi GBM is shown. And it is by machine, and it has fixed predefined format. It is automated and it has specific schema. Whereas GCN circulars, it is written by human, it has free format and it is citable. So every other astrophysical observatory have reported their transient observations through GCN. So over the time, GCN has changed the scientific. Thus, over the time, scientific landscape has changed, especially in the last decade with GW detection and neutrino detection. The GCN also has new transient reports, the gravitational wave and high energy neutrino users. Then it has also detected the gamma ray transients such as PD and magnetar flares. So also the technological landscape has changed, especially since late 90s to this time. So we need some solid streaming platform which are commercial based and rich in ecosystem of tools. So the Vera Rubin LSST, which is coming online next year, is going to use Apache Kafka, the streaming platform, which is built by LinkedIn for streaming their alerts. And GTF is also using this Apache Kafka. So the new GCN is built on the backbone of, it's not showing internet connection. Let's stop at this slide. Sorry for the interruption. So the new GCN, which is also built on this Kafka streaming platform, which is state of art of technology for sending the alerts. So earlier, the previous GCN, there were 3 platforms for sending the alerts. So for video event format and text and binaries information. So these were used to send using different protocols such as video event transfer protocol, emails, and computer socket. But with GCN over the Kafka, all 3 formats can be sent using one standard protocol, Apache Kafka. So there are a lot of advantages to move on to this new GCN system. It is self-subscription. Earlier, people used to sign up the form, and now people can manage their own account. They can use toggle on-off button to stop the emails in their inboxes. And new GCN has open standards based on one standard protocol, Apache Kafka. It is open source. Everything is over NASA GitHub, and it is highly available. Everything is running over the cloud. It is secure and reliable. So here's the new GCN website, which launched last year, and it has updated look. One can use any of the single sign-on method, and you can browse and search. So the new GCN circular is migrated in April only. We had global webinars for this. So this new GCN circular is now running over the cloud, and you can browse and search our new archive. You can manage your email subscription, and you can another new feature is web form. So you can submit the circulars using the web form, which will have Astroplevel Markdown, where you can embed tables, images, and coordinates. So it has integration with NASA ARIES. So there are a lot of improvements in GCN circulars. So first, I already mentioned, you can manage your own account. Then it is easy for community with this system to join and submit the circulars. It is faster. So now the circulars are sent in parallel. Earlier, it used to take around 15 minutes minimum to send the circular to all users. Now it takes a few seconds. It is more robust and sustainable as funded by NASA. So after the GCN circular migration, now the next is GCN notices. So these are the GCN notices producers. So for the new notices, it will be only distributed by Kafka, and it has preferred format JSON. And here step-by-step instruction are shown for a new notice producer. So any mission or any new transient can have their own notices type for streaming. So for example, it can be pulsars also if you want follow-up community. So for this new notices, we have introduced unified schema. So it has building blocks of JSON core schema, which has same property and consistent units. For the new observatory, so it is any specific field, if needed, can be added. So with this, the useful is that it is a standard way of keeping the database. So all across the mission, there will be consistent property and the uniform, which is useful or smoother for correlation searches. So here, with IPN, there will be new notices type for SGR and high energy transients. Here, as an example, IceCube GW follow-up schema is shown on the left, and on the right, the example of notices are shown. It announced only last week only. So there are new notices alert for IceCube GW follow-up by GCN. So in GCN, we are also trying to working on ML-based search engine with summer intern with me. He tried to use the Google AI tool for exploring the language models over the GCN circular. So as you know, GCN is human written as free format, and it is really difficult task to read every circular to extract the information. So with this exercise, we conducted this project, and here the hierarchical topic modeling was done, and here clustering, here 2D visualization map of GCN circular is shown using bird topic, and each gray point represent the GCN circular. It is here 6 topics are shown which are clustered together. So you can see this green one is all GCN which are optical reported, and brown one are all GCN clustered together which are radio reported observations. So it is giving promising results. So in this, as GCN is there since 30 years, so we also, as for exercise, we plotted the GCN circular based on the topics. So for example, the blue one started with is the Swift bad XRT UVT GCN circulars. So it has jumped since its launch 2004. Then in 2008, green color for me, GCN circular distribution is shown. In red color, LIGO Virgo GCN circular is shown, which has also maintenance gaps in this distribution. So machine learning is giving useful results. So another exercise what we conducted is information extraction from the GCN circular. So we used the training the GCN circulars using the model with question answer pair. So we asked the questions, we trained with the question, what is the redshift information, what is the event name, and what is the instrument name. So for this we used a Swift redshift catalog, and we extracted these information. So here, after the machine learning exercise for each GCN circular, this is 2 redshift, and this is predicted redshift by the machine learning tool, and the predicted GRB name and predicted telescope, which looks quite convincing. And on the right side, the distribution of all reported redshift by GCN is shown from using the machine learning. So this is, in this way, one can user can extract any of the information from all the GCN circulars as a literature. So after all about GCN, now coming to multi-messenger sources. So one of the transient type which is primarily reported by GCN is gamma ray burst. So after blazars, now it's multi-messenger with GRBs. So as GRB occurs, it outshines all other gamma ray sources in the sky. In the background, Fermi gamma ray sky is shown, and as GRB happens, the light curve GRB is shown as a prompt emission, which originates close to the burst site. So we have used the prompt emission to understand the central injet and viewing geometry of GRB, which is traditionally done using the afterglow analysis. So with GRB 1708, 17A, there was a lot of follow-up studies, and which indicated jet was viewed off axis. So it showed the increase. So what is like if there is an observer on off axis and there is a structured jet profile, so there will be increase in afterglow. There will be increase in afterglow light curve in all wavelengths, and then when 1 by gamma becomes equal to viewing angle, it starts dropping as similar to on-axis observer. So this was kind of feature was observed in GRB 1708, 17A. So it confirmed to most important information about the GRB jets, that it has structure beyond the jet core, and jet is viewed off axis. So we have used this information to find the imprint in prompt emission of GRB. So generally, afterglow is used for understanding whether viewing geometry of the GRBs. Here, for the first time, we have used prompt spectra to get the hint of viewing geometry. So here, short GRB spectra is shown in blue color. So here's a distribution of low energy spectral index is shown on the left side, which is generally fitted with band function from the Fermi catalog. So here we find that most of the GRBs have hard alpha, which makes it inconsistent with conventional synchrotron model. First point. Then out of these GRB, most of them have high energy spectral index as steep, which indicates cutoff power law kind of shape. So this kind of spectra indicates short GRBs have hard and narrow spectra for most of the time. This can be, this support the photospheric emission model. So we have used this photospheric emission model to understand the structure jet profile. So there's a study by Lundman et al. 2013 where he used the simulation for non-dissipative photosphere for the structure jet profile, and he used angle-dependent Lorentz vector profile for that. So here the schematic diagram of Lorentz vector profile is shown for the jet core angle shown in gray color. The gamma is constant. For the structure jet, we have considered this decaying Lorentz vector profile with angle beyond the jet cone. So for such cases, for the observer viewing off axis, will observe varying Lorentz vector. So thus in observer frame, there will be, due to Doppler boosting, there will be superposition of many temperature. So this is used to using multicolor black body model. Okay. So here multicolor black body is used for the, if jet is viewed on axis, so it shows like constant Lorentz vector profile, and there will be a single temperature for high zeta value. And for the off axis observer, we expect their spectra will be softer, as there will be superposition of multiple temperature black bodies. And this kind of spectra we expect for off axis observer. So this is used to study the 39 short GRBs observed by Swift and Fermi with redshift information. So we use photospheric emission model. So most of the GRB were consistent with this model, and we use this for further studying the structure jet of these short GRBs. So the Lindman et al. Have the prediction of low energy spectral index and Lorentz vector profile. There in the paper, they expect that alpha ranges from -1 to -0.5 for photospheric spectra when viewed off axis, and for on axis, alpha is expected to be hard. So this is used for this structure jet case, and you find that 43% are viewed outside and 57% are viewed on axis. Here, core angle of jet short GRB jet are shown, which shows the narrow core around 3 degrees, which is consistent with Moulet et al. 2018 with super luminous motion of radio from GRB 17/17A. And for the theta jet opening angle, also it is consistent with Fong et al. So this kind of study indicates that this methodology is favorable for the existing literature work. And thus, for non-dissipative photospheric allows us to access the viewing geometry and the Lorentz vector profile. And with this, we expect the bright GRB with LIGO is around 0.19 to 2.8 events per year. Yeah, thank you for listening.
One quick question. Only one question.
Okay.
Only one.
Beautiful talk, thank you. I will catch you on the GCN part, but this one, so we know that the observed 17087 was definitely 3-order magnitude weaker.
Yes.
So can we have a machine learning and an algorithm to look for the, all these events to see how many such things were actually seen, which were not properly reported, but, such very, the integrated thing was very low.
So
It has been looked at?
yeah. So there is a recent paper after O2 run by Fermi GBM team. So for that, they have used the targeted search. And for this 19, there was neutron star and black hole case. They find some around 2.5 sigma detection for that case. So using, even though it was weaker with targeted search, which has like better algorithm, we found it is like around 7 or 8 sigma detection.
Okay, so even the fluids can be substantially lower and you
And
still, okay.
but you with the better background modeling, the
Okay.
significance can be done, but that requires the computational power. So Fermi team has this program for every they have MMBA, like multi-messenger BA. So for every GW detection, if it has neutron star involved into it, they reported, they conduct this targeted search and report it by GCM.
Okay,
So I'm part of Fermi GWP, so I'm aware of this.
cool. That's very nice. I'll catch you later. Thanks.
Okay, so let us thank the speaker. Okay. And I now hand over to Raman to. There is no hard copy of the.
Okay, it's fine. Okay, so so this is the neutron star session. And first up, we have Aruberi from Aizar Mohali, and she'll be talking about the discovery of a new millisecond pulsar. So you have total of 25 minutes. So I'm assuming that you will leave 5 minutes for questions. And so I'll give you a 5-minute warning at 15 so that.
Good morning, everyone. So I'm Anu from Aizar Mohali. So I'll be talking about this work which I've been carrying out in Aizar Mohali with my research group at Aizar. And this work basically focused on neutron star X-ray binary systems with AstroSat. So as the name suggests, I'll be talking about fast timing in the broadband study of neutron star X-ray binary, and that led us to the discovery of the millisecond X-ray pulsar. So before I start my talk, I need to acknowledge my funding agencies, including my research group at Aizar Mohali. So thanks to all the funding agencies for helping me out in carrying out my research. So yes, I think in this audience, I don't require an introduction to AstroSat, but we all know that we have our own mission, AstroSat, which is a multi-wavelength mission. So with this observatory, I have been working with primarily with large PC counters and SXT telescope for doing the broadband and fast timing studies of neutron star systems. In this talk, I'll be focusing on low magnetic field neutron star systems, where the magnetic field is of the order of 10⁸ to 10⁹ Gauss. I'm not going to talk about X-ray pulsars. So what is important about neutron star low mass binary systems? We all know that we are unaware about the core of the composition of the core of the neutron star. And low mass X-ray binaries with neutron stars as a compact object are considered to as one of the very few tools by which we can actually try to understand the composition by understanding the equation of state models. And from observational point of view, we do have some observational features. Observational features such as thermonuclear X-ray burst, which is again one of the very few ways by which we can constrain equation of state of models by measuring mass and radius of the neutron stars. And in this talk, I'll be covering these two topics, which is accretion powered X-ray pulsars, which are again part of neutron star low mass X-ray binary systems, but they do exhibit very fast rotation. And I will eventually I'll tell you about the connection between these two classes as well. There are other observational features which can again lead us to the constraints on mass and radius, but I'll not be focusing on this talk. So coming back to thermonuclear X-ray burst, what are these bursts? So these are the observational features of which is shown here in the left panel, which is basically a sharp rise in your X-ray luminosity in the X-ray light curves and an exponential decay. So whenever you observe such features in the X-ray light curves of an X-ray binary system, this is the confirmed signature that the compact object is a neutron star. So because of the hard surface of the neutron star, these observational features are only evident or observed from the neutron star systems, cannot be observed from the black hole systems. And what makes them important too
There are some inherent assumptions while we are doing the thermonuclear burst study. So we assume that it is during these bursts, the emission is thermal, which means you can fit the flat body spectrum to the burst spectrum. And using the Stephen-Boltzmann law, you can basically estimate the radius of the neutron star. However, as I mentioned, there are some inherent assumptions and there are some systematics which propagate through our analysis. And one of them is we assume it to be thermally emitted spectrum, which may not be the case. You can have a contribution from the inverse quantization because of the presence of hot electrons in the neutron star atmosphere of the accreting neutron star. And then you also have uncertainty in the distance and propagating through your gravitational redshift and so on. So this is an example plot of a thermonuclear X-ray burst study of a particular system with AstroSat. And this was work led by one of my students, Pinaki Roy. And in this top panel, we see the observed burst profile during X-ray burst. And we see large count rates of almost kiloseconds during the thermonuclear X-ray burst. And we observe the temperature evolution by performing the time-resolved X-ray spectroscopy. Interestingly, these green shaded region are the times when we actually observed or detected burst oscillations during these thermonuclear X-ray bursts. And you can ask me later on what are the blue and black points. Just because of a shortness of time, I'm not going to go into details of the burst spectroscopy because that is not the main theme of this talk. But this is how we do perform the burst spectroscopy, and we estimate your radius of the neutron star from the Stephen-Boltzmann relationship. So thermonuclear burst oscillations, I did mention that the green shaded regions are the times when we actually detected burst oscillations. So these are asymmetric brightness patterns from the neutron star surface of the spinning neutron star systems, which can sometimes be discovered during thermonuclear X-ray bursts. They are very intermittent, and you have to have a very careful analysis algorithms to really detect these burst oscillations. And and they can be observed both during rising and the decline phase of the burst. And for the rising and the declining phase of the burst, there are different theories being proposed to explain the origin of the burst oscillations. So with AstroSat, for a case study for a particular neutron star system, 1636, we did observe a sharp peak around 581 Hertz, which is a well-known spin frequency of this neutron star system. And this is a well-studied neutron star system, so this was a good case for us to pick up with a neutron star study with AstroSat when AstroSat was launched, so that we can actually try to figure out whether we are able to detect the real features with AstroSat. So this was confirmation that we could significantly detect burst oscillations with lax PC on the AstroSat. And this is the dynamic power density spectrum supporting the fact that they are not always observed during the burst. So with AstroSat, we have an advantage of the broadband and the fast timing. Along with the large collecting area, you have sufficient photons to do a more detailed timing study of during these bursts. And so this is like a plot on the top, again, the thermonuclear X-ray burst profile of a particular burst observed in a very long observations. In fact, there were several observations. We actually explored the entire archive and find out all the bursts observed with AstroSat for a particular source. And then we did observe look at those particular observations in detail where we did find the burst oscillation. And this is a fraction RMS amplitude evolution during one of the burst oscillations we detected or during one burst. And it basically during the rising phase, as I mentioned, that you can detect burst oscillation. It did show some evolution of the fraction amplitude showing a decrease, which is well in agreement with the models in literature, which is the spreading of the spreading of the material on the surface of the spinning neutron star, which means the fractional amplitude as the radius of the neutron star expands, it will decrease. And then interesting in this observation was the high amplitude, high fractional amplitude measurements during the decline phase. And these observations are kind of challenging to the existing theoretical models to explain the high fraction amplitude burst oscillation. Generally, during the decline phase of the burst oscillation, one expects to have a lower fractional amplitude oscillations. And hence, it leads to a question that what causes the decline phase burst oscillations. Now coming to the second part of my talk, accreting millisecond exapulsars. So while we were doing this burst oscillation study, we started a pilot survey of accreting millisecond exapulsars, and all these accreting millisecond exapulsars are transient systems. So they undergo an outburst, and during outburst only we can observe them and observe all the exotic features like detection of oscillations, looking at the broadband spectrum and so on, and other studies during their outburst. And why they are important class of low mass hexabinary systems? Because even if there are hundreds of neutron star low mass hexabinary systems known to date, there are only handful of accreting millisecond exapulsars, only 25 till date observed with different observations. So, and it is an important class to link between different types or different populations of neutron star systems. For example, yesterday we heard about radio pulsars, and the connection between the recycling scenario between the radio pulsars and the accreting millisecond exapulsars, which are believed to be the spun up by the accretion onto the neutron stars. So, and if one has to understand the different classes of the linkage between different population of neutron stars, this forms an important bridge. And we have found evidence of that linkage by having transitional millisecond exapulsars also, where when it is radio bright, it is X-ray off, and if it is X-ray bright, it is radio off. So such systems are also known, and only 3 till date we know are transitional millisecond exapulsars. So hence it's an important class of study of neutron star binary systems, which are indeed an important population. So with AstroSat, as I mentioned in our pilot survey, we began with the first outburst, which was observed in this particular source, SAXJ 1748. And this is on the left, this is the outburst profile seen with Swift XRD. And these shaded regions are the times when AstroSat observations were taken. And we also had simultaneous XMM Newton observation. Advantage of having simultaneous XMM Newton observation will come in my next slide. But with AstroSat using lag spacing, we could estimate or detect pulsations from the system at 442 Hz. Even the fractional amplitude was at very low value. And these are the pulse profiles observed. So with having several multi-instrument data from multi-instrument like S60, LAX-PC, XMM Newton, FXPN, we could do broadband X-ray spectroscopy. And I'm sure now I don't have to explain this diagram anymore in this audience. So we do have different emission components in the X-ray spectrum. And doing that broadband X-ray spectroscopy with reflection models, because when we were enforcing XMM Newton data as well, we did find strong iron line feature in the X-ray spectrum, which is a Wiener signature of a reflection component in the broadband X-ray spectrum. We could actually figure out the ionization component of the acute disk and so on. And it gives us a confidence on all the spectral fits and without having, because S60 and LAX-PC has certain constraints when we are doing broadband X-ray spectroscopy, but XMM Newton, on the other hand, has a good high spectral resolution comparatively. And one can estimate the flux from doing this broadband X-ray spectroscopy. And doing that broadband X-ray spectroscopy, we can estimate the magnetic field or estimate the magnetic field of the neutron star, which we did from these equations, assuming that the matter is following the magnetic field lines of forces, and we can estimate during this using these equations, set of equations with some constants, the magnetic field of the neutron star, which was an upper limit of 10⁹. So coming to another interesting transient, this is a neutron star X-ray transient XTJ 1739 -285. This was never classified as an AMXP. This was just always, I mean, there are RXT observations since 1999, but it was classified as a neutron star X-ray transient based upon the terminated X-ray burst observed in this X-ray binary system. And this is a long-term light curve with NAXI of that particular source, showing a very long outburst in 2019 to 2020. And these shaded regions are the times when AstroSat observations were done. And and there are some quasi-simultaneous new star observations also taken during the same outburst. And with AstroSat, we exploited data during 2019 and 2020 observations. And in 2019, which is shown here in the left panel, this is in the middle panel, it's like an entire light curve during 2019 observation. And we do see large variability in the count rate, which shows large flickering. And if you zoom in into that small segment of the flare seen along light curve, you basically see or zoom in into the flaring part of this light curve. And then the hardness ratio is shown in the bottom panel, which is nothing but the count rate ratio in the hard to the soft pad. And basically, it did show that during the flares they are hard. And in 2020 observation of AstroSat LATSPC, we actually did not observe any flaring event. It was a very sort of a boring and a constant light curve, along with one thermonuclear X-ray burst, which is zoomed in here. So this thermonuclear X-ray burst was also observed in one of the observations, and this was consistently found in both new star observations taken quasi-simultaneously with AstroSat. Now, interesting part came. We first tried to detect burst oscillations in 2020 observation because we knew that in thermonuclear X-ray burst we have well-defined algorithms now and techniques to look or search for burst oscillation. We did detect burst oscillation at 383 Hertz. And there are several nicer observations of this particular neutron star X-ray transient that do show thermonuclear X-ray burst, and there are detection of burst oscillations at 386 Hertz. We were getting an offset of 3 Hertz. And then in the first observation, which is 2019, did not have any thermonuclear X-ray burst. We tried to apply the same technique what we applied for thermonuclear X-ray burst study. And then we look at the short segments of the flare, searching for any evidence of spin frequency of the neutron star in the power density spectrum. Interestingly, we did find a very sharp feature at 386 Hertz, which is the spin frequency of the neutron star being detected with NICER. That adds up the confidence that the signature or the detection is real, and it's the spin frequency of the neutron star. And we try to do it for different segments, merging segments and things like that. It is very intermittent. So it fades away or it is not detected if we are looking at a longer light curve or things like that. So there are some sources indeed where we can find intermittent pulsations, and hence that made a discovery of a new accreting millisecond X-ray pulsar, which is not a persistent but an intermittent source. Of course, with LATSPC, we have to explore power density spectrum in more detail. So we did look at the power density spectrum to search for any quasi-periodic oscillations and things like that. And yes, in one observation, we did find a signature of some feature and around 0.83 Hertz in the power density spectrum, which was a QPO. I'm not going to go into detail of this. And of course, the broadband X-ray spectroscopy with LPC and LATSPC together did show significant changes in the X-ray spectrum in these two observations, hinting towards some change in the spectral state of the source, although not significant transition because the photon index, etc., were almost consistent within the error bars, but we did see some strong changes, like for example, a hard power law tail, which can give a signature of either contribution from the jet or inverse quantization from the hot electrons around the neutron star. So there were some changes in the broadband X-ray spectrum as well. Of course, we can apply the same technique now, considering it to be an AMXP to estimate the magnetic field of the neutron star. So this was the estimation we observed in the of the magnetic field of this neutron star system. And then yes, this led to the discovery of a new system and an important addition. Now it has been accepted by the community as a new AMXP in the literature. So after adding it, it is 25. Earlier it was 24. Yeah, so future prospects, last part of my talk. And with future, our future is bright in the sense we have new upcoming missions like STROVAX. We do have current missions, NICER, and very upcoming mission ExpoSat, which again yesterday we heard talks about. We have Expect on board, along with POLIX, which will actually allow us to do long-term monitoring observations. And then I did some simulations. They are quick simulations, but yes, tried to explore what we can do with expect in terms of fast time, etc. So we can look at this light curve. This is just with some assumed count rate for a very faint source. If we can do significant study or fast timing study with expect. So this is the light curve with just 0.2 mean count rate of 0.2 counts per second and assuming some power law shape of the spectrum and so on. And yes, so yeah, so we can do observe, but of course the significance might be lower in the case of detection of features like a low frequency Q flow. But if we have a very bright source, say of 1 crab brightness, where expected count rate could be 200 counts per second, we can have really significant detection of any fast timing features in the power density spectrum and so on. So hence, the future is bright in terms of upcoming mission as well. We can do a lot of simultaneously fast timing broadband excess spectroscopy along with polarization measurements. And that's all, I think. Thank you.
Thank you, Arul, for the wonderful talk. So questions now? Yes.
Nice talk, Arul. So you briefly showed the QPOs and how do we know they are coming from thermonuclear X-ray burst, but not from some sort of boundary layer or accretion disk?
You mean the QPO?
Right.
QPOs are not from thermonuclear X-ray burst. They were from the persistent emission.
And what's the ratio of those two peaks?
They are subharmonic. They're like one is harmonic and other one is harmonic.
So there's one question.
When you estimate the size of the star from the spectral modeling of thermonuclear burst, is it that you are assuming it's emitting from the entire surface?
Yes, there are some inherent assumptions. So we assume that first assumption goes in that it's uniformly spread throughout the neutron star surface.
But that may be a very
That
tricky assumption.
exactly. So then we do have. So I mentioned that we have two black and blue lines in the plot. So we applied an alternative technique also, which is known as FA method, which is assuming a contribution from the complementary emission. Of course, we cannot take into all the assumptions which are built in, but we can try to discard some of them. So one of them was the opacity, basically the contribution from the hard electrons. Yeah, so that could be taken care of, assuming having a multiplicative factor in our modeling, which is like you model the persistent emission, add that multiplicative factor, which is the contribution of the persistent emission during the thermonuclear X-ray burst. And then that can lead to some discrimination of systematic uncertainty propagating through the burst spectroscopy. But yes, there are those assumptions which are difficult to really handle if we are doing this burst spectroscopy.
I have another question regarding the burst oscillation. So what is the oscillation frequency relation with the rising and sometimes when you see the decline part?
So there are two set of proposed models to explain this. So I think for the I should come from the decline phase burst oscillations first. Now we have a paper in the archive with Professor Nils Anderson and his group, where we try to question the same thing, that what is the origin of the decline phase burst oscillation. And that was motivated by our discovery paper where we did see the offset of 3 Hertz. Although this offset between the burst oscillation and the spin frequency of the neutron star are observed in a handful of other systems as well. So what is the real origin of the decay phase oscillation? So generally it is believed it's sort of excitations on the neutron star surface, which can lead to this decay phase oscillation. And this R-mode excitation is based upon another assumption, which is traditional approximation, which is basically used by geophysicists. And this assumption basically, so there is one classic equation which is easy to explain here. So that is basically the low mode frequency excitation from the neutron star surface. And the offset between the spin frequency of the neutron star and this mode excitation. So if that is true with traditional approximation, then we should observe in this offset between the spin frequency and the decay phase oscillation all times in all neutron star systems. But actually that is not the case. If you really see the literature and observe all the measured split frequency and the burst oscillation frequencies during the decay phase of the burst, we do not really see offset in all cases. There are only handful cases where we observe. So the question which came out of the study was whether we are assuming it correctly to apply traditional approximation in the first place, which basically shakes the entire thing of or foundation of our modeling of these burst oscillations. So that was our paper questioning that whether we are having the right assumptions in explaining the origin of the decay phase oscillation. While for the rising phase burst oscillation, they are very well explained with observations also, so we do not really cast doubts on our explanation of the rising phase oscillations with respect to the spreading of the matter on the spinning neutron star. So that is kind of well explained because our observations also had a consistent consistent observational evidence that it could be a hotspot or the spreading of the hotspot or a matter spreading across the neutron star.
Okay, so we don't really have time for any more questions. So let's move on to the next talk. This is by Niranjan. He will talk about accretion onto strongly magnetized misaligned neutron star. So you have, I'll give you a warning after 10 minutes. You finish 2 minutes within that, and then you have 3 minutes for questions.
Am I audible? Yes, yes. Good morning, everyone. I am Niranjan. I am a BSMS student at IISA Mohali, currently doing a master's thesis project with Dr. Indrajit Chakravarti. The topic of my today's talk is accretion onto strongly magnetized misaligned neutron stars. Coming to a bit of an introduction. Yeah, neutron stars are a type of compact objects formed as a result of core collapse of massive supergiant stars. And their typical masses range from 1.4 to 2.1 solar mass. And they have extremely strong magnetic fields. And unlike black holes, neutron stars have a hard surface. Neutron stars, in presence of a companion, can accrete matter onto its surface. And the geometry of accretion flow is significantly altered by the presence of a magnetic field. So the motivation or the aim of this study is to self-consistently work the process of accretion onto neutron stars with a misaligned magnetic and rotation axis. The previous simulation studies have used a fixed adiabatic index equation of state without considering any radiative processes. But we know that radiative processes like bremsstrahlung and cyclotron are important in the sense that they take away energy from the accretion flow, and it is important to consider those processes. So, when considering those processes, the temperature in the accretion flow varies by a large order of magnitudes, and hence it is important to account for that variation, and hence we should use a variable adiabatic index equation of state instead of a fixed gamma. So Singh and Chattopadhyay in 2018 had studied accretion onto an aligned neutron star with a variable gamma equation of state. But we know that most of the neutron stars detected so far have some degree of misalignment in the rotational magnetic axis, making this study relevant. Coming to the assumptions we are using in this, we are using ideal magnetohydrodynamics for the analysis, and the magnetic field is assumed to be strong and dipolar. And the region under consideration is the magnetosphere, where the magnetic pressure dominates both plasma pressure and Ram pressure, making the matter to move along the magnetic field lines and get accreted onto the poles. In order to mimic the strong gravity, we are using a Papchinsky and Vita potential, and we transform to a frame co-rotating with the neutron star to use the steady state conditions. In this particular animation, you can see that in this particular frame, there's a time dependent component. So we should transform to a co-rotating frame to use the steady state equations. And the governing equations are given as the continuity equation. We have the momentum equations where the potential is modified due to the centrifugal force, and there is also a component of Coriolis force. Then we have the induction equation, the first law of thermodynamics, where we have included the cyclotron and Bremsstrahlung cooling, and the total energy conservation along the field line, where H is the specific enthalpy. A little bit introduction to the CREOS, which is the variable gamma equation of state. These are the equations where capital theta is the dimensionless temperature, which is kT by mc square, and psi is the composition parameter. You can see here that for theta very much greater than 1, which is the relativistic limit, it gives back the gamma approximately equal to 4/3, and in the other extreme limit, we get gamma equals 5/3. So we use the methodology given here, which is using the conservation of energy equation. We get an equation for dV/dr, which is numerator by denominator, where you can see that denominator is given by V minus CS square by V. When V equal to the sound speed, which is the CS, denominator becomes 0, and for it to be a physical situation, the numerator should also be equal to 0 at that sonic point. So we essentially use that condition and use L'Hopital rule to get the value of dV/dr at the sonic point. Similarly, we get an expression for d theta dr, which is the variation of temperature along the accretion flow. So once we know the velocity at the sonic point, the temperature at the sonic point, and the variation of the velocity and the temperature, we can integrate inward and outward from the sonic point to get the solution, which is the variation of Mach number along this flow. And also, since the surface of the neutron star is hard, the accreted matter should actually fall with a very low velocity to the surface. So that means that there should be a shock very much close to the surface. So we impose Rankine-Hugoniot shock conditions to get the solution branch which satisfies the surface boundary condition. So we have verified the derivation for the misaligned case with the aligned case. Here you can see that the black dashed one is one of the solutions for aligned case with one sonic point, and the solid red and blue lines are for the misaligned case by substituting the angle equals 0 degree. Coming to one of the solutions for misaligned, this is for chi equals 5 degree. And you can see that we are interested in the right solution, which is the accretion solution, and the other dashed one is another one which does not extend till the surface, so we are not interested in that. Here you can see that near the surface there is a shock jump which gives us this particular solution, which actually might look like a vertical line with not much significance, but it's actually the post-shock branch which satisfies all these conditions as well as the constancy of the Bernoulli parameter. So it follows a shock jump from here, and then gradually the velocity decreases, and in this region the density is much high. The velocity decreases and it gradually falls onto the surface of the neutron star. So this is a plot of the critical energy versus the location of sonic point. At high energies and as well as low energies, we only have one sonic point, and in the middle region we have 3 sonic points, which is the part which is interesting in the misaligned case. So this is a plot for critical energy versus critical R for different angles of the symbol is not coming. It's different misalignment angles. You can see something interesting here. The blue one is the plot for aligned case, And intuitively, we would expect that with small angles of misalignment, it should change bit by bit. But then you can see that the for small angle 5 degree, it is the orange one. It's actually not pointing correctly. You can see the orange one in between. So it's changing drastically from the aligned to the 5 degree, and then it changes drastically to the green one for 15 degree. And after that, it comes down towards the aligned one, and you can see for the 60 degree, which is the pink line, it becomes almost close to the aligned case. And for further increase in the misalignment angle, it becomes increasingly closer to the aligned case. So looking at the solutions obtained, for this is for Bernoulli parameter of 1, which is the one sonic point regime, and the solid line represents 15 degree, and the dashed red line represents 5 degree. You can see that there's not much difference here for one sonic point regime with inner sonic point, as well as here of the outer sonic point with only one sonic point. But in the intermediate 3 sonic point regime, this is for the plot for misalignment of 15 degree. You can see the solution. Now I'm changing to the one with 5 degree. The solution drastically changes. So there's a significant difference between how the solution behaves in this case. And in this particular solution, as we have seen in some talks yesterday, there's a possibility of a secondary shock of the solution passing through here, happening of a secondary shock and then following this particular solution. So that gives us a scope for observational signatures of having difference in the accretion curve with such small degrees of misalignment change. So preliminary analysis of how the solution varies with the change in surface magnetic field. This is for 10 to the power 9, 10, 11, and 12 Bose. You can see that with increase in magnetic field, the inner sonic point, which is this particular part, it shifts farther away from the surface, and also the regime of 3 sonic point regime decreases. So this is for one particular solution. Here the solid one represents 10 to the power 10 Bose surface magnetic field, and the dashed one represents 10 to the power 9. For lower magnetic field, you can see that the velocity closer to the surface is much lower. And now you can have a look at the variation in the y-axis. This is for 10 to the power 9 and 10, and this is for 10 and 11. So with increase in magnetic field, the solution, the velocity closer to the surface is much higher. Now looking at the variation of the solution with the accretion rate, this is for 10 to the power 14, 15, and 16 grams per second of accretion rate. Here the solution comes, the inner sonic point comes further towards the surface with an increase in accretion rate, which is a testament of the increasing cooling. This is one such solution where dashed line represents 10 to the power 14, a lower accretion rate, and solid one represents higher 10 to the power 15, which has much higher cooling and hence lower velocity closer to the surface. So the conclusion, accretion onto misaligned neutron stars have been solved through the shorter accretion funnel in this work, and we have found that even small changes in the angle between magnetic and rotation axis can actually produce significant changes in the accretion solution. So if there is some mutation like dynamics in the system, it could actually produce some significant observational signatures, which would be interesting to look at. And matter was found to become transonic farther from the neutron star with an increase in magnetic field or a decrease in accretion rate. And another goal is that results from this study can be used as initial parameters for simulation studies in the same system, which could equip us to study the variabilities. Thank you.
Okay, questions for Niranjan?
Explain it to us why low magnetic field leads to multiple sonic points of the tendency of the shock formation. You showed various solutions and you showed that for low magnetic fields, the multiple sonic points were formed. Somewhere when you were showing, just before the accretion rate solutions, you showed that as you increase the magnetic, this I think somewhere here, as you increase the magnetic fields, the multiple sonic points reduce into single sonic points.
Yeah.
Why it happens?
Like the multiple sonic point regime, it's because of an interplay between the rotation and the magnetic, like so.
Gravitation.
Yeah, interplay between the rotation and gravitational force. So as the magnetic field increases, that comes into play here, and it becomes a single point.
Basically, if something is falling very fast, there is no question of forming multiple sonic points. Okay. So if this magnetic field is very strong, then what it does, it takes the entire matter and just forces it to follow the magnetic field. So the rotation doesn't have time to, sort of,
push the
alter the, halt the inflow.
Yeah.
Okay. So therefore, you don't have magnetic.
Small question.
Can I, so for now, just one question and then let us other questions. If there is time, I'll get that.
For all this plot, you're showing on the x-axis some R radialism.
Yeah.
But usually for magnetic, if there is magnetic field, the matter will come and then it will move along the magnetic field line and fall on the pole, right?
Yeah.
So what does this R represent?
Yeah, so I forgot to mention that, like.
Don't feel sorry about everything. There's no problem.
Yeah, it's actually following this geometry itself,
Right.
but then we are using R as the radial distance itself, but the angle of following this is constrained due to the geometry of the magnetic field. So there's a relation between R and the coordinate theta. So only R is mentioned here, but theta you can get, so it's uniquely determined.
So the magnetic field lines, okay, it's following the magnetic field line,
Right.
and then you are converting, assuming it to be a
Some straight.
no, assuming it to be a dipolar field, then you are converting that, mapping it into the radial.
Okay.
R, normal radius.
Normal radius.
Yeah,
The
we are
radius
mapping
is
it.
still in the units of
It's
radius of the
historical.
neutron.
Sorry,
What is 1 in R? Radius of the neutron.
it's 2 GM/c².
This is what we have converted that into, generally speaking, when you have magnetic field, everybody starts to, map everything in terms of the Alvin radius. What we have done, we have converted it to the social radius because it is compact enough.
So I have a very quick question about your future plans, because it's interesting to see different solutions
Yeah.
with the change in the magnetic field also. So do you have any plans to maybe apply to observations or something? Because
Yeah, like first of all, we are like planning to, right now it's just cyclotron and bremsstrahlung. So we are planning to see how synchrotron comes in here, because at higher like magnetic fields closer, synchrotron emission can also play a role. So once we are done that, probably matching with observations can be looked at.
And
You're-
sorry.
Yeah, go ahead.
So regarding dipolar magnetic field assumption, so yesterday as we were discussing in Deepank's talk also, so that assumption may not hold anymore because with the polarization measurement and so on.
Yeah.
So do you have any plans to incorporate higher multiples or
Yeah, actually,
higher models?
currently no, but we have to look at that at some point of time.
Basically, this is a case for pulsar,
Yeah,
pulsar.
Yeah.
Okay.
I met it.
So if you reduce the magnetic field, say you have gone up to 10 to the power 9, if you go to 10 to the power 8, you're in the regime of millisecond pulse.
Yeah.
Okay, so then you have a direct application with the observations of millisecond
Yeah,
pulse.
so I had used the initial conditions for accreting millisecond pulses, but in that case, the cooling is not sufficient with the cyclotron and bremsstrahlung. So in that regime, probably I'll have to look at synchrotron to get the post-shock branch closer to the surface and then follow it up.
So we are
So just one last quick
developing
question.
actual full MHD simulation for this.
I'm interested in the shock which is forming at the surface of the neutron star.
Yeah.
At the end. So you plotted through Mach number. Can you tell me what is the velocity jump there? which velocity to which velocity will jumping at this surface, this left side shock?
This particular jump is happening from around 0.8 C
To
this particular value. I'm not sure, but the boundary condition we are using is 10 to the power minus 3 or less C at the surface.
Basically, if you look at this solutions, so you will have this branch going, and near the surface you will have these kind of branches, right, which are of higher entropy. So this one comes and we are checked which branch it is jumping in. Okay, all these are with lot of bremsstrahlung and cyclotron emission.
it's very strong shock.
It's a very strong.
Yeah. So
Actually, he has missed because he's hurriedly doing it to be able to do the talk. There is a secondary shock also. Okay.
Outside.
Yeah, outside. So we have missed. He has missed it. So, but she wrote a paper sometime back. No, I mean this year it was published, where we also got a signature for spectral signature for the secondary shock. So we had spectral signature for both the shocks.
That will be weaker shock.
yeah,
It's not necessarily very weak. So this is very strong, the primary one. The secondary is not really very weak.
Okay, so let's thank the speaker once more. And we are running 15 minutes late. So when do you want to start the session after tea? It is supposed to be at 11:30. So maybe 40, 35.
35.
Okay, so we'll take a short break and come back at 11:35.
ये चीज मैं कुलदीप को बोलूंगा, कुलदीप का जो पेपर था क्या ना लगा for what?
Two talks, then lunch. It's Sujit and then Monomita. Monomita is Sujit's. Well, I said was. But once a PhD student ever.
I remember this because I was making a stand my and then I remember she I was saying totally squeezed.
Yeah.
Suraj, very topic.
अभी पेन ड्राइव अपने पास रखो, बीच में जब भी फ्री रहोगे कर देना, ठीक है? एक ही फोल्डर, एक ही फाइल
Where did the hard copy go?
मैं उनको पेन ड्राइव से दे दूंगा अभी दे
I already called.
What?
তাহলে আমি 20 মিনিটের মধ্যে আসলে বলবো, তারপরে আপনি 5 মিনিট পর হ্যাঁ মানে 5 মিনিট তো করছেন নাকি ऐसे लगता
है आपको क्यों बोल रहा जाना जाओ नहीं चलेगा किसी का ऑन द वे जाके हो जाएगा ओके
They took the bus.
Evening we have to go, right? For evening plan. What plan? To buy few things there. Did you announce anything? I don't know, it's just starting, right? No, that is what I'm telling you. So I will anyway have to go to buy stuff. No. Now you are telling me.
No, but they want to spend some time. It's not like they'll just go and... Okay. Let's get going. So next up we have Sudhir Bhattacharya from TIFR. He'll be talking about the permanent electricity of a millisecond sector.
Good morning. This talk is based on this paper. This paper published in 2020. And at the beginning, let me very briefly say what this work about. So we know that transient gravitational waves from mergers of many neutron stars and black holes have been detected, but continuous gravitational waves so far have not been detected. Only we have got upper limits. One such source or one class of such sources to emit continuous gravitational waves is spinning neutron stars or pulsars, in which the mass distribution of the neutron star is asymmetric around its spin axis. For example, here, the spin axis is perpendicular to the screen, and you see that this radius is smaller than this radius. Then we expect continuous gravitational waves. Here, we inferred that for a particular neutron star, PSR J1023, which is a millisecond pulsar, the radius in this direction and that direction are different by about 10 micrometers. While the usual radius of a neutron star is about 10 kilometers, this difference is about 10 micrometers, and that we inferred from a distance of about 4,500 light years. So before I say how we do it, let me quickly mention that when this claim or this result actually created a lot of enthusiasm and interest among the international community. For example, when this paper was first, I don't know why it is cut at the big below. Yes. So when this paper was it became public in August 2020, in the middle of Corona period, two international teams, the two main teams which work on continuous gravitational waves and try to find such waves observationally. One is independent research group in Germany, another is the LIGO continuous gravitational wave group. They invited me to give talks on this paper within a separation of about 7 days. So now coming back to this work, so here's the plan, and I'm not wasting time to read this. And here is a very brief background. I have already mentioned that if there is an asymmetry around the spin axis of the neutron star, it should emit gravitational waves, and that wave should exert a negative torque on the neutron star, and because of that torque, the neutron star will spin down, and this is the formula. This is the formula of nu dot, that is rate of change of spin frequency of the neutron star due to gravitational wave. I is the moment of inertia. Q is the mass quadruple moment, which is I into epsilon, where epsilon is the fractional difference in the radius in two directions, which means that if the radius in one direction is 10 micrometer less than the other direction, and typical radius is 10 kilometers, so 10 micrometer divided by 10 kilometer, epsilon will be about of the order of 10 to the power minus 9. That is called ellipticity. So that's what we got. Now, of course, as I said, that we have not directly detected continuous gravitational waves from these sources. The upper limit is of the order of 10 to the power minus 8 now for the best cases, and we say that it should be 10 to the power minus 9. So this is the reason we show that we have not detected so far with LIGO. But this nu dot, the rate of change of spin frequency of the neutron star, this we can measure by electromagnetic observations in radio, in X-ray, for example. And therefore, from this nu dot measurement in electromagnetic observation, as the pulsars slow down, we could infer that there is an ellipticity in the structure of the neutron star, and therefore it could emit gravitational waves continuously. But why do we consider this particular source, PSR J1023? Why this source? So here are some reasons. So far, there are only 3 millisecond pulsars, which are called transitional pulsars, which have shown both the accreting state, that is the low mass X-ray binary state or LMXB state, and non-accreting radio pulsar state, that is the radio millisecond pulsar, RMSB state. Both RMSB state and LMXB state. Only 3 sources have shown, and this is one of them, this source. In the RMSB state, the accretion rate is very low, almost 0, and therefore the pulsar wind coming from the pulsar stops the accretion. So accretion stops, accreted matter doesn't fall onto the neutron star, and there is pulsar wind. This is the pulsar phase. This is the radio millisecond pulsar phase, RMSB phase. And in the accretion phase, low mass X-ray binary phase, the accretion rate is high. Therefore, the pressure of the accreted matter is very high. So ultimately, it pushes through the magnetic field of the neutron star, and it populates the region around the neutron star. There is no more vacuum, and therefore the fills with the region around the neutron star fills with plasma, which is the accreted matter, and therefore the pulsar wind is quenched. And this is the LMXB phase, or low mass X-ray binary phase. But we'll show, or we'll discuss at least, that for certain sources, for example, this source, and this is also theoretically found, that if the accretion rate is not so high, then accreted matter could reach the neutron star surface, but still in certain portions of the region around neutron star, it is still vacuum, where accreted matter cannot reach. Plus, there still it is vacuum, so the pulsar wind is still active. So in such cases, both accretion and pulsar wind simultaneously can be active. So this is one such source. So now, and so why this source? Because this source is an ideal and unique source to estimate the neutron star ellipticity, because this is the only MSP, millisecond pulsar, for which the spin down rate has been measured for both RMSB and LMXB phases or states. However, this source shows many complex observational aspects from radio to gamma rays. Some of these are unique, very unique, not seen from other sources, which, when not fully understood, could introduce systematics, making our conclusion unreliable. And this is the problem for many astronomical problems. Astronomical data are dirty, so it is usually very difficult to make clean conclusions. So what's the way forward? How do we make our clean conclusion? So this is the way. Therefore, in our formalism, we rely on angular momentum conservation and energy conservation, which are basic principles of physics and which should be valid irrespective of observational aspects. That's what we hope or expect. And when using these basic principles, we'll have our conclusion, we'll have our picture, we will apply them to some of the observational aspects, and we'll show that those main observational aspects would be explained. Now, these problems. What are the unique complex features of these sources? Let me describe some of them, many of them. So, this is in the LMXB state. This is an accreting pulsar. We know it's light cylinder radius. I'm not explaining what are these things. I'm assuming that it's known. So its distance is known. Mass is known with some uncertainty. Spin frequency is known. And its light cylinder radius, which depends on spin frequency, is also known. The co-rotation radius, where the Keplerian angular speed of the disk material is same as the neutron star angular speed. This is also mostly known. the uncertainty is because of the mass uncertainty. Now coming to these unique properties. You see that nu dot, rate of change of the spin frequency of the neutron star, that is, it's basically the decrease, that is, the pulsar is slowing down. So nu dot in the RMSB phase is this, and nu dot is LMSB phase is measured to be this, which means in the LMSB phase, which happens within a say weeks or months of the RMSB phase, there is 32% increase in spin down rate in the LMSB state. This implies an extra torque, huge extra torque of about 10 to the power 31 CGS unit. This is not a matter of joke. Where this such a extremely high torque comes from? So what should be the agent? See, what is the change from the non-accreting phase to accreting phase? It is only the accretion. And accretion can spin up the star. It does not spin down. Moreover, the accretion rate is extremely small. It cannot explain this high increase of the nu dot. So what is the source of this increase, sudden increase?
Rate, roughly estimated accretion rate?
So accretion rate is of the order of 10 to the power minus 13 imsan per year or something.
So in this source, when there is a accretion phase and the radio phase, both the phases has also been observed.
Yeah, I couldn't hear you. Just one.
Yeah. So in this PSRJ 1023, as you mentioned, that there can be a stage where both accretion is never stopped completely. So there can be an accretion phase coincident with the radio bright phase also. So has it been observed?
No, it's in the RMSB phase. In the RMSB phase, accretion is stopped. So accretion is stopped, only pulsar. In the LMSB phase, we interpret, this is the interpretation, and some other people have also interpreted, because without this interpretation, we cannot explain anything for this source. That pulsar wind is still active when the accretion is going on. So this is one problem, that where does this high torque suddenly comes from? And the second thing is that in the RMSB phase, there is some gamma ray emission from the source, which is natural. It comes from the pulsar wind, we know. But in the LMSB phase, there is also gamma ray emission, which doesn't happen usually. And that gamma ray emission 5 to 10 times higher than that in the RMSB phase. So these two are extremely difficult things to explain. And moreover, there are more things. So this is one of the, this is a unique source apart from another transition pulsar, that in the LMSB phase, it shows two very stable states. This is the light curve, the X-ray intensity versus time, X-ray intensity versus time. So you see that black is the high mode, higher intensity phase, and blue is the lower intensity phase. It's extremely stable to different phases. These are the intensities and typical time durations of these two modes. And there is another mode, we are not talking about it. So one has to explain that as well. Moreover, we see the X-ray pulsation, the millisecond period X-ray pulsation only in the high mode, but not in the low mode. So what's the explanation? And then some people have measured from the spectral analysis, X-ray spectral analysis, the inner edge radius of the accretion disk is about, say, 20 kilometers or 25 kilometers or so, which is very close to RCO, co-rotation radius, which means in the high mode, which means that in the high mode, the disk could be inside, this can extend inside the RCO, and that's the criterion for X-ray pulsation. So if we consider this is correct, and that can explain the pulsation. What is that?
Could you use that?
But, and then we can say that the source in the high mode, for that, for high mode, the source, the RM is less than RCO, and for low mode, RM is greater than RCO. Therefore, in low mode, there is no pulsation. So, considering this light, everything is fine for this. Although one has to understand that why there are two different modes, but that is possibly we need some stable agent to get these two stable modes. But that is because that possibly this goes inside RCO and goes outside RCO. That explains pulsation. That explains the spectral result. But there is a huge problem. The problem is that this source has been observed in the RMSP phase. And the RMSP phase, we have measured nu dot RMSP. And from nu dot RMSP, we can estimate its magnetic field. That is the standard way we estimate. If we consider that the slowing down in the RMSP phase is only due to electromagnetic radiation, without considering gravitational radiation, only that is the standard way. If we do that, magnetic field comes out to be about 10 to the power 8 Gauss or so. Mu is the magnetic this dipole moment. Magnetic field come out to be about 10 to the power 8 Gauss or so, which is standard for this kind of sources. But considering the low luminosity of this source, we know that the accretion rate is very low for this source. If we consider this magnetic field will stop the accretion flow. This will not enter the light cylinder. All these explanations consider the accretion disk enter the light cylinder. The standard wave accretion happens. These things, spectral results are explained, and all these modes are explained, etc. But if we do not consider gravitational wave, just the electromagnetic radiation in the RMSP phase, magnetic field is high, 10 to the power 8 Gauss of the order of accretion disk would not enter. So this is a huge problem again. And then there is this, the source of gamma rays. So I have already mentioned that these gamma rays could originate in the RMSP phase from the pulsar magnetospheric activities due to pulsar wind, and same should happen for LMXB state. Otherwise, there is no other source of gamma rays for this source. So the pulsar wind should remain active in the LMXB phase, which is consistent with the fact that the accretion rate is very low. So these are the problems. Now, to solve this problem, so I'll skip this. So there are several problems I mentioned. But as I mentioned, what we'll do, we'll start with angular momentum conservation or torque budget equation and energy conservation considering gamma rays. And we'll see that some of these problems will be solved self-consistently and mutually each other. So our formalism now. So we write the equation. That is in RMSP phase, we have measured the nu dot, total nu dot, which is nu dot RMSP. So there can be only two components, nu dot due to pulsar wind and nu dot due to gravitational wave, PW and GW in the RMSP phase. And in LMSB phase, there can be, again we have measured the nu dot LMSB, total nu dot. There can be three components, due to pulsar wind, due to gravitational wave, and due to accretion. Now, here I emphasize that we do not a priori assume non-zero values of nu dot GW RMSP and nu dot GW LMSP. That means we have not a priori assumed that there is gravitational wave emission from this source. We have just put the term for the sake of completeness, but these terms could be zero. We'll see whether they can be zero or they have to be a non-zero value, have to have a non-zero. So, as I mentioned, rather first we will try to see in a direct way if at least one of them, that is one of these two terms, gravitational wave term, must be non-zero. And if yes, then in what condition Then we will estimate their values by solving these equations. And note that I have already mentioned, judging from the low X-ray luminosity, this accretion term cannot be more than 5% of nu dot LMX bit. Hence, for simple calculations, we neglect this term. But of course, for later, we will consider it. Now, these are the two equations from torque budget, angular momentum conservation. Then we consider this energy. So this SD is the spin down. So spin down energy, spin down power, luminosity power due to pulsar wind in the RMSP phase, and that same in the LMXB phase. This can be written in two ways. One is in terms of nu dot, and another in terms, this is the theoretical, and another in terms of observation. That is luminosity, gamma RMSP is the gamma ray luminosity observed in RMSP phase, gamma ray luminosity observed in LMXB phase, and eta is the gamma ray emission efficiency in each case. So two ways. This is the theoretical way, we can write this. It is the observational way. And from this, we take the ratio, we get this, and we get our three equations. First two from torque, and second and third one is from energy. Now these three equations, so how many minutes?
So you have spoken for 22 minutes.
22 minutes. Okay. So if we now ignore these gravitational wave terms, both the gravitational wave terms, then we get from observation, this ratio comes out to be this 1.32. This ratio comes out to be 5 to 10, that is observation. And therefore, this eta ratio, that gamma ray efficiency in the two phases, their ratio is 3.8 to between 3.8 to 7.6. However, this eta ratio, we do not expect to be much more than 1. Why the eta, the gamma ray efficiency, will increase if nothing else increases? If it increases, it should remain close to 1. It could be 1 point something, but it cannot be 3.8 or something. Or the only way this can happen, this can be so large, if in the LMXB phase, the pulsar wind actually interacts with the accretion flow, and from there gamma ray emission is coming. But if that happens, then the accretion would be stopped again outside the light cylinder. Then we cannot anyway explain the X-ray pulsations, the X-ray modes, and the increase of the huge increase of the nu dot in LMXB. So this is not feasible. It should be close to 1. Therefore, we cannot neglect this term, particularly nu dot GW RMSP. So then we take these three equations and we formally try to solve them. We solve them graphically. You see that from these equations with a little algebra, we get this one equation. And you compare it, the straight line equation y equal to mx plus c, you see it's the same. It's y equal to mx plus c. It's color coded, you can easily see it. So you see that then if we plot this is the something of interest. This is nu dot due to gravitational waves, and we plot against this, we get this straight line. This is considering the other in the LMXB phase, the gravitational radiation is 0. But which is not very physical. If there is ellipticity in the RMSP phase, the ellipticity will not vanish in the LMXB phase. So we consider the other possibility that remains same. This remains same. Then we get this dashed curve, and this is for this gamma ray ratio of 5. If we consider gamma ray ratio of 10, we get this. So the point is that this ratio, which should not be much greater than 1, which should be mostly here, we get a non-zero value of this nu dot GW RMSP, which means in the radio pulsar phase, the neutron star is emitting gravitational waves. And that is without considering the requirement of accretion disk. Without considering the requirement of accretion disk, we have got this. So now this is a conclusion Now, if we put some known values and some standard values, we get, I'm not going into the details, I have put some known values and standard values. And I have got this magnetic field is really low, it's of the order of 10 to the power 7 Gauss. The mass quadrupole moment is 10 to the power 36 CGS unit. And the ellipticity, which I mentioned, is of the order of 10 to the power minus 9. That means the difference in radius is of the order of 10 microns or so. So this is for one set of values. So just to check that what values we get. Now I come to that. So really, how much time I have? Can I speak for 5 minutes?
So you have spoken for 25.5 minutes. So whatever.
So 4.5 minutes I'll find. Anyway,
you have 5 minutes. Yes, please go ahead.
So, so implication of formalism means now that we have come to some picture, we'll apply it to some of the main problems, observational, complex observational aspects of this source. And we'll try to explain that this picture can explain those things. So the first one is about the accretion, high mode and low mode. So in the high mode, for this specific value sets, we got Rm equal to this in the high mode, and RCO equal to this, which means in high mode Rm is less than RCO, which is which can explain the X-ray pulsation, observed X-ray pulsation in the high mode, and also it is consistent with the observed Rin value from the spectral analysis. And in the low mode, we find that Rm is greater than RCO for this one set of examples. Rm is greater than RCO, therefore the disk is outside the co-rotation radius RCO, and therefore we do not expect pulsations, and that's what we find, that low mode there is no pulsation. And we find two modes because the disk goes inside RCO and goes out of RCO, which is a stable thing. That's why we see these two stable modes. And then I have already, there are two other main problems. One is that why there is an increase of torque in the elementary phase, spin down torque, and why there was the increased gamma ray emission. Both of these I have included in my formalism, in the equations. The only thing remains is why there is an increase of pulsar activities, which gives rise to a higher gamma ray emission in the elementary phase. So here I already mentioned it, that if the accretion rate is high but not too high, then this is a simulation done by these people, Parfrey. So this is not my paper, this is some other people done simulation. So this yellow is the accretion disk. You see that it goes onto the neutron star, but it does not spread in this region. So this region is still vacuum and pulsar wind is still active. And what happens when the accretion disk goes inside it, these magnetic field lines, they open up. Because there is torque, they move around, the magnetic field is frozen in the plasma, and then they open up. So they open up, and therefore, now there will be an increased pulsar activity, the increased pulsar wind, because there are so many more magnetic field lines. How many more? It's increased by this factor. RLC is the radius of the light cylinder divided by Rm. Rm is here, up to which disk is extended, square of that, because we take the area. So this is roughly the factor by which the power of the pulsar wind will increase, we expect. And that comes out to be around 10 from our calculation. And that's what we see from the gamma ray emission, that 5 to 10, a factor of 5 to 10 is increase in the gamma ray emission in the elementary phase. So this our formalism self-consistently explains the main observational aspects. So we start with general torque budget equations, and here is some energy budget equation. So if we proceed on the way, we get that pulsar ellipticity, that is gravitational radiation, as a requirement, and then that explains the relatively low pulsar magnetic field, and therefore the high mode and low modes, and the pulsation in the high mode, and observational X-ray spectral observation, and so on. And that in turn explains the open up of the more magnetic field lines, because there is now a disk due to low magnetic field, open up of the magnetic field lines, and higher gamma ray in the LMSB phase. So now what we have done, 2-3 more slides. What we have done, now that we have our picture in place, we try to constrain parameters of this source. In order to constrain source parameters, we used full ranges of measured parameter values and entire expected ranges of other input parameters values, and hence more than, so we considered a grid of many parameters. So basically we have a billion, more than a billion, almost 2 billion combinations of input parameter values I tried. And then I used the following constraints. I imposed the following constraints, that in high mode, Rm is less than or equal to RCO. Low mode, Rm is greater than or equal to RCO, which is a requirement. And from the observed irradiation of the companion star, it is from the observation, the optical observation. We put this constraint, that is the spin down power of the pulsar wind is greater than this. And then just now I explained that this is another constraint. And the moment of inertia of the neutron star should be in this range. I found it a detailed relativistic calculation in another paper in 2017. So these 4 basic constraints I have applied, and I considered billions of combinations of input parameters. And I find if we put this constraint, that is in LMSB phase and RMSB phase, ellipticity is same, then these are the values of Q, D, M, mu, D, Q, and epsilon. So B is the magnetic field, which is, as I mentioned, it's relatively low. Q is of the order of 10 to the power 36 gram centimeter square, and epsilon, which is the fractional difference of the radius, is again of the order of 10 to the power -9. The main thing, okay, and then we relax that constraint, and we consider that maybe in the LMSB phase, the pulsar ellipticity is slightly increased because of accretion. So I put in instead of equal to here, I consider greater than or equal to, and I still get this kind of range of Q. And if now there is no constraint at all, that is, there is no mutual condition between the pulsar ellipticity in the LMSB phase and RMSB phase, then this is the range. The thing to be noted is there are 2 things, that the values remain similar, 10 to the power 36 gram centimeter square, which means a pulsar ellipticity of the order of 10 to the power -9, or an additional radius in one direction of about 10 micrometers. And other thing to be noted, that even if there is no mutual condition, the lower value is not 0, it is higher than 0, which means in both phases there is a pulsar ellipticity. That's why I say that a permanent ellipticity of this pulsar. So here is the summary. PSR J1023 is an ideal and unique millisecond pulsar for the neutron star ellipticity measurement, as this is the only MSP for which the stellar spin down rate has been measured in both RMSP and LMSB steps. And we do not we do not apparently assume a non-zero ellipticity. This is important, but we get a non-zero value if we consider neutron star torque budget and the pulsar magnetospheric origin of gamma rays in 2 states. So we do not start with pulsar ellipticity, but we get one. This simple formalism self-consistently explains X-ray observations and gamma ray observations in the LMSB state. We explored a large range of parameter values for the first time for this source and inferred a permanent pulsar mass quadruple moment in this range and ellipticity range of the order of 10 to the power -9. And thank you.
So, thank you for this very interesting results. So, very quick questions from, okay, Professor Joshi.
A very nice talk, Sudeep. I've not kept track of this pulsar. So has it switched back to RMSB? And if so, the other question is from the archival observations. You mentioned the pulsar wind luminosity being estimated from the irradiance of the companion. So
Some limit.
yeah. So is there a difference in the RMSP and the LMXP phases of the irradiance from the optical observations?
See, in the RMSP phase, you can identify the star cleanly, and there you can find the change of star's temperature and star's luminosity, and from that you get that. The LMSB phase, there is so much radiation in optical from other sources as well, you cannot do that.
Other questions?
Yes.
Okay. Okay, yes.
So I had a quick question about the accretion disk area or estimate from the excess spectral parameters. Perhaps, we were in discussion about the wrong estimations by Campanite and others and the team members. So what they quote is around 26 kilometers as the measure.
But we have now done independently as well.
Yeah, so but the radius is still small.
No. So it's not your thing, but later I have done independently as well, and I found that XMM Newton and from New Star, from both we are getting some values. So the thing is that it's small, but it's not that small, and basically that is the lower limit. So the thing is that there's no time, but you have to show that the lower limit of Rn is within RCO. If you can show that, for example, with 3 sigma or something, then that serves your purpose. So yes, there was some problem in there.
In the spectral fitting. Or rather, not even the spectral fitting.
Not spectral fitting. How they from spectral parameter, how they write the final number. So there is some problem.
There was some.
There is some problem.
Mistake in the
Maybe some problem in the spectrum fitting as well. But we have now done this independently, and we have found a similar thing what they have said.
Okay.
Okay. So let's thank the speaker again. And now for the last talk before the lunch, we have okay, no, it's not the last talk before lunch. So the penultimate talk before the lunch. So we have Monolitha Chakraborty talking about neutron star low mass X-ray binaries in the high luminosity regime. I'm just trying to keep the audience motivated. So, Monolitha, you have a total of 25 minutes. So, if I keep 5 minutes for questions, then I'll give you a warning after 15 minutes. Okay. You will have 5 minutes after.
Thanks. Am I audible? Am I audible?
Yes.
Okay, so good afternoon, everyone. Good afternoon. Yeah. So first, I would like to thank the organizers for inviting me to give a talk here. It has been an enriching experience, both in terms of scenery and as well as scientific discussions. So today I will be going to talk about what neutron stars do, particularly in the high luminosity regimes. I will take a little bit of a liberty and give you two specific scenarios. And this work has primarily been led by my ex-PhD student, Unnati, who is now a postdoc at TPU, and along with all these other collaborators. So the good thing about having a talk on the last day of a conference is you don't need to give much introductions. So thankfully, all the other speakers have already introduced the basics of neutron stars. I would only like to remind you about the different types of neutron stars that we see. In our spectral color diagram, we see that neutron stars can be broadly distinguished into two classes: the atoms, which are a little bit the low luminosity sources compared to the other class, which is the Z source. And these Z sources are basically observing the most high luminosity state, very close to the Erickson luminosities, and they show high variability. And along the Z track, you can see the different branches like a horizontal branch, normal branch, and flaring branch. And you can see that the spectral and the variability characteristics are very distinctly different along these tracks. Which basically means the disk and the corona transitioning in different configurations along the track, and how they are doing so remains an open question. So let me go to by the way, I just wanted to mention there are exceptions to this, which is mentioned by one of the speakers, 1701, which shows kind of transition between these two states. The first example I would like to give you is related to the continuum behavior. So for that, we have already shown this figure many times, but only key point to take away from here is that the emission from neutron star X-ray binaries can come from very complex regions, and that disk boundary layer, corona can all contribute to the spectrum. And secondly, in the spectral behavior, we can also often see very strong reflection features which are coming from reflection from the corona on the disk and so on. So let's talk a little bit about the lines themselves. So this spectral line. Okay. Sorry. Oops. Sorry. Something is going on.
No, this is the lower one is for going back.
Oh, that's fine. Okay, sorry. Okay, so talking about lines, the lines are very interesting features. They come from the inner regions of the accretion flow, and they contain all the signatures of the dynamical rotational effects as well as the relativistic effects. And on top of that, the line profile is governed by these features, like, for example, the inclination of the binary, the inner and the outer radii, as well as the emissivity profile of the disk. So, sorry. So a good modeling of the line profile can give you a handle on the measurement of the neutron star mass and radius, which is one of the primary goals of neutron star physics. For example, you can see the famous M and R diagram, and the solid line represents the equations of states, and this green band that you see basically here. Sorry, this green band that you see is basically one of the constraints that have been put by line measurements. So they are indeed very interesting to look for. Apart from that, variability is also something we are very interested in, and many speakers before me, including Arijit and others, have given a very detailed introduction about the various variability models. Again, the key takeaway point from there is basically looking at how the variability behaves over energy and looking at the lag behavior, one can put an idea of how the propagations are developing at different regions of either the accretion disk or the corona, and they're propagating through the accretion flow. Okay, so given that intro, let us talk about some of the studies that we have been doing. So one of the examples is this classical Z source, which is very soft and typically remains in the very high luminosity state. So there, this particular source was observed using AstroSat over 5 different epochs, and you can see the Z-like tracks. This is particularly in the normal branch and the flaring branch. And interesting things we need to note here is the zoomed in. You can look at the zoomed in image. The thing to note here is the source state stays in 2 distinct states. One, in the region where it's come, there is not much variability, and then immediately it transition back to this particular state where you can see highly variable flares within a very short time, and corresponding to that in the HID, this corresponds to this flaring branch of the hardness intensity diagram. So it interesting to study what is happening to the binary in this as it transitions from between these 2 states. So once we look at the radiative behavior of this, we see that the spectra is roughly well modeled by a standard boundary layer, a very hot boundary layer close to the neutron star, a multicolored disk black body, and quantization in a hot carbon. Okay. But interestingly, when we look at the behavior of the spectral parameters with the flux, the things to note here is, here the red colors represent the normal branch and the blue colors represent the flaring branch where you saw the high variability. So the thing to note here is that as the flux increased, after a while, as the source transitions to the flaring branch, the temperature of the inner disk suddenly sharply, sorry about this, sharply rises, which basically means with increasing accretion, the disk is probably shrinking inwards, and along with that, the temperature of the hot spot, which is there at the boundary layer of the neutron star and the disk, is also getting heated. The boundary layer is basically getting heated up. So that is also observed from this transition layers. And we also saw that the componization is showing an increase in behavior in the flaring branch. This is just a contribution, overall contribution, and that's probably because there's a lot of seed photons available to componize the photons. We also look at the nicer spectrum along with astros. There is only one case there were simultaneous observations, but there were few other nicer observations. And nicer is typically a softer instrument compared to astrosat. And in nicer, we could actually observe the boundary layer emission a little bit more better. And we saw that in the nicer emission, whatever the changes the source is showing is primarily driven by the expansion of the boundary layer, the hitting layer at the transition between the neutron star and the disk. And not only that, in the nicer spectra, what we saw is an emission line, which is a very cool thing. And over the 8 nicer epochs, this was very strongly present in at least 2. And this emission line had an energy roughly around 6.5 to 6.7 keV. And the inner disk radius turned out to be around 6 to 10 gravitational radii. So we looked at interesting things, that the line energy shows a very strong correlation with the normalization of the multicolor black body, which is basically the inner disk radii. So this correlation could be okay. We don't have a wide variation in the normalization or the inner disk radii, but whatever we have, we could actually model it using a simple gravitational redshift correction of the line profile. And from there, we could get an estimate of the black hole mass, neutron star mass, which turned out to be 2.3 solar mass, slightly on the higher side, but that can be explained by the systematics that goes in calculating the neutron star mass. For example, the scattering factor, the anisotropy, and so on. Also, the rest energy of the line turned out to be a little bit on the higher side at 6.9 keV, which basically signifies a very highly ionized disk, which you would expect at such high velocity. Okay, so that's good. But now, what about the variability? So in the HID, as I told you, there are 2 branches, the normal branch and the flaring branch. So we looked at the variability behavior in these 2 branches, and what we saw is at the normal branch, the variability behaved like this. I'm sorry, it's got that, but it basically, this is the profile over the 5 astrosat epochs, and this is for the flaring branch. So what can we take away from here? The first thing is there is a very power law kind of red noise.
Top one is the pointer.
Okay, sorry. Power law, which is the red noise that we have been hearing about. This is basically related to possibly related to the inhomogeneous accretion. Again, we learned about it in the other talks as well. In the very high accretion flow. And the other interesting thing we saw is there is a peaked noise. It's not exactly a QPO, but it's still quite a significant peak that is sitting there. And this peaked noise is primarily present in the flaring branch, but there were some signatures in the normal branch as well. So we call this peaked noise as flaring branch noise or low frequency noise. and the frequencies were about 3 to 8 hertz. The idea is that in the flaring branch, the peaked noise may have been originating from the accretion shock. We just heard about the accretion shock, right? So the idea is that there are photon bubbles that are forming inside the accretion shock, and these photon bubbles are coalescing each other and diffusing out. And the degree of coalescing and how they diffuse through the accretion column basically gives rise to this peaked noise behavior in the flaring branch. In the normal branch also, there is this behavior. In the normal branch also, there is this behavior. And the idea is actually that the peaked noise that is there in the flaring branch is slightly different in origin from the flaring branch noise. And the idea is that in the normal branch, it is coming mostly from the shock oscillations that are forming in the transition layer between the disk and the boundary layer, or disk and the neutron star surface. And there are certain interesting things. We noted that the power law index and the RMS of the variability goes lower as you go towards the normal branch state. Also, the central frequency of the peaked noise moved as we go into the as we go in the flaring branch. So in the normal branch, the central frequency was higher, which is related to the transition layer model, and in the flaring branch, the central frequency was lower, which is related to the possibly related to the photon bubble model. Okay. And finally, another interesting thing is we looked at the variability spectrum, and the variability spectrum showed an increase in behavior with energy, possibly implying that the corona is also on the variability that is generating in the disk or the boundary layer and kind of acting as an amplifier. The other cool thing that we noticed is that there was a lag that was present at the soft energies for the low frequency noise. And this this hard lag that is present at the soft energies basically corresponds to that fluctuation propagation model that we heard about. And the idea is that the fluctuations are propagating from the outer disk to the inner disk. And as they are propagating, the hard photons are kind of emitting from the either the inner regions of the disk or the componentized corona and emitting later than the propagating fluctuations that were emitted at the softer regions of the disk. Okay, that's all about continuum. Let's now move on to some transient features also at high luminosity. My job is easier because Alu gave a very, very nice introduction to bursts. I'll be talking a little bit on bursts, that they are my favorite. So I will not spend time in introduction because she already did that. The only thing that I would like to mention is that the study of bursts can also provide a very strong constraint on the neutron star equation of state. And there are a lot of questions that still remains related to, the burst, this kind of constraining equations of state to burst measurements. Firstly, how does the burst interacts with the surroundings, to the accretion? There are a few questions about that. So this precisely something I'm very interested in. And the second thing is, how does the flame space? Does it cover the entire neutron star surface or not? If it doesn't, measurement of radius from the burst spectral measurements would be not enough for constraining the neutron star radius. So to address the question, spectroscopy is the important thing for bursts. But what I was saying that earlier, it was thought that the typical burst spectra is mostly a Planckian spectrum, which is single thermal emission. But slowly, as our measurements are getting improved, we see that there is a very strong deviation from the standard Planckian spectrum. And the idea behind this is twofold. One possibility is that the burst emission is coming from the neutron star surface and it's interacting with the surroundings, either the corona or the disk itself, getting a reflection. Reflection. So that is kind of skewing the burst profile, the single Planckian profile. The second idea is that the burst emission is highly luminous. It has a lot of photons, and these photons are imparting some radiation drag, radiation torque on the accretion disk, thereby hindering the accretion flow. That can also change the emission during the persistent emission during the burst and resulting in a modification of the burst profile. So a lot of new results are to be obtained to really understand what is going on through the burst spectrum, and then only we can use it to measure the radius from the burst spectroscopy. So one of the thing we did is that looked at the burst spectrum using AstroSat, using both SXT and LAX-PC for the first time, because it gave a very broadband coverage, and that will help us, figure out any excess and its nature from the burst spectroscopy. Here you can see an example of such a spectrum using SXT and LAX-PC. We tried a bunch of models representing a single Planckian, the interaction with the disk, the interaction with the corona, the radiation drag. Of course, with the current statistics, it's very difficult to distinguish between these models. But we found out that in most cases, we get the list residuals with a double thermal model, double Planckian model. And that's what we work with. Here you can see the double Planckian with the blue curve. And the blue curve basically represents that the reflection from the disk is happening when the burst is shining on the disk. Okay. The other interesting thing we noted that during the peak of the burst, this interaction excess that we see becomes the highest here. This is the peak of the burst, and this is the contribution of this excess component. So it becomes detectable and higher only during the peak of the burst, when the luminosity is high enough. And we saw that there is a strong correlation between the burst flux and the interaction contribution, the interaction excess. And the strong correlation showed a slightly, break in the dependencies. There was some sort of a transition, and it's an interesting question. What does it represent? But the key takeaway point is the more the photons increase from the burst, they are interacting in a more efficient manner with the surroundings, changing the burst spectrum. We also did similar exercises using LAX-PC and NISA, and we saw that this is again similar kind of plots that Aru showed. But here you can see the plots with NISA and NISA plus LAX-PC. The black ones are just the normal single Planckian, and the red ones where excess has been detected. Now, interesting thing to note here is when we have both NISA and LAX-PC, we can trace out the excess component over a longer duration during the burst. And also, we can figure out what is the level of burst accretion interaction is happening throughout the different burst phase. And that will help us trace the radiation, the cooling of the burst, and calculate the radius during the cooling. There were questions in the previous couple of talks. So I think this will be very helpful towards that answer. Also, we see that the NISA plus LAX-PC and the just NISA or just LAX-PC, if we just compare the corresponding parameters, for example, here we compare the temperature, here we compare basically the FA factor that Aru talked about. It's basically a scaling factor which quantifies the change. So if I look at that, we see that they match closely. However, there is a slight deviation at the certain higher luminosities or certain parameter ranges. So when we have joint broadband feeds, we get a better handle on this excess interaction that happens. And not only that, we get a much more constrained measurement. So the error bars you can see are much lower in this direction than compared to this direction. So basically, a broadband study can give you a much better handle, first of all, on how much this excess is happening, how long, and secondly, what is the nature, like it's a reflection of the radiation drag and so on. So we also tried some more physical reflection models, but at this point of time, it's very difficult for us to get full constraints on the realistic parameters. But eventually, hopefully with better instruments and better wideband coverage, we will be able to address this question. So here I keep my summary. I will not like to read through all of this, but just like to mention that broadband emission and variability studies can give key insights about what is happening when the transition level changes from one branch to the other branches. And secondly, for burst, as I mentioned, we really need to find out what is happening during the burst accretion interaction and how, or burst corona interaction, and how that is changing the burst parameters. Then only we can put a good constraint on how the radius is changing during the burst and use that to constrain the equation of state. And eventually, as new instruments come up, new emissions come up, like Polix or eventually Strobex, I will mention. I'm very happy about that. We'll be able to address these questions. Thank you.
Thank you, Monica, for this excellent talk. So let's start with Melinda, since he didn't get to ask the last two questions.
I'm curious that it is changing from the Planckian you showed, right? But it is only, looks like it's only affecting the lower frequency side. Why is that?
That lower energy. Yeah.
I mean, lower frequency energy.
I think we should not trust just that, because that is often dependent upon which instrument you are using and what is, how sensitive that instrument is. For example, if you use NICE, you will always get a soft excess. If you use LaxBC, you tend to get this one. So that's the idea, but also it can be also physical, depending on how, through interactions, whether the photons are getting shifted towards the softer.
So is there any speculation? I mean, is there any scientific speculation? Did someone?
You mean models?
Models, yeah.
There are some, but at this point of time, the problem is that direct application to the observational data is challenging. There are some cases where this has been applied to super bursts or very long duration bursts, which have much longer duration and much higher fluxes. So basically better sensitivity in terms of signal to noise ratio. So there people have been able to trace some physical conditions. Yeah, but eventually we'll be able to.
So these burst models are very few. The realistic burst model considering neutron star atmosphere during the burst condition are very few, and only a few groups, only one or two groups have them, and they have not mostly converted them to XPEX, so nobody can use them. That's the problem.
But we did some exercises with the Suleimanov models, which are the atmosphere models Phil is mentioning. But I would not like to comment at the moment whether I eliminate some scenarios over the other.
And we did some model independent study during my PhD, which was not like dependent upon any XPEG modeling, but we just used the hardnesses where this is lost. So it was like independent of any XPEG model. So we did find change in the hardness ratio, which was actually a signature of the change in the temperature during these bursts. And there was evidence of the deviation from the Planckian spectrum. And the temperature.
You were talking about compound cooling at the harder expense.
Yeah, harder.
Yeah. Even for our case, we obtained that. For the lack of time, I didn't show it.
Yeah,
but
so we didn't use any XPEG modeling as such. We just used the
like we also got in the light of. So we had one particular case where we got Newstar data, and in the Newstar you can very strongly see the lag.
Exactly.
Deep. Sorry.
Yeah. So we analyzed all Bose experience data that time using all that and we required hard energy.
Okay, another question.
My question is related to the HID, hydrogenicity diagram. Suppose in black hole, we always seen the source outward start from hard step and then move soft, means anti-clockwise. So is this kind of pattern is also followed in neutron star. Means the
showed the HID.
Yes, in HID. So this means we always found it is from hard to soft. So they in neutron star is also following like that. Some unique pattern.
Yeah, typically I showed in the very first slide. The only thing I would like to comment here is I have been talking a lot about the Z sources. So some of the Z sources, like the one I talked about, stays mostly in the soft state. So it doesn't literally go to the hard state at all.
So they start from soft state or hard state?
They are mostly in the high soft state only.
Only start from there.
This particular class of sources.
So it's not fixed pattern.
There are some fixed patterns which I already showed in the very first slide. I can go back if you want.
Start is not really defined.
Yeah.
Generally, binary is started from hard state and then go.
I think we may be confusing it with the black hole stage because there we have Q diagrams sort of.
Yeah, but here you can also see the mass accretion rate shown. Right?
Yeah.
So if you follow the mass accretion rate track arrow, then you will be able to figure out which is the direction.
So the direction is unique.
Typically.
Okay, so let's thank the speaker again. And let's thank all four speakers of this session. And then I will hand over to Mr. Mishra for the next session.
Welcome to the last session of this conference, which is dedicated to gamma ray bursts. And there'll be a couple of talks in this session. The first talk is before lunch, and there'll be 6 talks divided into 2 sessions after lunch. So we're running short of time. I'll request all the speakers to please stick to the time limit so that at least we get some time for the discussions and conclusions, which is planned at the end of the meeting. So the first speaker of this session is Amit Shukla, and he'll talk about the giga electron volt emission from binary neutron star merger. Amit, you have 30 minutes. I'll give you a warning at around 25 minutes, and then we can have some time for question answers.
Hope I'm audible. So first of all, thanks to Indranil Da for inviting me here for this talk and to look this beautiful campus, and apologies for not talking about blazars. So I was asked to talk about blazars, but I swiftly skipped and put this abstract. But there is a reason to do this, and this is very opt to present this particular piece of work because of the currently ongoing LVK 04. So as in morning, Vidushi just glimpsed about
Top one.
Yeah, so glimpsed about one of the unique observation of GW 170817A. This is the first EM counterpart detected of EM counterpart detected of any DNS mergers. However, we were very lucky in this particular case because the Fermi satellite was actually going into the SSA passage, and Fermi lat was switched off. However, the GPM was switched. Just it was barely having a few seconds before GPM got this trigger, and further it was confirmed by the integral telescope that yes, there is a GRB which is co-spatially as well as in the temporal space coinciding with the PNS merger LIGO event. However, due to lat going inside the SSA area or passage, we couldn't see any lat observation. That is there any prompt lat observation? So once lat comes back to the again to the line of sight of the source or the event or came into the field of view, lat again looks back for the flux. However, they couldn't see any GV emission from this particular source or this particular event, and that was a bit very enigmatic because a lot of models thinks that there will be some emission initially at the close to prompt phase or initial after glow phase, and probably even at the later stage. So to keep this in mind, we started a project, one of my master students, along with a collaboration with GSSI Italy. We have a postdoc there, Vishwajit Banerjee. So we have started that, okay, let's look into the Fermi lat data. They have around 137 lat detected GRB, and we decided to check if there is anything present which gives us some indication of indication about the BNS mergers and so on. And another motivation was there, this magic and GRB, which were detected at very high energies. And we wanted to understand whether the emission is synchrotron or SSC or its external Compton. So while doing this debate, we were discussing about it, how to develop our codes and so on. I'm being from the field of blazar, so we think about in the time lags and all. So when we were discussing about GRB, most of the people think that there is a prompt emission and probably a afterglow which decay with the power law of T inverse. However, when I was debating with Vishwajit and Pawan, we had this discussion. I was telling them if there is a binary merger, or we all are discussing if there is a binary merger and a kilonova, probably there will be a delay and there will be emission which is delayed and may be detected with formula in later parts. So keeping this idea in mind, we started developing or working with the Fermi public tool, which is called GTBus. And we started our analysis. However, we realized working with GTBus is very difficult, and it does not allow you to work beyond a certain time stamp. So from T0 to around 6,000 seconds, somehow Fermi people doesn't like to search for a GV emission from GRBs. So, but we were having a different mindset. So we developed our own code which can analyze any GRB data, and it can analyze data up to almost 1 lakh seconds or 100,000 seconds. So once we did that, and we were testing with all these 136 GRBs, what we found something interesting, but let me give a very brief introduction, which is very required for this particular GRB. So GRBs are most energetic sources and generally classified in two classes, short GRBs and long GRBs. And their progenitors, and these short GRBs are mostly suggested that they are due to the binary mergers, and the long GRB probably be due to the progenitor of a massive star collapse. However, this classification is now becoming very hazy. And with this particular GRB, which is GRB 211-211A, we call it Christmas GRB, has changed how we think about GRB progenitors. So this is a long GRB detected by GBM and SwiftPat. It was a long GRB, but shown a characteristics of a binary merger. So alongside with this particular this particular GRB has associated with a kilonova, as well as HMXT satellite has detected a precursor quasi-periodic oscillation in the light curve. So that these two particular indicators suggested that this is actually a binary merger in a long GRB. However, when we heard about this GRB, we again started discussing, oh, there is a kilonova, probably there is a delayed emission. And luckily, our code was ready at that time. And Vishwajit, one fine day, just ran the code. And he called me back. I still remember, he called me back with so much enthusiasm, said, we saw that. And I said, no, you have to cross-check, please. But again, he said, no, we have to talk. We have seen actually a delayed emission. So Fermi is a satellite which detects photon from 20 MeV with 300 GeV and is very opt to look for delayed GeV emissions, because it's actually a survey satellite which scans the entire sky within 3 hours. So once we did that, we actually detected a gamma ray emission, a delayed gamma ray emission from the source about almost around 6 sigma. So the TS was around 36. So this is a TS map. Basically, we have used a log likelihood test. So this is a test map of a field, before 1 day before. So T minus almost 1 day. And when we have integrated, we have not seen any test statistics at the center, which is basically the location of 211-211A. However, when we have extended this particular, so we have redone the analysis for T plus certain T plus 20 kiloseconds, and we have seen this signal with TS36. However, when we have gone beyond, let's say after T plus 1 day to 2 day, we have again not seen any significant test statistics.
So once we saw these test map, the first thing is we have to check whether there is any other source, other blazar in the field of view, which is actually giving us this particular signal. So we have modeled most of the all possible background sources and shown. Basically, it's a part of the paper, the supplement paper, supplement of this nature paper, that we have seen no significant emission from any possible source which were present in the ROI, or region of interest. However, so we have seen it, and the work mostly, so the code was developed by Pawan and Vishwajit with the discussion with me and some other colleagues at GSSI Italy. And so initially we have seen basically this prompt. So basically we have seen this afterglow emission, which is seen around from 4 kiloseconds to 7 kiloseconds. So if you integrate between this, you see a GV emission. And this particular point is consistent with the T inverse, so the regular afterglow emission. However, the emission which was detected in red from 12 kiloseconds to 20 kiloseconds does not fit with our regular afterglow decay power law, which is basically T inverse. And this is the excess was detected, and that could be associated with kilonova, the external Compton emission from the infrared kilonova photons. And for this two particular epochs, we have also made the spectrum. However, our spectrum is not very constraining. We cannot tell right now, but the uncertainties are a bit large, but the average spectrum is around 2.9. So index is around 2.9. And once we have done this, it got published and got a lot of noise also, along with 3 other nature papers. And one of the nature papers by Kuntal also. So this is the first GeV emission detected by any binary mergers. So once we have done that, once we actually got the data, so we just tried to actually model it to see whether it fits with the forward shock and kilonova model. So the first plot which you see here, it's a light curve post trigger time, and the 2 points which you see here, this one and this one, these are the Fermi-Lag detections. And when you can see the afterglow model actually explain the first point. However, it doesn't explain the second point, which is basically access to the our afterglow emission. However, once we included the emission from external Compton emission from the kilonova photons, through the high energetic non-thermal electrons, we could actually explain basically this excess, and which sort of confirms that we have seen for first time the external Compton emission from kilonova photons through a GRB. So this has basically changed our idea to look for multi-messenger events in Fermi-Lag. So this is the cartoon which basically we put up. So we basically say that there are 2 possibilities. This kilonova photons can come either from the behind through the shock region, or it can also come isotropically, and they can produce these GeV photons through external Compton. We actually favored this particular model. However, the discussion on these 2 possibilities are present in the publication. So this particular event actually motivated us to understand what we can further do with the GeV data. So Fermi is operating from almost 17 years, and it has detected almost more than 100 GRBs. Basically, those are detected in lag. However, there are several GRBs which were detected with GBM, and they were not seen in the Fermi-Lag because people have not searched for it, because they thought there may not be any possible GeV emission after 6,000 seconds. So we got motivated with this particular event, and we started expanding our analysis
tools. So basically, we are actually parallelly developing an analysis tool for Fermi data analysis, which basically analyze each pixel of a Fermi data and try to see if there is any excess present in the this particular field. So once we have done that, so basically these are the goals that we wanted to look for the excess GB emission beyond the 10 kiloseconds and so on, and we are developing this particular tool. So this is the first result. So this is our, so this is one of the NSNS merger GW patch. And this is from, I think, O3 run. So we have picked up one of these particular patch. This is around 1000 degree, having 1000 degree of cross section. So this basically this kind of analysis requires huge amount of computational power. So we currently, when we started, we were not having that kind of a computational power. So we can analyze the entire data set in few hours or in a few days. Basically, to analyze this entire 1000 degree patch may require almost a month time on a decent workstation. So what we have done actually, initially we have chosen a small patch of the this particular field, and then we have selected a pixel size of around 0.45 degrees and done the Fermi analysis. This is very similar what Fermi private tool also does. They take around 0.2 degrees, but still there are discussions. We are also trying to improve our analysis, but around 1 GB, the PSF of Fermi is around 0.6 degrees. So going much smaller than 0.6 degrees may not even help. So we have chosen an optimum value of 0.45, and we are analyzing considering a 5 degree of ROI, this particular pixel. And then again, we shift this pixel and reanalyze this data. So now you have to think that we have to do it for entire 1000 degree patch. And this we have done. This is the very first result. I'm not presenting you the result which we have currently. I'm not allowed right now. But this is something which we have done at the very first time. And then to overcome the problem of computational power, we already tried from our department and JSSI to get as many as workstation or clusters we can achieve. And currently we are in the process to achieve 200 cores available to this particular project. And we are in the process. It may take another month to reach. We have already reached 200 core, and the 100 core will be added in next 1 month or so, 1 to 2 months. So, however, parallelly, we have submitted a proposal to Seneca for 100,000 second core hours. So we have initially got 20K core hours with the promise that in case once we actually show the first result, they will give us the much more data set, much more computational time. So this is the first result. And so as you can see, for one of the particular patch, initially when we did the analysis, we have, so this is a tested statistics. I'm not showing the plus map, I'm just showing the significance map. So as you can see, when we have done it from 0 to 500 seconds, we have not seen any testing statistics, which is around consistent with the 0 to 3 sigma. There is a bit of increase from 500 to 10,000, 5,000 to 10,000 seconds. There is an increase in the testing statistics. However, when we have done the analysis of 10,000 to 15,000 seconds, we saw some significant differences. And once we have got this, we got very excited, to be honest. And then again, we have saw the dimming of the source, and there was no flux, there was no significant detection. However, we were not very confident about this particular analysis or particular patch because most of the photons which we have seen are consistent with the background. So if I fit a model to it, it was basically telling us it's a background. This index was consistent with the background. And further, we have some communication with Fermi team, and I think there are is still a publication. They also confirm. So we actually explain this particular brightening as a fluctuation in the Fermi background. And further, it was confirmed by the Fermi group that yes, it is basically a fluctuation in the Fermi background. However, this is the method. And what is the best possible, in case if we actually detect a brightening, the most optimum or most possible way to understand it probably will only see emission in 1 or 2 pixels, and rest of the pixels should not show a significant increase in the TS map or in the TS. And that's why, because we expect the GRB or VNS merger event to be probably a point like emission. So with this, we have already developed this tool, and we are in the process of submitting this publication. We are working with actually O3 and O4 runs currently and trying to analyze the data. The current bottleneck is we are not having enough computational power. And there our different collaborators are coming into the play, and they are actually giving us a lot of computational power. So our understanding is that once we complete our code, we will actually share with our all collaborators, and there will be a system which will prompt them once we see any VNS merger, and they will basically run the pipelines parallelly, and we may end up with some either positive or negative results. So this is one of the possibilities which we are exploring. The other possibility which we are exploring is the multi-messenger, multi-waveband, multi-messenger follow-ups of these GW events. So we have already put a proposal with GMRT in last 2 proposals, and already won almost 15 hours of follow-up time. So there are 3 groups who are actually working on the VNS mergers, and all these 3 groups are coming up with a common trigger criterion, and we have come up with common trigger criterion once either one of these EM counterparts, so one of these satellites like GPM or BAT or any other telescope tells us there is a EM counterpart of GW event, then we will basically trigger the GMRT after 2 to 3 days, and next after 7 days of P0 and so on. So there is a discussion going about the final trigger, but more or less this trigger is there. So we are just waiting for something to happen in O3 run, sorry, in O4 run. Moreover, we have understanding with VRC Maze telescope. Currently, Maze telescope or Maze team is in this part of this collaboration, a small collaboration, and they agreed to actually look each and every GRB, more or less each and every GRB and VNS merger trigger once the telescope is ready to turn. So let's see if we see trigger today, now, probably in the evening, they will turn the telescope towards the field and then look for the PV emission. This is almost guaranteed. There is a discussion going on. It's not formally, it's not formal, but within the collaboration, we are doing this. So this is our team. So we have faculty members from DASE. So me, Bhargav, Abhirup, we all are part of this team. And from the Grand Sasso and Italy side, we have a big team of multi-messenger astronomy led by Maika Baransi and some people from INFN in our team. We are having people from DHEP and DTP, TIFR to support our theoretical aspects. We are having people from Astrophysical Science Division from BRC, mainly the Maze team. We are having some experts, transients experts from the IA Bangalore, and we also have members from INRAVE and Virgo collaboration. And we are working on some private communication. Still, we do not have any private communication. So basically, we rely on our public GCNs. However, we are working on a model where in case INRAVE or Virgo collaborations, they see some events, probably will implement them and try to figure either GMRT or any other optical, any other Indian facilities. So this I will stop, and actually I like to invite any one of you who are interested in transient astronomy or multi-messenger astronomy. People can join our effort, and we are planning for a couple of meetings in next year. So if you are interested, please let me know, and probably we will extend our collaboration and effort with you. Thank you.
Thank you, Amit. Questions for Amit?
So, Amit, this is about the GV, sort of the test statistic became higher from 10 to 15,000 seconds. So you were searching where there was a GRB at that location of the sky?
No. So for this event, there is no GRB. So this is a GW patch. So a virtual LIGO collaboration gives us a GW error patch.
Okay.
They tells us there is a probable candidate within this error patch. So something like this. So they are saying the gravitational wave might have come from this particular region of the sky.
Okay. So
And
then you were searching in that region for any additional excess
Yes, so
GV
this is around 1,000 degrees. So we are developing our tool such that we try to search every 0.5 degree pixel and then correlate with the 4FGL catalog. And once we see if there is no correlation or there is no catalog source present, then we try to understand more.
And when you say you are making your tool, is this any different from the standard Fermi analysis?
Yes. So Fermi has few tools. Some of them are private, some of them are public. So one of the private tool is called Player Alert something. So basically what they do is they download the entire Fermi light data, Fermi lab data for 1 day, and they run through this pipeline, I think, at Stanford. And this pipeline tells you that is there any brightening in the Fermi map. So this is what you see every day. They give you some alerts as either ETL or GCM. So a very similar tool. This kind of tool is not publicly available. So you have to actually develop it using likelihood analysis. So we are taking the likelihood analysis packages of Fermilab and trying to implement to develop this.
So, Amit, if I understood correctly, it is because those tools are not available publicly, so you are trying to have your own tools. And
then, yeah, nice talk. So GRB 1509 and GW 1509, you showed the results. So how much hours it took computationally?
So this is what I have shown you. That was done on a small lab with a very bad RAM, and I think it took a few days to do that. But our current understanding is to do a 1 pixel requires on a cluster which we have with around 256 GB RAM and so on, may take around 1 minute. So that scales up to 1,000 degree pixels of the scale it. So we are thinking around 7 to 10 days we'll be able to complete 1 patch.
So with laptop we can do within 7, like in a week.
In a week time, yes. So I think this took 2 days, 1 day, probably something. So this was actually done by my student Sushmita. She got a 3 months fellowship from institute to visit JSSI Italy, and she worked with Marika there, Marika and BCG, and they are basically started this particular.
Plus for the 70%, although you mentioned that for me lab didn't observe for 2,000 a second, but after that there were lag detection did you try to test the lag detection?
We actually doing it. It's the paper is in pipeline. Probably I can tell you privately, but not publicly.
Okay, because 1509 is black hole mergers where we don't expect Nova. Most
Yes,
likely.
yes, that's true.
But for 17
right.
it is
So right now our analysis is driven by the smallest patches, because that's what we can do it within a given time. So if So all these collaborators which I show you, once they contribute to this computational power, probably will extend to most of the O3 and O4. So this is the plan, but that requires enormous computational power, something like what they have at Stanford. So we cannot get that right now, but we are trying as much as possible.
Okay, thanks. Next.
Okay, so, yeah, so you have showed the GEP data point or the long but the kilonova GRB. But then for the 17817, I think you did the analysis, but I think you didn't find any GEP flux. Is that correct?
Interesting question. The answer is no.
So what?
But there is a caveat. This no comes with a lot of experience because there are patches, there are times when you see detection of very slight detection from the field above PS.
But it also depends on the luminosity of the burst. Is that true? Like,
So
the electron
see,
distribution.
so what we do not understand much about, okay, I particularly don't understand about the kilonova physics and this external component emission. So our main idea is to look for the relativity. And once we see something, probably we can understand more and more. So about 17, we actually analyzed almost entire data few times with different strategies. So the problem with Fermi-Lab is it would take a longer period from background dominance. Now you can shorten your this bin. So you can go from 1 month to 1 day. The problem here is your background starts fluctuating.
When the fluctuations become
so you will see there is a excess which probably may not be true. So we have seen access, which is basically before this 17017. And once we saw that, we thought it's probably a fluctuation, and we are working on it. It's not a settled issue. So we see time to time some excess, but I personally think it's not associated with GW1708. Another thing what we are trying, which is not done, I forgot to tell. So you have seen this patch. So even we may not get a detection, but for each pixel we get the upper limit for the flux, and that can associate it to the GW event or binary merger event. So there is a method, there is a Bayesian method, which actually allow us to integrate all these pixels. So the probability of each pixel and give us a one upper. So probably, and we are working on one of my students is working on
the kilonova signature is very important.
Yes, that is very important. But even at the end, probably we will tell from this patch, this is the upper limit to detect or for
Okay, nice talk. I have a question regarding the future strategy of observation. In case of a gravitation wave, you get GeV emission. So, in a sense of other electromagnetic counterpart, what it can add to the physics of GRBs, and in case you get GeV emission, what will be the future strategy, observational strategy, for further follow-up of the event?
So there are several strategies are discussed currently for our GMRT proposal, like GMRT, and we are also trying for some optical telescopes. I can talk about that. So for the GMRT proposals, what we have proposed, so initially we want to observe it on either T0 plus 2 to 3 days. So, and the reason behind it, the radio emission depends on the angle at what we are seeing this year. So if it is a very on-axis event, probably we see the radio emission very quickly because of the time contraction. However, if it is a delayed, it's an off-axis event like 170817, then probably we'll detect the the radio emission much farther, around more than 100 days, right? So we are scanning these possible 3 time span. One is around 2 to 3 days from T0, 7 to 10 days from T0, And I think next, the last one is around 20 to 25 days. This is the current understanding between the PPIs who have got the time on GMRT. So this is one of the criteria. For the optical observations, I think as soon as you see the trigger, you can see that's what Engrave is doing. So they get this internal information from Virgo, and basically, I think ZTF and Engrave are doing the similar thing.
And in case if you don't have other wave bands like optical, if you have radio and GV, which is most probable.
Yes.
So what this can add to the physics, because you need multi-wavelength model.
Yes. So radio observations will definitely add about the jet environment. So if you, I think there's a paper by Giancarlo Ghirlanda in Science about 17. So he has constrained the entire jet environment using that relay observations. So I think the radio observations will be very important. We are in the process for relay observations as well, but probably take some time. We are looking for people.
Okay, one last question is coming.
So I'm not aware of these fields, but I just want to know what is the uncertainty of this positional uncertainty of this analysis.
So we are having this 1,000-degree patch.
But for optical and GMRT, how?
So if it is it's a GRB, then it's a very precise, I think, few degrees. So what we are looking, few arc minutes. So that electromagnetic counterpart must be very well localized within, I think, few arc minutes. So this is what the trigger criteria are. Yeah.
No, but GW will give some position information.
Yeah, so that is 1,000-degree.
Correct,
But if there is no associated GRB,
correct.
we will not
that is 1,000-degree. Then you do some analysis.
Yes.
And try to detect the
GEV emission. Yeah, so that is around 0.5 degrees.
0.5 degree. So
our pixel is 0.5 degree.
And optical position field of view roughly 10 arc meter, 12 arc meter. Can we position it?
I think if we have a GRB, then it should be very good. It should be localized within this range of few arc meters, as I remember. But probably Kuntal may tell us more. She is the expert.
Any more questions? Otherwise, we break for lunch, and let's thank Amit again for this very interesting talk. So Rahul has one last question.
Yeah, thanks. Very nice talk. I have a question like in this case particularly 211211A. Basically we have earlier signature from the kilonode from the optical observation.
Yes.
So we go for the search basically for the GV emission.
Yes.
So how we can search for like basically how to differentiate between the GV emission from the afterglow and from the kilonode.
So that's what I said. So if this emission is a regular afterglow, which falls as the inverse, right? Basically, the power law index should be around -1, right? This is a regular general afterglow decay index. So if you see excess, which is basically here, if you see this point, which is observed after 10,000 kiloseconds, so this is not falling on the afterglow line or this index. If it is a part of afterglow, then it should come here. Sorry, it's a touch screen, sorry. So then it should come somewhere here, but it has excess. So that indicates there is another component beyond forward shock. So there is something happening beyond forward shock, and that probably due to the kilonova.
I have another connected question. Like LAT has detected many short GRB.
Not many, but yes.
Yeah, there are many. So do we expect like such kind of kilonova emission on the LAT or the short GRB early?
So we have not seen any. So if you look for the paper, we have analyzed all the LATs detected GRBs, and we have not seen any delayed emission till now.
So anything special for this particular case?
I think the special case is this is the distance. It's a 350 megaparsecs, and this is a very low luminosity GRB. The luminosity is only 10 to 45.
I think it was one of the right. Luminosity is very low.
10 to the power 45 and 350 megaparsecs. So it was a closed GRB and a dim GRB, but it was so close so that. And actually, OPPO run was operational. Probably they have seen the.
I think we can continue this discussion over lunch. And since we are delayed by half an hour for lunch, I request you all to be please back by 2:15 at the latest so that we can start the next session. So thanks all of you.
I had a question, but I
Then you will delete that.
regarding this GR, this was one of the lowest.
So we are working on both. The problem with both is it's a pilot. So you have its pilot, you begin its pilot. The major portion of the GRPs you can't use, and for you people are not giving them. So to be honest, so they are actually right of to hijack the data and they are not giving us both GRP data. Both GRP and all, there are three GRPs. So last 1 year is very effective for so there are three GRPs and they all three are prices and they all piled up. But medium 29 lakh things are not really that you have. No, that they do not do that. They lost one GRP and they were telling
Shabnam, you are talking 20 minutes. Let you know after 20 minutes. Mukesh, yours is 20 minutes and let you know 15 minutes. Will this 15 to 10 minutes? Rahul, will copy your 30th? Input? You are
अभी just सभी तो
Okay, so good afternoon, everyone, and welcome back. And thanks for being here right on time. It's exactly 2:15 when we start this session. So this session has 3 talks. The first talk will be delivered by Dr. Shabnam from ICER Thiruvananthapuram. Shabnam, you have 30 minutes for the talk. You can please start.
I'm audible. So, good afternoon, everyone. And first of all, I would like to thank the organizers for giving me this chance to give a talk here. And as you can see the title on the slide, so I will be talking about more on the modeling part of the GRBs and particularly on one of the aspects that we could find in a continuation of 2 works that have spanned over like almost 2.5 years. And I'll tell you how crucial certain aspects of observations are. It becomes necessary for modeling and coming to some assistance. So it will be on the title as onset of particle acceleration that you will see in prompt emission in gamma ray bursts. I'll start with a brief introduction. I know introduction has been given by Vidushi as well. So what you see here on the screen is the sky map of the gamma ray sky as it has been observed or as is observed by Fermi. And the dark bright region that you see here is basically the gamma ray emission that's coming from the Milky Way galaxy. And then a gamma ray burst happens. So there's a light one, as you can see, it's so bright that it almost outshines one of the major sources in the sky. So what we immediately see in a detector is a sudden rise in counts, and you call that as a prompt emission. That is what we call, and which lasts from a few seconds to few hundreds of seconds. And apart from that, so what we understand, so these are the brightest explosions that we know in the universe. They come from cosmological distances, and they are believed to be a narrow beam of intense flashes of light. So apart from the prompt, gamma ray burst is not restricted to only the gamma ray field of observations, but there is something called as a glow, which comes after this prompt, as the name suggests, after glow, which extends over a longer duration of time in contrast to the prompt, from hundreds of seconds to even days and months, and in certain cases, several years as well. And that is basically observed in all the wavelengths starting from the gamma rays until radios, which allows for the multi-wavelength observations of the GRBs. So so basically there are two major classes of GRBs, which we consider the progenitors, which are binary neutron star mergers, or it is the core collapse of the death of very massive stars. I'll give you a basic framework within which we understand how GRBs happen, what gives rise to prompt, and what gives rise to output. There's a basic framework. It's not that we understand everything of it. Okay. So the basic framework is something that we refer to as a classical fireball model. So irrespective of whether you start from the merger of two neutron stars, or if there is the core collapse of a massive star, you finally end up in a scenario where you have a very compact object at the center and you start accreting the matter around it, which ends up producing a lot of energy, let's assume in some form of a fireball, as the name suggests, where it is dominant in radiations and you have some amount of baryonic as well as electronic matter present in it. And because of the high radiation pressure, because the luminosities are much, much higher than the Eddington luminosities, it pushes the material outwards, which basically accelerates or particles to velocities close to the speed of light. And we believe these are put out in the form of a jet. And now the emission that we call as the prompt is something that we consider to originate in the jet. Okay, so you consider that this shells of matter that is being accelerated from the central engine. You can consider they have different masses and different inputs of energy, so they can attain different terminal velocities. And you can imagine that the shells are going out with asymptotic of different Lorentz factors. And you can imagine a scenario where a fast-moving shell can go and crash into a slow-moving shell, which results in the dissipation of the differential kinetic energies of the shells, creating shocks, and where basically you can expect your electronic or hydraulic we have options for modeling, where your particles gets accelerated to high velocities and later on cooled by various processes that we know. So this is basically what we call as internal shocks, which gives rise to the non-thermal emission largely that we consider. But apart from that, as I said initially, all of it is present in the form of a huge fireball, which is optically very thick. So as it expands, what happens is the density drops. And at one point, the photons get decoupled from the plasma. And that is basically what we refer to as the photosphere. So from a photosphere, you would basically expect to see some kind of a thermalized emission. As I said, this is a very simplistic picture. And as I said, you can have shells which can move and crash into the slow-moving shells and then result in shocks, wherein you can expect non-thermal emissions to come. Okay, so this basically composes of what we call as the prompt emission. This is the basic framework in which we understand what prompt emission happens. And the jet would now further go on and crash into the interstellar medium. And that is what we call as external shock. The jet goes and crashes into a medium that is outside. And that shocks, the emission that is produced in those is what gives rise to the afterglow that we see, where it extends from all the wavelengths. So this is a basic framework. And some of the key questions in that picture, if you have seen any point, if you take, it's an open question in GRB. But one of the major things, because the radiation is the only thing that largely you can collect from it. So first the question you can ask is how that is produced, what is the mechanism that gives rise to these radiation processes, what are the dynamics of the outflow. When you say it is relativistic, you want to ask the question how relativistic is it, does it change, the luminosity changes, the baryonic loading changes. There's a lot of dynamics that can happen in the jet.
And where in the outflow is this radiation produced? Is it from the photosphere, or are we talking about cases where shocks can happen below the photosphere in optically thick regions or optically thin regions? So there's a lot of questions that can ask there, and also what is the composition of the jet? Okay, whether it is baryonic is the case that I told as a fireball model, but you can have alternate options where majority of your
Fireball is leptonic.
no, it's electronic. But in the sense it's a radiation dominated model, whereas you can have pointing flux just where most of your energy is in magnetic fields instead. And also to ask the question, what is the central engine that basically powers this whole thing? So all these are outstanding or open questions for us to study. And in this aspect, because we see gamma ray spectrum, it is generally non-thermal in nature, as you can see. It is very broad. It doesn't look anywhere close to anything that is thermal, and it's typically modeled using a mathematical function that is called named after David Band as band function, which is nothing but two power laws smoothly joined here. So you characterize by two power law indices alpha and beta at lower and higher indices respectively, and you have a break. So these are the three main parameters that you have apart from the normalization. And what is the current scenario in the modeling? Because you have the spectrum, of course, you try out various models, starting from band to black bodies and various others you want to do. But one of the technical problems that we have, that is establishing a model, you do statistical analysis of it. But the point where we stand is sometimes we are in a case where we fit models to the data and we cannot distinguish the models between them. We cannot say one model is better over the other statistically. So that is basically, we say they are degenerate models. Both models become equally good. So this is one of the cases where I show you the new plots of a spectrum of a GRB, where you can see that I can fit a black body plus a synchrotron, which is shown in the green that you can see here, whereas I have a Comptonization model. So these are two different radiation models, and I can fit both of them equally good with the data. Okay, so now the question comes, they give you completely two different spectral shades, and how do I choose one over the other? And similarly,
different objects, right?
No, it's the same GRB and the same.
But it's not matching.
It's not matching. So that's one of the things I always have an issue, even with the AGN spectrums, when people show, you are not allowed to show data points in any of your plot until you don't fit it. Either you show the residuals before you want to see. So because we use forward folding technique. So in that case, you do not know what is your data point exactly in the energy space. You only know it in the count space. So you start with a model and you convolve through the instrument, and then you see it in the count space. The only place you can compare data is the count space. So typically, we are not allowed to show data points in a Neo-Smith plot with your model. So if you want to show it, you show it in the count space, and that is where you have to compare. So that's the reason why I have not shown the data points over here.
Okay.
But they are equally good fits from the statistical point of view. So that's what I
You have the data only where it's crossing.
And
or within the error limits. Or within the error limits.
So and the other, and also from another point of view, also I should tell why I said these two models are equally good is also from a statistical point of view, you can compare one model is better or the other only if they are nested models. So nested models is like I can compare band with band plus black body. So if one model is a subset of the other model, they are nested models. So you can always tell, comparing the statistics, whether I need a black body or not. That's the question you can ask. But if I have two different models, for example, these are two different models, then the statistical comparison of saying which gives me the lowest chi-square is not a right way to do. Statistically, it is not correct. Even though people do it, it is not correct. So only thing is that with the residuals, they are good. There is no anything that is deviating. If it is good enough, they are random in nature. It is safe to say you are consistent with the data and nobody can rule that out. Until you have to science-wise show it that this is better. So that is what we have. So how to break the degeneracy is the question. So when you have degeneracy in those cases, how do we do it? So on the right-hand side I've shown here is also a case similar to that, where people also use spectral width measurement. That is, they measure the full width half maximum of the band fit that is done to the GRTs to tell whether they come from a synchrotron or a black body, because black bodies are very narrow in comparison Synchrotrons are very broad. But as you can see, I can fit this data with a synchrotron, which is in green. So by the band fit, whoever had done the band fit, they claimed that this DRV was inconsistent with synchrotron emission. But I was able to fit a synchrotron model directly with the data. Good enough. And it was not a bad fit. So this is the, I would say, a drawback or a caveat that one should be very much aware of when you do forward folding technique in X-ray analysis. That you cannot rule out a model just with one because you do not know how it will play out in the count space. So in these cases, breaking the degeneracy is one of the major problems. So simply with spectral analysis, if I say I'm stuck over here, how do I go forward becomes a question. So it is in this case, polarimetric observations become a key point because now it gives some extra information which you can combine with spectrum and then have to come up with a physical model that can explain both of them together. So, so I'll be presenting, as I said, the summary of two works that we have done. So first, we will be presenting the spectropolarimetric observation that we did for the DRV 1608-21A, which was a very bright burst, extremely bright burst, and it is among the top 5 bursts that have been observed by this. And during the prompt phase, it started with a first emission episode, which was not that bright, but it extended over a very long duration of nearly 100 seconds. And what we basically saw was that this was observed basically in the GBM, and this had a spectrum which was something like a cutoff power law. That was what we could best fit it. And it had a fluence, again, it's very bright, so it's around 10 to the minus 5 per centimeter square. But the interesting part was after the 100 seconds, when we actually had a very bright episode, which was nearly 100 times more brighter than the first emission episode that we had. So it was nearly after a delay of 112-15 seconds that we saw this. And it had a duration of nearly 90 seconds or so. And interestingly, the spectrum for this burst did not go anything with that of a band. It was not a conventional shape. As you can see, if you have seen the previous cases, the band would have looked something like this, with just 2 power laws and the peak, but that was not how it looked. So it basically needed a shape which was something like this, very broad. So we fitted it phenomenologically, basically using a band and a high energy cutoff, which was the major requirement that we had. And we characterize these spectral properties as one can see here below. In the upper panel, what I've shown is the power law indices, and which the black shows the low energy power law indices over here, and the blue one shows the beta, which is over here. So it shows this flatness part. Okay, corresponds to that. And in the peak that is lower, in the panel lower, we see this is the, so we need a black body as well. So what this spectrum characterizes, to summarize, it had 3 breaks. So we had a peak for a black body, which came, and there was a band peak, and there was high energy cutoff. So there were 3 breaks in the spectra, and these 3 breaks is what I've shown here. And you can see something interesting if you just look at this plot, is that the low energy part of the spectrum, which was characterized by, like, say, alpha, the black body also came in the low energy part around 30 keV, and the band peak, which is around 1 MeV, they are very stable, extremely stable without much any of deviations. But if you look at the high energy part of the spectrum, that is the beta and the cutoff, you can see there is an evolution in the beta as well as an inverse behavior of how they move with time. So this was something that readily one could see from the phenomenological point of view. So now the interesting part came when we did the polarization measurement for this. So first we attempted the polarization measurement on the entire duration of this. So the polarization measurement was made enabled by the CZT instrument on AstroSat, which is capable of doing polarization measurements. And this was done in the energy range 100 to 300 keV that we did during this burst duration. And what we saw was that, so this was time integrated. So we found that if you look at the contour plots of what is showing on the y-axis is the polarization fraction, and on the x-axis is the sky polarization angle. And you see that we had a very low polarization of 20%. We say low in the sense is because the confidence level is much lower by 68%, and a little more higher if you bring it almost touches zero. So it is not that significant the result. So it's mostly low, that is the thing. But you can say an interesting part of it is that it had two centers of polarization angles. So that was the interesting part. You could see is that you can say that it might be due to that it's not able to constrain. But in another way, if you think it is because you're fitting this modulation that you're observed with a cosine, and it could be possible that it could be a summation of two cosines that we are seeing. So the posterior can suggest think that there might be two cosines that might be present in your data. And this, because it was quite bright and we had enough of Compton events, we were able to do time resolved polarimetry over this burst. And we basically did that. And so we divided the main episode of this burst into three parts. That is basically starting the rise phase. And in the rise phase, we saw that it has a high polarization fraction, and there was a polarization angle measured with it. And during the peak, so this is during the peak phase, where we can see there's a slight drop in the polarization fraction, but it's still within the error bars. So we cannot link that. But there was a sharp change in the polarization angle. So the angle almost switched by 90 degrees, close to 90 degrees. And when we did the decay phase of the burst, we again saw a flipping back to its previous polarization. So this was the main key result that we had for this burst, that the polarization fractions, if you look, it's quite high. It's higher than 45% throughout the burst. And whereas the polarization angle basically showed a temporal change, which flipped by 90 degrees twice during the single pulse of the burst. And so moving on, yeah, so if, in yesterday's talk, basically, Dipankar had summarized the polarimetry theoretical models. So because this is an extremely bright burst, it is safe for us to consider that we have viewed this jet almost within the jet cone. And if that is the case, then what we have shown here is the various models that predicts the theoretical. You can predict the polarization fractions which you would see. On the y-axis, what we are seeing is the ratio of the viewing angle with respect to the jet cone. So if the ratio is less than 1, it basically means that you are viewing it within the jet cone. And if it is greater than 1, you are viewing it outside of axis. And basically, because we are within the jet cone, we can assume that safely. So we look at these models, and the pink one that shows here is basically for synchrotron emission that comes from an ordered magnetic fields. And we find that it can have polarization fractions which are quite high. And whereas in the case of if it is synchrotron emission coming from a randomized magnetic fields, or it is coming due to Compton drag, that is inverse Compton scattering, in both cases you would expect to see very low polarizations. So the high polarization fraction observed throughout the burst duration suggests that this has to come from a synchrotron ordered magnetic fields. So this has a key, it drives you the physics, because identifying the radiation model allows you to do the remaining microphysical modeling that you can do with the dynamics. So we were able to rule this out, and we were able to.
Here you're assuming that it is an index Compton, that you are not actually seeing the seed photons.
Yeah. So the seed photons in that case would be mostly the thermal photons that here.
That, whatever it is,
yeah,
we don't know. Okay. Thermal photons are anyway doesn't have much polarization.
No. Yeah. So so particularly the important thing, if to notice that this in the spectrum, if you saw the Fermi GBM plus lag, so it's like a huge several orders of magnitude of spectrum that we are seeing. And the band peak was around 1 MeV. The polarization measurement that we made was only 100 to 300 keV. So that was an interesting part because 100 to 300 kV, there is no spectral change. It's very stable. But during that time, but you can overall see that the photons, that is basically the nature of the polarimetry of the photons has completely changed with time. So this was something which drive our next piece of work. But before we start off with, I'll also give you, so in terms of the observation of this GRB, there was an afterglow that was observed, but we actually saw, so in the duration of the burst itself, towards the end of it, roughly starting from 135 seconds or so, we actually saw an extra component that was required apart from this band with the high cutoff. So this extra component in LAT, which was basically required, which we consider as the onset of afterglow, and nearly half an hour later, an optical afterglow was observed, but unfortunately no emission lines were seen, and therefore we have no redshift measurements for it. And there was a campaign of on radio observations done, but there was no significant detections that were seen. So it is key to just remember that we have an afterglow. We know exactly from at what time the afterglow has roughly started. Okay, this will allow us to do the modeling that we will be doing in the next one. So this was a follow-up paper that we did because now we understood that the spectrum corresponds to synchrotron, which we now did completely from a phenomenological point of view. From the polarimetry allowed us to constrain that the spectrum has to be synchrotron produced in an ordered magnitude. So now once we know that, what is the way forward is that we need to test the synchrotron spectra or the radiation directly with the data instead of using a phenomenological model. So this was what we did. And what interestingly we found was that, so we basically did the spectral analysis in the 3 bins where we had the polarimetric change. So see, the key result that we had was this, there was a change in the polarization angle. But how and why this change in the polarization angle happened is something that's an open question, because the current physics of how much we know is not easy to explain that change of the flip of the polarization angle or the swing in the polarization angle that we have observed. So, but interestingly, what we came out when we did the direct modeling with the synchrotron radiation was this, is that, so because it was very dry GRB, we stuck to fast cooling. So we considered that the electrons cool well within the dynamical time. That is, by the time the electron crossed the shock region, they have emitted their radiation. So that's a fast cool spectra. So we considered a fast cool electron distribution. So basically in the E square NE, you will see a flat, that is a cool part of the spectrum of the, or not spectrum, the electron distributions. And what we found was that in the initial interval, the first and in the third interval, the electron spectrum was consistent with that of a completely cooled electron spectrum, where after the this break, it was almost a cutoff. Okay, whereas in the second or the peak region, where we had the brightest emission, or where we saw the flip in the polarization angle, we basically see that there is a power law that emerges, and then there is a high energy cutoff. Okay, so the most important thing, the result that we find as we transit from the first episode or the first interval that we see, you do not require an extra power law there. Okay, you have a completely cooled electron distribution, and then basically during the second part, you basically have an onset of particle acceleration, because we know that the electrons have to be accelerated to some form of power law, and that is how they produce the radiations. So generally always you see a partly it has cooled and partly it is still in the power law. So but here you, for the first time, you are able to see an onset of it, because you never see an onset. You know that particles have accelerated and you're seeing the radiation of it. You do not get to see that onset part of it. And here we are actually able to see that initially whatever has accelerated had cooled, and suddenly there has been some re-acceleration or whatever acceleration that has happened at the site, and which produces a power law in this region. So this basically marks the onset of particle acceleration that we see. And because we did a direct modeling on this, we were able to constrain the power law index. And we found that the power law index was around 2.3, which is consistent with the Fermi acceleration processes, which is being, or that has been also seen in particle in simulation studies. And we also went ahead and did the estimate on some of the physical parameters, that is the total number of radiating electrons, as well as the magnetization that you can see in the downstream as the outflow force, because where the particles are largely accelerated and produce this. And we were able to find this as a key result, where you see in the panel over here, I show you the number of electrons, radiating electrons. Here is the magnetic field intensity in the region, and here is the magnetization. So magnetization is the ratio of the Poynting flux to that of the enthalpy flux that you have, the macroenthalpy flux. And so you see that basically you see an increase in the number of radiating electrons. So during this time, whereas in comparison to that, the magnetic field intensity is not changing much. However, the magnetization drops, because magnetization has a dependence on the number of inverse dependence on the number of radiating electrons, and therefore we can see that as it increases, the magnetization basically drops in this region. And based on several studies that has been done analytically also to understand the particle simulation study by Lemoyne and Pelletier and those papers, we basically use, because in a ordered magnetic field, you can consider the central engine actually has long magnetic fields which are frozen to the plasma. So in such a case, at very high distances far away from the central engine, the dominant magnetic field component would be the transverse component rather than the poloidal component. So you consider that the shocks that we see is the transverse shocks, and based on that, we basically used the relations that were brought out in this analysis study. And what was interesting was that this observation of seeing and no acceleration and then an acceleration allowed us to constrain the Lorentz factor of this DRT. Okay, so this basically comes out from this expression where the relative Lorentz factor across the shock, if you combine these two, you get that it has a limit. So the acceleration would happen only if the magnetization is below a certain critical value. Okay, so and we find that the relative Lorentz factor has to be less than a certain value of the Lorentz factor. That basically allows for the acceleration to happen. Otherwise, the relative Lorentz factor is higher than that. So with this, we know that in these two intervals, here the colored lines basically follows this expression, whereas the black line is where the relative Lorentz factor is equal to gamma. So their intersection points gives you, for example, in the second interval where there is acceleration, it gives you an upper limit for the Lorentz factor, whereas in the other two beams, you get a lower limit for it. So this basically tells you that the bulk Lorentz factor can range somewhere between 420 to 770, and this corresponds to an emission radius that we're talking around 10 to the 18 centimeters. So with this, we have also done the estimates on the cooling Lorentz factors, the minimum Lorentz factor, the power law of that radiation, and the magnetic field intensities. As you can see that the gamma C and gamma M are not very far off. They are much closer by. The magnetic field intensities are roughly constant. It's not changing much. Whereas you can see the number of electrons has a massive change of an order of magnitude, where similarly the magnetization also drops significantly during this period. And so what is the physical scenario that we are suggesting? The physical scenario is this, because we have already seen the afterglow. So we know that afterglow happens later. So there have the emission, this bright episode that we saw, it is around at a 10 to 18 centimeters, and it is going at a Lorentz factor of close to 500 and so, and it has delay of nearly 100 seconds. So what we're suggesting is that what we are actually seeing as a very bright episode is basically an external shock that has happened because of the interaction of the jet with a ring of nebula that might exist in case of certain Wolf-Rayet stars. So 10% of the Wolf-Rayet stars are found to have nebula rings because of their extreme mass loss rings. That is safe. So what we can say is that this external very bright region that we had in between is basically happening due to the interaction of the jet that happens with this nebulae. And that is, and in the shock, in the forward shock, the electrons get accelerated, and that's the pulse that we basically see. And what we think is that as it goes through that medium with about whose density or the profile is something which we do not know, there might have been an increase in the number of electrons or a density that it has encountered, which might have crossed this increase in number of electrons and dropping the magnetization at a point, which made randomized the magnetic field lines at that region, and this might have caused the flip in the angle that we are trying to see. So this is just a suggestion, but it's not a foolproof thing. So it's an we envisage that this could have been a scenario that could have given rise to this. So just summary. So the main thing is that the spectropolarimetry is the observational key that we had here, because it allowed us to confirm that it is a synchrotron model. And it is with the synchrotron model, we know that we went ahead and did the direct model testing, which allowed us to constrain these parameters. And as I said, what is the key output of this analysis is also this, that we have now found a new way to independently estimate the Lorentz factor, the bulk Lorentz factor of this jet. And since we know that if this scenario that we envisage this can be true, then that means only a small fraction of the GRBs would exhibit this kind of phenomena, where we will have a latent extreme flaring that you would see when the jet would interact with this kind of nebulary.
Questions?
Both results are very interesting, especially the flipping of the angle. Did you check the polarization angle in first 100 seconds?
No, the first 100 seconds there was no observation in AstroSat. The AstroSat didn't see that. Yeah, so the emission wise, the fluence, as you said, and when you integrate it over 100 seconds, you get 10 to the minus 5. That seems bright, but the flux level is actually quite low. So we do not see it because of the high background existence.
If your explanation of that nebula is correct, in that case the nebula should be abundant in other sources as well. So we should be expecting this flipping in other sources.
So no, so that is what I said. So Wolfram stars are considered as a potential candidates for the coordinators of long reactions. But among the Wolfram stars, first of all, it's not a well-studied sample of Wolfram stars, but among them only 10% of Wolfram stars are found to have rings. So it's not that all the Wolfram stars have rings. So in that, what we consider is that the first precursor that we see is the jet emission, the prompt generally that we interpreted. But the flaring that we are actually seeing is actually the interaction of jet with the nebula ring. And then you have that.
So I was curious about your discussion of the acceleration mechanism in the context of shock acceleration. Isn't it kind of understood now that the shock acceleration the time scales will be much longer than these processes, in the sense that it would be like half a day or more than a day to accelerate particles to that kind of high energies, if the shock acceleration was the only process? Yeah, but how long, I mean, even in the rest frame, how long are these?
Then you take the time dilation factor.
Yeah, so but this happens, as I said, this an observed trend, it is around the cooling time scale at least is around 10 seconds. That is the limit that we take.
Yeah.
But yeah, of course, you can
So it will be
calculate.
1000 seconds, right?
Yeah, but it still will not be.
But 1000 seconds is not good enough for shock acceleration.
No.
That's what I have a feeling about. That's what it seems now. Unless your initial particles already have some,
Yeah, so of course that's an open question even in Fermi acceleration, where the injection problem is, where you already need the particles with certain velocities above their thermal to start the back and forth process. Yeah, so I mean, we do not claim on what could be the process of the particle acceleration as such, but we kind of assess like from the slopes, we kind of consistent with what is being predicted in Spitz-Koste's results also.
Thank you.
So the interesting was that the Spitz-Koste's particle simulations say that you can have a power law with a cutoff. And we basically see exactly that the kind of an electron distribution the power law with a cutoff, and the cutoff has certain values. So that's one of the future studies that we are doing, where we are trying to find the evolution of this cutoff, because they have certain predictions of how that.
Those simulations predict some time scale?
On the realistic scenario of timescales, that I'm not very sure.
So actually, Yeah, I am actually interested about this magnetic field intensity does not change very much. I mean to say, if you look at the standard shock scenario, when your GRV would have hit that ring, it would have generated this. If this is the case, then one possibility would be that the magnetic fields are aligned along with the jet even in the ring. So that means they will not be compressed. And so you would see this, which is interesting because then your magnetic fields are essentially along the shock normal, which makes the shock acceleration even more efficient. So that is one comment I have. And another point that I wanted to make is in your shape of the spectrum, when you don't see higher gamma rays, have you not wondered about the EBL, what people have been talking about, like a higher gamma ray getting absorbed because of the extracted background?
Yeah, so see, there are two reasons. One is, for example, the electrons.
This is also G, you know?
Yeah, we have seen in 100 MeVs to GeV. Yeah. So 4 GeV is something the highest.
Oh, okay. Then example the 50 G.
Yeah. So.
So it was only 4 G.
Yeah, it's a maximum that we've seen.
I had many questions, but I forgot most of them. So whatever I remember, one thing you said about the compositions like baryonic or pointing flux, but you seem to be all your analysis is based on it taking to electron. Okay. So what is the point in talking about whether it's baryonic and pointing flux? All your analysis is based on electronic. Whatever you're doing.
Yes, sir.
Okay, it's electronic, right?
Yeah, so it depends. Like, so there are even hydrodynamic simulation models that also been tried. I think what Bhargav also showed that even if you start off with magnetic field lines, which are very strong, because you need magnetic field lines or particles just to launch the jet by the theories of launching of jets. But it's also saying that by the time they come out of the stellar cocoon, it mostly dissipates majority of it, and it largely becomes a baryon-dominated jet as it flows out. So
don't say baryon all the time. They don't say baryon. They say it's electronic.
It's electronic. It becomes basically kinetically dominated. So basically, the kinetic pressure.
Yeah. So, but there are, as I must also tell that there are, like for synchrotron models, largely they have a lot of issues with electronic synchrotron models to explain certain data. And there are a group of people who have now come up with hadronic synchrotron models to explain certain aspects of it. So I would still say it's an open thing. And
no, it's how the jets are launched is an open thing. Nobody knows.
I think
what I'm saying is that when you're talking about the contents, and all your analysis is based on leptonic medium, whether it's fast moving, slow moving, doesn't matter. Then this question, you will never be able to raise this question in the first place.
No, so yeah. So I would address it in because of course in DRPs we have to do it all in a model inference mode. When I put that question, that was a general open questions. Like there are cases where I have also published papers on where we have found GRPs which are highly dominant in the photospheric or blackbody components. So those cases you cannot explain it using a pointing cluster. So those cases definitely we'll have to go with other radiation dominant or like not radiation like but baryon dominated or electronic dominated.
We just kind of hindered, the jet will be hindered.
But at the same time, for example, this very GRB itself, if you consider, we are asking that it has to have ordered magnetic fields on scales at least of 1 over gamma.
I have no problem with magnetic fields. Magnet is fine. What I'm saying is,
yeah, you want more.
You can't even talk about whether it's baryonic or not. No. That's what I'm saying. It might be. It might have baryon loading. I have no problem with that either. What I am saying is, with the analysis you are doing, you will not even be able to scratch the question. What is the content of the jet? That's my point.
Yeah. But maybe someone in the audience will be inspired to do the hadronic modeling. That's why.
But you see, problem with hadronic modeling is that if you insert hadron, it's very difficult to go to gamma of 500. I mean, it's impossible.
But these with like range of 55 because also like.
But this is low luminosity.
No, it's very high.
Okay, one last question by Jagdish.
Okay, so just wanted to know about this onset of particle acceleration. So you have this shock region where the particles are evolving with time. They did synchrotron cooling, inverse Raman cooling, and even the shock region is expanding with time. So you actually said something like the particles cool, and then you find the signature of onset of particle acceleration.
Yeah.
So how can you just comment?
No, so what we see is that, see, the particles, the first, when I say that particles are definitely accelerated, and we have seen it cooled, and that is how we already saw the radiation. Right? So generally what we see is when we model the spectrum and when we look at the electron distribution, we kind of roughly get a feeling of there is a certain fraction of electrons which are cooled and certain fraction of electrons which are still being in the power loop. Right. So what we saw in the first interval was that it was completely cool because there was no power law and it was a cutoff. So it seems electrons have entirely cooled.
They
Whereas
are
in that one
continuously injected by the central region. Is that correct? Right.
Sorry?
The particles are continuously injected by the
Yeah,
central region.
that is what we said. We proposed is that
Yeah, that's what.
as
one shot.
No,
But you can take the assumption like you do the afterglow model. You can actually assume the particles.
Sometimes
no, so there are different ways to look at it. One is that even from the central engine, as I said, different shells of matter get jetted out. You can have a change in the number of matter that is ejected with time, which is also there. So the number can change. And along with that, what we proposed here was that, like, maybe as it interacts through that ring, the ring also might have certain clumps, or we do not know the density profile of how that ring is. And maybe it is that might have changed or induced more electrons in that region, and because of the change in properties of the shock, it might have.
Just one quick question you can answer later on. We can talk in the, because the question is, and others I forget, is that you had a very long prompt emission, right?
Yeah.
Okay, this was very low and then. So, I mean, could you just talk, say something about what exactly is going on there in the
That long. Yeah, so what we suggested was this. So in this,
I think,
yeah,
you can answer the question. But I will forget the question.
I'm sorry about that, but we still have 5 more talks to before we conclude the session. So the next talk will be, let's thank Shabnam once again for a very interesting talk. The next talk is by Mukesh Vyas. And he'll be speaking about photon scattering in a relativistic outflow having velocity shear.
Thank you, madam. So in next 20 minutes, we'll be learning about a photon's journey in a plasma with velocity shear. It is an overlooked but a very abundant phenomenon in high energy astrophysics. My name is Mukesh. I did my PhD here, and currently I'm a postdoc at Bar-Ilan University, Israel, working with Saha here. It doesn't go. So here's the outline. I will introduce Fermi acceleration and demonstrate that our work is a photon analog of Fermi process, and we'll analyze we'll explain the model with results, and we'll conclude the talk. So I always start the talk with something very simple that everybody understands. So Fermi acceleration is a process through which a charged particle gets accelerated across the shock. There's a velocity difference between the fluids across the shock, and the particle oscillates back and forth, scattering with magnetic irregularities. So when the particle goes from pre-shock region to post-shock region, it sees the fluid is coming towards it. It gains energy. So this process keeps on repeating and it gains energy. So the message is, when a charged particle operates between layers of different velocities, it gains energy. And if you integrate it over all the angles, you find out that the fractional energy change of the electron is proportional to the speed, relative speed of the shock regions. A more advanced version of the same process is a shearing plasma. Suppose a fluid is moving with a very high speed in the middle, and the speed is different at different angles. So the same charged particle keeps on scattering with the different layers of different speeds. It also gains energy in the same process.
This is what we know as particle acceleration in shearing flows. So if you type in Google Scholar, shearing flows, particle acceleration, etc., you find there are thousands of paper written in there. So it's very topic, it's famous one. But there is another analog. What if it's not an electron but a photon? You leave a photon, the photon scatters not with magnetic irregularities, scatters with electrons. So if the medium is optically thick, the photon will get scattered with it and it should do something. It's basically compensating the shear layers. So if you put photon population here and it's optically thick plasma, the photons would also scatter with electrons and it will be escaping to the observer. This phenomenon is not studied, while it is present almost everywhere because shear is ubiquitous in relativistic plasma. So this is what I'll be talking about. Not with electrons, which is well studied. What happens to photon in shearing plasma? Okay. So the required conditions are pretty simple. You need a relativistic flow and relativistic flow, but fluid should be optically thick so that the photon can have multiple scatters. And I will show that at the end, the photon population that escapes to the observer, they show power law spectrum. And again, we see power law spectrum everywhere. Like this is the spectrum of Cygnus X1. In soft state, this red curve, you can see that it has a power law at high energies. And you see the power laws in other sources as well. But if you look closely to the structure of these objects, X-ray binaries, you find out that in the inner region of the accretion disk, very close to the black hole, there's a very sharp shear present. So the question which we ask is, does this shear has any role to produce these power laws? It's an unconventional question that we ask. And we showed in previous works that when you study the radiation-driven winds from these accretion disks, winds also have sharp shear. So the shear is present everywhere and it can have a role in what you see in soft state. I can remind that in soft state, you only have the accretion disks, not the jets. It's not just these accretion disks or X-ray binaries. The power laws come everywhere. This is a typical GRB spectrum. At high energies, it has a power law, which is conventionally explained by other synchrotron shock model, as we knew in the last talk. We also presented one more model in recent years, which is backscattering model, that also shows this power law spectrum and bulk of this comptonization through the shear layer is what I will present in this work. So this is the structure. There can be many cases, accretion disks, a plasma that has turbulence, the atmosphere around the neutron stars, they will find the shear. We take just one case in this talk, which is assume a GRD jet, which has a structural profile. It is faster in the middle, slow in the outskirts. And this kind of profile has not only observational evidences, but also from simulation people have seen that the jet should have this kind of profile. It should be faster along the jet axis and should slow down in certain manner as you go away from the central axis. So from these simulations, we can consider this kind of Lorentz vector profile, with gamma 0 being the Lorentz vector at the center along the axis, and gamma minimum is far away from this axis. In between, it changes with this kind of profile, and P is profile index. It's typically like the power law change. But that doesn't matter, no matter what the change is. If it changes from some Lorentz vector to another, there's a shear. So how we proceed? We do two types of studies. One is numerical simulations, and other one is theoretical study. So numerical simulations, it's a Monte Carlo code. You have a jet, you give the Lorentz vector profile, inject millions of photons at the base, track each and every photon, keeps on having scattering with the shear layers, and once the jet becomes optically thin, with optical depth equals 1, it escapes to the observer. It can escape at all angles. You can map any observer at any place, and the observer will receive these parallel wavefronts. So you can see through numerical simulations what is the distribution, spectral distribution of those photons which went through the scattering between these layers. So this is one way of finding out. Second one is analytic. We also want to develop a theoretical model, how the spectra should behave. So this is a simple geometric description of the same model, jet, and at any point you see there are two electrons, a photon scatters from one electron to another with mean free path lambda, and it has a scattering angle. So in the electron rest frame, let's say the second electron's rest frame, the energies are equal if it's Thomson scattering, and simple relativistic transformation gives us the energy gain in one scattering in the left frame, which turns out to be this one. So we see that the ratio of the Lorentz vector between these two electrons are moving with different Lorentz vectors, right? So this electron has gamma, this electron has gamma 2. So the gain can be found out, which is proportional to the gradient of Lorentz vectors. Here xi is a coordinate. So you can give any distribution of Lorentz vector gradient. It can change with radial distance, with angle. Here, though, to assume that the Lorentz vector changes only with theta. It's just a polar angle dependence. So when we work out this, we find out that the gain per scattering is a function of coordinates, because the Lorentz vector is a function of coordinates. At different coordinates, the Lorentz vector is different, so we get the different gain. So you get a gain which depends where the photon is scattering at the particular moment. You also see this A, which is the mean free path over the radial coordinate. This A is basically the expansion factor. As you can see, the plasma is not cylindrical, it's expanding. So you can imagine two layers which are moving like this. So when electron scatters from one layer to another, there's already an expansion factor. Because of that expansion, photon loses energy. So it gains energy because of this shear, loses energy because of the expansion. So everything has been taken care of. In fact, it can lose energy while in the shear also. It depends on which angle it is trying to hit. But you can find out that on an average, it gains energy. So that gain was coordinate dependent, depending upon particular coordinates. So to find out the spectral slot, you need to find out what is the average gain. To find the average gain, we integrate it and find the expectation value over entire scattering volume. It will give me one number for given set of parameters. What is the maximum Lorentz vector? What is the minimum? What is the profile index? You put one set of parameters, integrate it over entire space, divide by the volume, you find out one number of average energy gain that the photon should have once it escapes. Next, what you need is the probabilities, scattering probabilities. Again, the scattering probabilities are coordinate dependent, depends on optical depths. If optical depth is 1, the photon escapes, doesn't scatter anymore. If it's high, keeps on scattering. But there's one more problem here, which is, does this pen work? Okay. So this is the jet. It is faster in the middle and slower in the outskirts. So the Lorentz vector is like this, as I explained. Optical depth goes like this. So in the middle, the optical depth is less. It's because of the relativistic, you see the optical depths. It depends on the Lorentz vectors. So in the middle funnel here, the optical depths are less. So what happens is when the photon gets scattered like this, once it enters in this optical funnel, in the center funnel, just escapes because the optical depths are minimum in the center. This is why when you see this distribution of photons here, most of the high energy photons are escaping from the inner region of the jet. This is exactly because the optical depth in the middle funnel is very small.
Why there is no lambda dependence on optical depth?
Is
lambda dependence on optical depth?
It is. That's why it comes in this densities. I did not show all the calculations. But
Also sigma.
sigma is cross section, it's Thomson.
So
Yeah, of course, it depends on cross section. Depends. It's constant here. It depends. That's why it is coordinate dependent. So probably, so there are two types of optical depths. One, it escapes to photospheric radial surface outside. Second, we had to make an assumption here. When the photon escapes to the middle region, inner region here, it just escapes. So we assume that in the middle funnel, optical depth is very small, which is true. Yeah, it is because the optical depth is very small in the funnel. So most of the photons scatter from the inner region. Okay. Now again, the same problem. The optical depth is coordinate dependent. And then you have to find the average optical depth. So entire scattering space dividing by the volume. And this is why you get a single number of probabilities. Where we use these, suppose you inject N0 photons, after K scattering, N photons are left. This is a standard calculation for the energy gain for electrons. So we repeat the same thing. If you manipulate this a little bit, you find out that the spectrum of the photons that escape should depend on energy in form of the power law. So the photon index should be given by beta. And again, it depends on P bar and P bar that we calculated before. So just plug in those numbers here, you can find out what will be the photon index of the escape photon population. Now we come to the results. As I showed, we have two ways of finding this. One is through numerical simulations, other one, the analytic one that we obtained. So we inject the monoelectric photons with this energy, and they go through plenty of scatterings, they escape, and this is the spectrum of the photons for an observer which is at 0 degree. It's along the axis. And you can see, as we expected, the photons distribute themselves in form of power law. Or P given by, I think P is 4 here, I cannot see it. But we kept its profile index P is 4. You can keep on changing this. And this is the Lorentz profile. Okay. So this is simulated results. And if I put this value of P and find out G bar and P bar and calculate it analytically, the beta turns out to be this, which is again hidden, is minus 2 point something. 1 second. I forgot the number. Okay, minus 1.76. So analytic beta is 1.76 and numerical simulation like this. So we have perfect agreement between the simulations and our theory, which are independent of each other. If you increase P, you know P is the profile index which determines how fast the Lorentz vector is changing between the layers. So if you increase P, that means the shear is pretty strong. What you expect is once you increase the value of P 2.546, the spectrum becomes harder because photons get more energy. Another problem is if you keep on increasing P, the region becomes smaller. So it goes both ways. The photons gain more energy because the shear is pretty strong, but the region becomes smaller. Like if you increase P, the Lorentz vector goes like this. It's pretty sharp. So this region keeps on decreasing by the given function we have taken. So the spectrum becomes harder, both in numerical simulations and in analytic calculations. At the end, we compare the simulations and the theory, changing P from 0 to infinity, and beta turns out to be like this. So this dashed curve is coming from this analytic results, and these dots are simulation results, which are in agreement with each other. Now, there's one interesting thing you can see here, is that the power law is vanishing at P equals roughly 2. What we generally expect is it should vanish at P equals 0. If you put P equals 0, it's constant Lorentz vector. But the question is why it is vanishing at finite P. It is because there's an expansion factor. The expansion factor leads to the loss of energy of the photons. Shear layer leads to the energy gain. So if P is less than 2, that means it cannot overcome the energy loss by the expansion. It's just to see the beauty of the process here. So there is some finite value of P through which the power laws appear. So the range of beta that we get here is minus infinity to minus 1.5 in both the simulations in theory. So this is the work that I presented here now. The range of obtained range through observations of the high energy power laws in gamma ray burst form phase is of the similar order. It's very steep, sometimes very steep. It's not the power law, sometimes it is too steep, you cannot even see if it is power law or not. But it mostly goes up to minus 1.5, maybe a little bit more than that.
Why are you misspelling your own name?
Double joint.
Consider this is really. So this beta range, we recover the range of beta, so that we have a way of saying that it's a new mechanism through which you can generate high energy power laws, and you can explain those power laws appearing in gamma ray burst. But as I said, the theory is not limited to gamma ray burst as well. It can be, it is applicable to many other sources like AGN. Another work that we did is in blazar jets, where we explained this edge brightening of the blazar jets. We discussed in one of the talks yesterday. We explained this using this model. If there is a shear in the photon and the Lorentz vector distribution and the AGN jets, we could show that naturally this limb brightening comes close to the JKS. This is under review and it's a topic of another presentation. It is going through strict review because it's slightly unconventional explanation to this. And again, the jets can be accelerating and decelerating. There are many evidences and observations that the jets do accelerate or decelerate. Accelerate at small scales, decelerate at large scales. So when they decelerate, you can imagine a photon striking against decelerating layers. The same process should take place. It is worth investigating as well. And in the turbulent plasma or the inner region of the accretion disks, and the many other cases you can imagine. Another one where you can say that in the neutron star atmosphere, when the matter falls onto the surface of the neutron star, it forms a strong shock. So the velocity is higher at the outer side, while it dips pretty small at the surface. So you can imagine photons trapped between those layers. The same process will go on. So one needs to check what happened to the photon population there as well. So a lot of things to discuss. And also we were having a discussion at T 2 days before with Chadma. She told that they obtained high energy photons have a lag with the soft photons. So we just had a discussion about this. It can naturally come from there. If the soft photons just escape after the first few scatterings, but high energy photons spend a long time in the scatterings, gain energy. So they will come in later. They will be coming later. So we haven't checked the numbers yet, but these are the possibilities. Maybe one of the many predictions that we will make with this. Thank you.
Go back to the spectra, similarity spectra. One slide, maybe. Yeah, here. So how do you decide where to fit the power line? Is there like a little shoulder before you are fitting the power line?
There is a Python program that fits the power load.
So you have to select the data point.
That is the best answer. That's a bad answer.
Yeah, I'm not very good in fitting these things.
But I'm saying
Having a shoulder part.
Shoulder
Why
is here.
Yeah, so why are you putting it there and not somewhere else?
you might not have many data points further down. I see some sort of cutoff where you're starting your power.
So you want I should be starting from here?
No, different power laws are given.
Yeah, you have some sort of two power laws.
Okay, in observations you also get two power laws, right?
This is not observation, this is simulation.
No, that's what I'm saying. We did not concentrate on the lower part of this part, right? So
what is the injected energy?
It's 10 to the minus 7 electrons hash mass. Thomson photons. 10 to the minus 7 times the electrons hash mass. So yeah.
In observation, that is cutoff. Second one is beta. No,
Scale is.
so beta is like the center one, which is between two shoulders.
Yeah, so if you see there are two power laws right here, but what we wanted to see is only the population of those. For why I chose this part is the question, right?
Yeah, because you have to have some sort of numbers for where to decide where to fit the power pass. Further down, you have very little bit of data points. I think if you put data points in this part, further down you might not have it in the same.
Yeah, but I could see that this is a clear power law, so I just fitted this one. And there's a routine written that fits. I'm not very good at
Very bad answer.
So, okay, but
PhD allow.
Okay,
review में बैठता हूँ.
Mukesh, I have a couple of questions regarding the efficiency of this whole process. You see, my first question is how good approximation is Thompson scattering? Klein-Ishina would work here better. A. Point number 2 is that when you're comparing something with traditional shock acceleration, and in shock acceleration, the electron scatters always has an head-on collision. That's why Fermi first order is far more efficient. Whereas over here, the photons need not have a head-on collision with the electrons. Right? So it will be absolutely inefficient process. So the question is the time scales of this acceleration is much larger than what you would expect in any of these. So that's the two major concerns I have.
So we saw in the simulation that if the photon says there are only just 10 to 15 scatterings, they regain energy in that case. So the time scale is
but the cross section is wrong. Cross section should be Klein-Ishina.
In simulation, they just Klein-Ishina. Analytic it is Thomson. Simulation time doesn't have.
So then how do they match?
Because the photon's energy is pretty small. You see, Klein-Ishina is applicable only to photon's energy related to electron energy. So it's 10 to the minus 7 rest mass energy of the photons, which is still small here. So most of the photons will get the energy, which is smaller than the electrons. I think Thomson's scattering.
No, I think what I mean, generally speaking, if this photon and electrons scatter, the scattering is taken in the electron rest frame.
Yeah.
So if the electron is moving very fast anyway, then if you do the dilation, this Lorentz transformation.
The whole interaction is done in the rest frame of the electron.
Doesn't matter. The energy of the electron and the energy of the proton, if they are comparable, then the cross section
is not comparable. Photon energy is pretty small.
Okay.
The photon
When
energy
you go to the electron rest frame, then if you make this Lorentz transformation, the energy becomes of the photon becomes much less than this rest
that is how it enables to use the Thomson scattering cross section.
That's everybody does that.
That is,
All the radiation pundits are doing that.
It will start affecting at very high energies when the photon's energy becomes comparable to the electron's rest mass. That is the portion where the cutoff is.
I have many issues. I'll talk to you separately.
Okay, I have a question regarding the spectral lag. You are explaining you can explain the spectral lag using this model. So we didn't observe spectral lag in case of short gamma rivers. So the question is now again connected to his question, that is it dependent on the time scale? So if the time scales are too short, that in case of short gamma rivers they didn't get that time to get this spectral lag in high energy and low energy photons.
It depends on what optical.
What are the time scales?
So time scale is a fraction of second to 7 seconds. It depends on what optical depth you launch photons with.
Okay. So that can explain the absence of spectral lag in case of short gamma rivers.
No, you have the spectral lag. What did you say? The spectra is there for short gamma rays, no?
But lag is not.
Lag is not there in case of short.
We haven't studied that lag yet.
Okay. I get the answer.
Maybe,
Sure.
Yeah, and so I have two questions. So one is that how much, because in your simulation, you know how many number of photons you have injected. So how much fraction of that actually comes in this power law?
It's a small fraction.
You have a number like how much percentage of your total?
10 to the minus 5, which is minus 4, minus 5.
Okay, and whatever you showed here is basically for an on-axis case. So do you have an idea, like if you considered it off-axis, will these power law indices or like the power law expectations that you're seeing?
Okay. The analytic work is for only on-axis jets. How the simulations are capable of explaining the spectra. So what you would see that the power law that you get, it doesn't depend on observer's angle, high energy power law, because with the intrinsic process, once it escapes, it doesn't matter where the observer is. The fluxes do change, but beta remains roughly the same for all of them. That's what I could check when I check for different objects.
Remind me what is beta?
Beta is high energy power law. High energy photon index.
This is just the
photon index.
The issue of the escape over the acceleration time.
Okay, one last question, Pratik.
I wanted to ask you something completely different. Did I understand you correctly that you can generate an energy-dependent time delay of the photons in this process?
Yes.
You can. So in case I give you an a measure of an energy-dependent time delay at the detector, and you can do that in your simulations, can you test Lorentz invariance violation study? Can you do an LIV study from your simulations?
What is invariance here?
That the photon, the photon will speed of there is an energy dependent due to the travel of the photon.
Yeah, but
not at the source, but due to the space in the space itself. That's a Lorentz invariance.
There is
Right?
something-
And I want to test if it's a violated or if I want to make a test of violation of that or not.
I think we will discuss about it, but here it is only because of the photon is spending time between the electrons.
And so photon energy should be.
It needs an optical depth.
Yeah.
It needs some optical
No,
depth.
but if I have a large energy range from MEV photons to TeV photons on the GRP coming out, and if I see an energy dependent time delay, assuming that I can take care of the delay of the photons at the source, I can make the study of what is happening in the space.
So I think the photon energy should be very, very high.
Photon energy has to be very high.
I think those photon energy are very, very low.
Okay.
These are low, but the simulations can take care of the high energy photons as well. But if the photon energy is very high, it just shoots the electron away and doesn't get energy anymore. So there is a cutoff after that.
Okay, let's thank Mukesh for this very nice talk. The discussions can continue over the tea break. The next talk is by Dimple before we break for tea. I should start talking, I think. Okay, thanks for giving me this opportunity to present my work here. So apart from the theory and simulation that was going on till now, I will be talking about the observational aspects and the machine learning algorithm. So the talk will be about, today's talk will be about insights into the GRB classification using machine learning algorithm. Some of the glimpses of the classification conundrum are already given by Amit. Thank you. And I will be looking for the solution of this conundrum through machine learning algorithms. So I'm skipping this part that you already have a very good introduction of gamma ray burst through last talks on gamma ray burst. So I will be talking about the classification. So initially in 1993, the classification was introduced based on their duration, T90 duration, which represents the time period in which 90% of fluence is collected by any detector or any instrument. So this distribution shows the bimodality in this, which clearly indicates that there are two classes of gamma ray burst, and they could have two different progenitors. So talking about their properties, which give hints what can be the progenitors of these two classes, on galactic scale, the location of the gamma ray burst can tell more about their origin, their history. So on galactic scale, short gamma ray bursts are found to be share diverse host galaxy type, which shows that they have broad delay time distribution. Delay time distribution here is the time from the birth of the progenitor to the burst, to the end of their lifetime. On subgalactic scale, they are found to be placed at large offset from the center of the galaxy, which shows that they might be kicked out from their birth sites. On individual progenitor scales, they are found to be associated with gravitation wave. From this event, you all know gravitation wave 170817. They have low density environments, which means they are located at the halo of the galaxies, and they are found to be associated with R2 nucleosynthesis, which shows that they might originate from the compact binary mergers. On the other hand, the long gamma ray bursts found to be associated with this young stellar population, and they have negligible offset, and they are found to be associated with supernovae, which shows that they might originate from the collapsed stars. Now the picture is very clear. We have already picked that short gamma ray bursts, which have T90 duration less than 2 seconds, originate from the compact binary merger, and long gamma ray bursts originate from the collapser. But we have challenges ahead. What are these challenges? For example, this GRB 210217A, it was observed by two of the satellites, Swift and Fermi, but the both satellites reported it as different classification. Swift classified it as a long burst with a duration of 4 seconds, and the Fermi classified it as a short burst. Now the question is not about short or long. We are tracing back their history. We are tracing back with the duration that either they are coming from the compact binary merger or from the collapser. So the question is, what can be their progenitors? So apart from this GRB, there are 16 other GRB which are facing the same problem. They have been observed from various satellites and classified differently. Apart from this, Amit has already talked about GRB 211211A, which is a long GRB found to be associated with the kilonova, giving indication that it is associated with compact binary merger. Apart from this, GRB 20826A, which is a short GRB, was found to be associated with the collapser. Now, you will say that they might die on the boundary of their separation, but this short gamma ray burst was found to be of existing for 0.96 seconds, and this is again lying very far away from the boundary with T90 duration of 43 seconds. Now, how to solve this conundrum? So one thing, we can use the existing parameter which differentiate between these two classes. Using those parameters, we can get a hint if it is coming from compact binary or from the collapser. So what we have we have done in case of 210217A, we use these three parameters, these three distributions, to calculate the probability of this burst being a short GRB using the Gaussian mixture model, which is a machine learning algorithm. But again, for case of hardness ratio, the probability is 98%. For E peak, it is 96%. For minimum variability time scale, it is 28%. Again, we have confusion if it is a short or long. It is going with short or long. So these methods are dependent on T90 duration, which is again dependent on the satellite or the method of extraction, and it do not capture all the information. We have bits of information: E peak, T90, hardness ratio, and minimum variability time scale. So we have to move on to some other method. So one approach can be, we should use the full light curves without extracting any parameter. You should, if you use the raw light curves and give it to some of single satellite and give it to some machine learning algorithm to capture the fine structure in the light curves, what will we get? So we analyzed the prompt emission light curves like these light curves. Okay. So for this work, we use the prompt emission light curve from Swift catalog, but the problem is this has a diverse data set which shows different duration, fluence, and start time of the burst. So we need to standardize the data so that the machine learning algorithm do not distract with this information. So we standardize the data with few steps, normalizing the light curve by fluence, shifting them to the same start time, padding them with the zeros, and then applying the Fourier transform. Now, after doing this, the next challenge was to manage this huge data. So the dimension of the matrix that we got after standardization was 1400 into 26,000. So to give it directly to the machine learning algorithm, that can again distract the algorithm. So we followed the approach. We first reduced the dimensionality of the data using principal component analysis, and we use the components which give the 99% of the information. These are the 500 components. Now safely we can give these number of components, this data, to the unsupervised machine learning algorithm. So we give it the used UMAP, which is a topological algorithm which squeeze the high dimensional data based on the similarity, dissimilarity between different data points and squeeze it to the lower dimension. So this is 2-dimension two-dimensional clustering that we got after applying this algorithm to our data. So each point is representing a GRB. And if these 2 points, these 2 GRBs are lying closer, that means they are similar. The coin structure within the light source is similar. If they are lying apart, one is lying here, one is lying here, that they are dissimilar. This is a simple interpretation, but we got. But so to check what are the clusters embedded in this 2D plane, we check the density profile, and we observed that there are 5 different subclusters embedded in this cluster. Now the next step is to use this clustering. Now how to use this clustering? We have 5 clusters. How to use this clustering to interpret, to break this conundrum. So what we have done in this interpretation of we have used this for the interpretation of kilonova associated GRBs. So we put all the kilonova associated GRB in the embedding, and interestingly, the all short gamma ray bursts that are associated with the kilonova are lying at one end, and the long gamma ray bursts which are associated with the kilonova are lying on the another end. So initially, when we performed this machine learning algorithm, we thought that the all kilonova associated GRB should lie together because all are coming from the compact binary merger. But we got this. So I was confused if there is something wrong with the machine learning algorithm, if the results are wrong. So I used different algorithm which is independent of UMAP, TSNE, which use the neighborhood distribution to put together all the data points similar and dissimilar. We again got the same result with the independent algorithm. The 2 classes, short gamma ray burst associated with kilonova and long gamma ray burst associated with kilonova, lies apart. Now, from these embeddings, it is difficult to say what exactly is the mechanism, what is moving these GRBs apart. So what can be done with the existing information? We know the T90, we know the minimum variability timescale. We color coded all the embedding using these parameters T90 and minimum variability timescale. Now these 2 parameters give important information about their progenitor system. T90 tells that how much time the central engine will be active, and minimum variability timescale tells about the emitting size of the emitting region of the progenitors. So for these 2 clusters, you can see this cluster, the T90 duration is less as compared to this cluster, and minimum variability timescale are similar, which shows that central engine is active for a longer time for the long gamma ray burst, but the compactness of the central engine is similar. So what can be interpreted with this? What can be the possible progenitor? So there can be subgroup within the compact binary mergers itself. One can come from the binary neutron star, other can come from the binary neutron star black hole mergers, or there can be subclasses within the binary neutron star itself. So the outcomes, what we get after the merger, that depends on the extent of tidal disruption, the masses of neutron star and black hole involved, the maximum mass of neutron stars supported by the equation of state, and the spins of compact binary involved. So what can be the pathways in case of BNS mergers and in case of neutron star black hole merger? Now I'm talking about GRB 211211A, what caused the central engine to be active for a longer time, which we do not expect in case of compact binary mergers. So if in case of binary neutron star merger, if at least one neutron star has high magnetic field, it can halt this, and that can elongate the duration of the burst. Apart from that, the BNS merger, if we are looking at different angles, that can also mislead the if we are looking at different angle, at this angle or that angle, that can also give different duration of the burst. Looking for the neutron star black hole mergers, if the tidal if it has efficient tidal disruption material, it can elongate the duration of the burst, which was confirmed by Zhu et al., which invoked the fallback accretion to the remnant black hole to explain the long duration of these three long bursts, which was associated with the kilonovae. So what are the future aspects of this work? So one thing is we can predict in future, we can predict the kilonovae association of the GRB association with the long gamma ray burst or short gamma ray burst. If some burst is lying close to this cluster, if some burst is lying in this cluster, then it might be associated with the kilonovae, and it is worth observing that candidate. So one implication is that apart from that, we have 5 clusters, subcluster. We can check what can be the progenitor system of these. And apart from that, we can check other VHE emission, if they are similar or not. In case of VHE emission, we can check projection of the VHE emission GRBs and can check if they are similar or not, or if they are like other general GRBs. So, okay. And with next generation gravitation wave detector, we can disentangle the black hole neutron star merger or binary neutron star merger, these kind of progenitor from that. How the spin, how the inclination are affecting the afterglows or the EM counterpart of these compact binary. So with this, I conclude my work. So for more detailed questions.
Thank you. Questions?
You said that the long duration bursts is because of it has a stronger magnetic field. Okay, but the problem with that is that if you have, I understand, if you have a stronger magnetic field, then the two neutron stars which are sort of inspiraling will have to overcome the magnetic field energy of both, right? But the GRB is not because of this burst, right? The GRB is because of the, I mean, according to the theory, is in the collision of the internal shocks, collision of two, I mean, shells in the jet itself.
Yes.
So
how much time the jet will be active, that will be dependent on the disruption of the neutron star to the black hole. So if the material is halted and it didn't get that time
No, you're not understanding. What I'm saying is that whenever, I mean, even if it is a by BNS merger or it's a BNS black hole merger, whatever, any two things merge, then after it merges, it will form the proto neutron star or proto black hole. Okay. And the circumstellar material, that will become the temporary accretion disk. This is gospel. Okay. I mean, I'm not saying this either or any of them is true. But as far as the gospel goes, then you have this temporary accretion disk, and things are so hot, so much matter is, eaten up in such a small time. It really creates a very highly energetic, scenario, and it really fires to very relativistic jets. Yes. And when you are, firing at say Lorentz factors of hundreds, then obviously one shell will be faster than the other shell, and they will collide and they produce the gamma ray burst. Yes. Okay. From here, after it collides, the rest of the things is more or less at least 50-60% we understand. Okay. The point is that this long burst, long prompt emission cannot, I mean, as far as I can sort of think of at the moment, that cannot be just thought of by two merging strong magnetic field neutron stars. Because after it merges, then the whole central engine is kicked up. The strong magnetic field of the neutron stars will actually delay the merger. And after the merger happens, then the whole thing starts.
Okay. So if you look at a different manner, you said that there is a accretion disk that will.
No, it will come later, after it merges.
After it merges, if the final product has high magnetic field and the spin, then the accretion disk, the time of the accretion disk, it will.
No, that has no. I mean, if it is first of all, it has to be neutron star to have a magnetic field. Yes. A black will not have a magnetic field in the first place. Okay. But let's say there's a neutron star and there is so much matter around. So like you have more than around, stellar mass material around. Okay. Solar mass material around, not stellar mass. So that is being eaten up in few seconds or few tenths of seconds.
So
okay.
What I assume
So what it will do, it will, because of the pass field, it will open up the closed field lines to open field lines, and it will, power very fast jets. But having a strong magnetic field of the two binaries, you're not okay. I'll talk to you later.
Okay.
It will delay the merger. That's what I'm trying to say.
So
Merger delay time, not the jet duration.
okay. So my point is, after the merger, the central engine, the neutron star, if it is with high magnetic field, then the accretion disk around it can halt for longer duration. And
It never halts. What will do? It will channelize with the.
yeah, it will channelize. So it will channelize in a longer time.
No, it will be very fast. It will be
Okay.
faster than that.
I'm comparing the short duration 2 seconds and the long duration greater than 2 seconds. So it can channelize in more than 2 seconds. So that's the longer
Magnetically, it
duration.
will be more about how much material is there around
Yeah.
it. That would be.
Yeah, that is the point. That material, in how much time the material will be channelized, that time will be.
Simple, very interesting work. One of my master students also work on the similar lines, but not exactly same algorithm. So I want to actually learn that how you are standardizing your light curves for short and long GRV, because at some point you said you are taking a Fourier transform. And once you take the Fourier transform, if you have a short GRV and the signal which is you are getting from that, you have basically less bins. So if you extend it for the same time, you are actually integrating to noise. And that gives you a much flatter
Yes.
noise.
And next task is to check what is the effect of FFT or for the first.
The other question I have, have you taken care of the red noise leaking? Which is basically if you have the same flux levels. Because if that is not the case, then you get the spectrum which is not correct. So there's some intricacies, but probably we can discuss.
Okay, the future project is on that.
Sure,
We will look for the
Actually, one of
FFT.
my master's students did a similar thing, and we are struggling with the point how to normalize it, because if we go for the
Both of you have the same problem?
Sorry?
Both of you have the same problem? Your master's student.
So ideas are similar. So, but we are using a different algorithm. But the issue is you have if you take a short GRB, then you have a less time to integrate. Then you actually integrate over the noise. And your spectrum, when you take the Fourier transform, it becomes much flatter, white noise kind of the thing.
We haven't taken those short GRB which have very less duration.
Okay. So
and apart
probably we can discuss at some point.
Yeah, I think more or less on that line, but because you have included both short and long GRBs in the classification, right? So when you take in the light curves, the binning becomes a significant factor, deciding which binning to choose, because you have to see the signal first to use.
So for this, we have used 64 millisecond binning, and we showed gamma reverse which have durations less than 64 milliseconds. We have omitted all those gamma reverse. And apart from that, which is the future work, we are looking for the implication of the binning on this clustering. But for this project, we have taken binning of 64 milliseconds, so that short and long both it should not affect the both.
But the preliminary results with different binnings also do not
Don't show any
variations. Variations on it. Okay, and then you have also done the minimum variable times.
Yeah.
So what method did you use to establish the minimum variable?
So because we had huge samples, so for all the gamma variables, it is difficult to do wavelet analysis and to calculate the minimum variability time scale. So what we have considered we have done the Bayesian binning, and the shortest Bayesian bin we have considered that the minimum variability time scale should be near that.
Yeah,
that is
so,
a huge method, I know, but
so
we will be looking for.
Yeah, so that is one thing which anyway if you do, you will see it, because I've done a work similar on that. So actually the minimum variability timescale estimates from Bayesian block and the wavelet analysis do not match.
Okay.
There is a correlation problem with both these estimates. So this can be something that, when
That
you
can
do,
be taken
yeah,
care of.
you can do it.
Yeah. I'm thinking of doing that because I know it is pure method. So just to see the trend, how the, if you say that how the shortest begin will show the trend in this.
We have left.
So,
Go for the school that will be boarding.
okay, so let's break for tea now, and some of the discussion can continue over tea. And please try to be back by 4:05 because we still have 3 more talks to go. So let's keep this tea break short for about 15 minutes.
Test. Yeah, this is this. ये ऊपर वाला नीचे क्यों जा रहा है? अच्छा स्टोर जा रहा है। हाँ, कहाँ जा रहा है? ये नेक्स्ट के लिए है, बैक के लिए। अच्छा, बैक के लिए। ये बैक के लिए और ये नेक्स्ट के लिए ऐसे है। पूरा जो होल बटन है नेक्स्ट। अच्छा, इसको खाली दबा तो नेक्स्ट, और पीछे आना है तो नेक्स्ट। पॉइंट के लिए। हाँ, पॉइंट के लिए।
मैं 20 मिनट्स में बता दूंगी ताकि फिर 5 मिनट्स और रहेगा तो 5 मिनट्स
क्वेश्चन
20 में एक बार मैं
आवाज आएगी। हाँ, यही यहाँ लगा ये अच्छा। हाँ, ठीक है। आप ठीक है।
Okay, so let's begin with the last session of this exciting conference. We have three talks in this session. The first talk will be by Jagdish. It's on very high energy gamma rays from GRB afterglows, implications for radiator models.
Am I audible? Okay, so following the normal distribution, let me just thank the organizer for scheduling this nice conference and giving this chance to speak here. So I will be talking about VHE gamma rays from GRB. So when we call VHE, that means 100 GeV to 100 TeV. Okay. So we also have ultra high energy gamma rays, and that is very difficult to actually observe from these extragalactic distances. But we do have definitely the galactic object in ultra high energy, which is like 100 TeV to 100 PeV. So I will talk about VHE gamma rays and then how it can help us. Basically, there were some of the questions like Thomson regime, clandestine regime kind of processes, which can actually come into picture now when we do modeling. So this work has been developed in collaboration with Soeb, and then Monica also joined it, and then interaction with us. Okay, so the outline of the talk, I think already in the GRB session, there is a lot of discussion about what are the models there. And I will try to just hint, like the models are actually motivated by the observations. Okay, like you start with some kind of, you have in priority some observations, and then you start building a model. So people were asking that, okay, can we put proton very easily in GRB jets? It was very frankly, people were using that in the past. But it was the ice cube detection of GRB 130427A, when actually they tried to see neutrino detection from the GRB and they did not find anything. So from that point of time, people are a little bit careful. So they don't very freely put protons in the jet. So, okay, so you already know about this GRB evolution. So you have the burst, and then you have the evolution of the Lorentz factor, and then finally you have this external shock. Okay. So in the external shock, electrons as well as protons both can be accelerated to higher energies. Okay, and how we basically trying to understand the composition of the external shock particle by modeling the observations. So the afterglows are basically the late time emission from GRBs, and then So in the afterglow, you have the peak emission when the blast wave starts decelerating, and after that, the afterglow follows self-similar evolution. During the self-similar evolution, you can write the Lorentz factor as as a power law in time, and so that you can evolve Lorentz factor, magnetic field, radius, all of the blast wave of the parameters of the blast wave, and we can constrain some of the parameters like the Lorentz factor, circumburst medium density, and the parameters of the electron spectrum. Okay, now the next question comes. Okay, we have long GRBs and short GRBs, and their progenitors are like type 1b stars. They are like massive stars, and the surrounding mediums are not very well known. It can be ISM, that is very uncertain, like they are very large redshift. So the wind medium persists or not, it's not very clear. So very simple model is one can start with surrounding medium is ISM and do the modeling. And then the more complex is if the surrounding medium is the wind, then the density follows the R dependence, and then you can actually see the features in the light path. Okay, I will just describe synchrotron self-compton model. And the whole idea of synchrotron self-compton model actually got very successful with some of the DHE detection in GRBs. Okay, so we were lucky because we are trying this model, and that GRB in 1901 when Bose happened, we applied this model to this GRB. So we assume a continuous injection of electrons. It follows a power law, and you have the continuity equation here where the losses are like synchrotron and inverse Compton, and then you have the source function. Okay. So here what comes is like this Compton parameter, which is basically the ratio between the power in the synchrotron, SSC peak, synchrotron self-Compton peak, and the synchrotron peak. Okay. And now why, if it is Thomson regime, then it is a constant. But if it is a Klein-Messner regime, then it is a parameter of gamma. So when it is a parameter of gamma, then the equations are like very complex. Like you have to solve for all Lorentz factor, and then it becomes a little bit like heavy to solve. So the solution of this equation in the time-independent regime, one can approximate these behaviors, and then you have the slow cooling and fast cooling. GRBs in the afterglow we are modeling mostly after 50 seconds. So what we have seen, the spectrum of electrons generally taken is in the slow cooling region. So I will not spend much time.
Continuity equation is a strange space.
Sorry?
The continuity equation is a strange space.
Yeah, so it's basically like continuity equation, but you can call it Fokker-Planck when you put the diffusion coefficient. So there is no diffusion coefficient. So it becomes continuity equation. So it's just a balance equation. So, okay, we have. So one of the ideas, like, you have Fermi light, which was seeing photons, and the idea was to know what is the spectrum of a GRB. Okay, so initial detectors, they found photons, like lead detected photons up to tens of GeV, and up to a very, very long time, we could actually model the photons with synchrotron model. But synchrotron model has a limitation. This is the maximum energy produced by synchrotron in the top region. It depends on the Lorentz factor. So if the Lorentz factor is 1000, that is the maximum value, then you can have tens of GeV photons coming from the synchrotron method, synchrotron process. But if the photons are like 100 GeV TeV, then definitely you need a new component of radiation. Okay, so just to say about the GeV TeV radiation implications. So definitely one is the modeling, like synchrotron, or like the leptonic or the hadronic. The second is it can tell us about the intergalactic magnetic field. Like the GeV TeV photons come from very large redshift, and then these electrons propagate through the EVL medium, and then they can produce the electron-positron pairs. So initially you can have a GeV spectrum at the observer, and after some delay you can have MEV photons coming to the observer. So that way you can actually constant the intergalactic magnetic field. You can estimate the upper limit on the Lorentz factor. jet structure, and all these are the Lorentz invariance. Violation is actually, it has come very, very recently in GRBs by 22-1009A, because there are photons above 10 TeV, and then also the Baikal detector, I think the Russian one, they also propose 241 TeV photon, and the redshift is like 0.15. So the standard EVL model doesn't support this kind of propagation of photons. Then actually you need Lorentz invariance violation, because the cross section can actually change, and then the photons can come to the observer. So definitely people also putting axiom kind of documented particles, but in this talk I will just try to give the recent EHE GRB detections and the models what we have applied. So let me just go to one of the bright GRB before at first. So 130427A was one of the first GRB where there was evidence of photons of these energies like 7395 GeV. And Liu et al. Actually modeled this burst using synchrotron self-Compton model. Okay, but it was not very conclusive because we also modeled this burst by a very different approach. We assume that there are nuclei in the, because these are massive stars, there can be some contamination by the nuclei, and then if the nuclei, and there were very these kind of target photons available within the jet. So if you assume it like you basically try to explain these photons, and based on that you constrain what is the number of iron nuclei within the jet. So this kind of model could also explain these photons. So we still don't have a conclusive proof here about the synchrotron self-Compton model. So now I will just go to, there were already a lot of discussion about Toronto telescopes. They are providing us this EHE component, and the idea is to understand the origin of these particles. So well, I have listed some of the GRBs here. These two, based on the isotropic gamma ray energy release, looks like very standard GRBs. This is another one. It has this in low luminosity GRBs. Again, it was detected in the KV-TeV band. There is a recent detection of this GRB, which is called brightest of all time. And so this GRB is actually very recent, and it's changing a lot of understanding, and modeling efforts have increased a lot. So, well, let me just say a few words about these. EHE first GRB is this, where there was you have these photons, and then you have this extra component which cannot be explained by the synchrotron. So, and sorry. So it was having a redshift 0.42, and it was detected by magic on Mars 55 seconds, and the afterglow was like 10 to the power minus 3 times the energy in the probe. So this is the multi-wavelength light curve. It was observed across the multi-wavelength from radio to gamma rays, and you can see here the LED light curve, and also the magic light curve. This. So the second GRB was 180720B. It could not observe it early in time. It started doing the observation around this epoch. Okay, and it was a deep afterglow because the afterglow energy was around 10⁻⁻⁶ compared to the prompt emission. The third one is this, which is low luminosity GRB. Here you can see features like the TeV light curve and the X-ray light curve were very, very following each other in the spectral index. So let me first tell what I am doing. I am basically trying to model these three objects first, and then I will discuss the board GRB, which is modeled by some other groups in the recent efforts. Okay, so as people are already talking about it, about the efficiency of the process, so definitely the electronic ones, they are very, very efficient. The electrons do accelerate and they cool very fast within the dynamic time scale, so the efficiencies are very, very large. Definitely they do depend on these epsilon B, which is the fraction of energy in the magnetic field. In some cases, it can be 10 to the power minus 5 also. So that based on that, you can estimate the this parameter. But the hadronic ones, definitely they are very less efficient comparatively. But still, people do play based on their choice, and they actually sometimes put these models in this.
Is this opacity or time scales?
This is the non-thermal process efficiency, the dynamic time versus the cooling time.
Oh, okay.
So, yeah, so what happens like the particles they cool either in the Thomson regime and or in the Klein-Messina regime. Okay, so in the Klein-Messina regime, what happens like the cross section of interaction becomes less. So particle doesn't cool by inverse Compton that effectively. So the particles are available to cool by the synchrotron process. Okay, so what you will see the signature in general, you will have enhancement in the synchrotron radiation compared to the Thomson. Okay, so these signatures one can probe based on what is the process actually. So here I will just discuss how the Klein-Messina process comes into picture. So this is the cutoff energy one can calculate. So this is the maximum energy where you can find photons. They are in the Thomson regime. Above this energy, they will be in the Klein-Messina. This paper also put this dot curve. So up to here, they basically call it Thomson regime, and here then the interaction goes into the Klein-Messina. So if you have observations in this energy band here, actually then you will start probing the Klein-Messina interaction. So further, this paper also gave this insight that early in time, generally the model can be SSC dominated. Late in time, it can be EC dominated. Okay, so we have tried to check if this is very true in these PHEs. So this is our first SSC model which we applied. What we found, like this is the first curve. It was detected around average time 90 seconds, and the second one is around 150 seconds. Okay, these are the lines. Basically, these photons are without EBL attenuation, and this is the with EBL attenuation. Okay, and what we found, basically the model parameters what we have chosen, based on that we found these photons are in the scattering in the Thomson regime. Okay, if the observations are here, then it would have been a Klein-Messina. But again, it's model dependent. It's because we are not scanning the parameter space. If we scan, then actually we can reach to those steps. So this is another option is because this burst is at a redshift from where we can actually observe photons of 200 GeV without attenuation, and that was again consistent with this model and explaining the data very well. Here comes, so using the same parameter, we also try to explain the light curves. Okay, so this model is the wind one, which is ours, and this is by another group. This is the ISM model. This green line, ours is the optical data, and there this one is the optical data. So there was this hardness seen in the optical data, which we could not explain either of in these two models. Okay, and the origin is still not very clear, but there can be more complex models like jet structure, too many things, which we have not tried still. But yeah, these kind of features sometimes do occur, and they are open to interpret. So these are the model parameters. We basically, so if you see the model parameters, they are very similar to the standard GRBs in general, what we see. And this parameter here in their model, it is the ISM density. And in our model, this is basically 10 to the power minus 7 this solar mass accretion rate. So going to this another, the second GRB, because I told you that in late time there can be EC dominance. So we do check on this GRB, whether this is possible or not. So this GRB has like, okay, so again, this condition has to be satisfied. It is the density of this thing, and then this is the fraction of energy in the magnetic field. The problem here in this plot is this uncertainty. You know, this is huge. Actually, one can fit many models here around this. You know, one can put this synchrotron here to so many. So this is the problem in this source, and maybe that's why the model has a lot of choice.
You don't have any data point there, do you?
This is the error bar with the whole. This one is the whole. range of where the data point can be.
Dots are the data points, right?
No, this is the optical, and then this box is the X-ray.
Oh, acha.
Yeah, this one. But I will just show the next GRB before discussing its modeling. Yeah, if you see this GRB, okay, 1908-29A, it has very, very precise X-ray data, and one can then can't play with this. So the model is more, better explained in this case. So we had these restrictions here, and to follow these restrictions, what we found, even this emission from this GRB is late in time, but it can be explained with the SSC model. But if you check this GRB, here we more or less, we can find some parameter space where the external component can be dominant, and you can explain the bus with the external component. So this is the SSC, and this is the external component part. So the light curve has been explained, and these are the parameters, and this is the the afterglow, where the afterglow are occurring, and these are the standard model parameters for this year. So yeah, so within the SSC model, we could explain the emissions, and they are consistent with these big models. So the whole idea now, up to now, what you have seen, okay, lepton models are very fine, okay. But now I will just show this GRB to you. So what happened? Lasso collaboration published this paper recently, okay, and then they also modeled this whole. Lasso has detected 64,000 photons in this energy range, 0.2 to 10 eV, okay, and this is the data point, and this is the SSC with the Klein-Messina model. You can see for the first two epochs, it cannot explain the data, but in the late epoch, it is fine, okay. And then comes the Zhang et al., which is the most famous guy. This is the second paper. So, yeah, Bing Zhang. So what he did, so he started thinking, okay, what can be the origin of this? Because now the SSC model in this case cannot explain the data very well. Here, he actually got motivated to put protons in the shock region. So the picture is something like this. This is the first GRB, where you can see prompt emission up to here, up to 300 seconds. And also you have afterglow superimposed together, okay? And this MeV emission is given by this Chinese satellite. And this is the nice light curve. And you can see when this MeV photons goes down, it gives less chance for proton absorption, and you can actually estimate larger amount of proton, and then you can have the proton dominance in these cases. So they have a complete SSC plus electromagnetic cascade model. They do P gamma, PP interactions, and they do explain because initial in the time you have prompt and prompt superimposed with the afterglow, so you can see the cascade dominance in the first two light curves, and in the last two ones, it is very clean data, and it is well explained by the SSC, and then they have the SSC dominance for these two epochs. And in their hadron model, they have taken a power law of protons with spectral index -2 and energy range from 1 TeV to 10 eV. And what they found, the expected neutrino events for this duration are around 0.3. So this is the picture, like, what is happening. Like the observations are motivating the model. The neutrino did something good, basically helped us to not really put particles and do the modeling. But now these recent models where you have TeV photons, then definitely you're going to explore the models. So yeah, with this, I will be completing. So just to summarize, we have 4 GRBs. 2 looks like very standard. One is low luminosity GRBs, and that you can model by, you can model by SSC, but there are many groups. They do call it off-axis emission. They do call it ultra-high energy cosmic interaction in that source. So you have multiple choices, but in this talk, I'm not talking about them. And yeah, I have already discussed this both GRB. Yeah, with this, I think.
To add one more to your list, just last week, Magic, this is, got accepted last week. Magic detected another GRB at a redshift of 1.1. So it's a 2012-16C. So this is now currently the highest redshift from which high energy gamma rays have been seen from any object.
What is the maximum energy of photon?
The maximum energy of the photon is about 200 GeV. Okay. Because it's heavily attenuated by the EBL. It's quite consistent with
So it
EBL.
looks like the source will be very, very luminous because it's surpassing the.
Yes.
That much.
Yes. Yeah. So
we can discuss
that would add to your list for your model. But another question I wanted to ask you is that, so the concept that which we had many years ago when we were students, we were hearing talks about GRBs being sources of ultra high energy cosmic rays.
Yes.
Is this now kind of getting dead?
Okay, so it's like the choice of the group. Okay, so there is Kota and Murat's group. They basically say that okay, in the standard GRBs you have radiation field, particles cannot accelerate because the radiation will damp them. So they choose low luminosity GRB. They say, oh, there is no radiation field is less, particle can actually boost to ultra high energy cosmic rays. So those are the hypothetical models actively working for low luminosity GRB as well as for choke GRB. Okay. But once this vote came, brightest of all time, people again started putting the ultra high energy cosmic rays into the picture. So it's a source dependent and driven by the objects.
I did not get it. What do you? I mean, so if there is radiation field, what will it do?
So okay, so this is not my idea.
I know.
Kota at all. So what they call basically, okay, so you have this zone, the stop region where the particles are accelerating. Okay, if there are the radiation field luminosity is very, very high, what they say, okay, P gamma interaction will quench the acceleration. The particle will not boost because the cooling will be effective. Okay, that's how they call, okay, the standard GRBs cannot accelerate. They choose low luminosity GRB. But the board is again defining,
yeah, I mean, something along that line. So, because in hadronic models, like their radiation efficiency becomes less. And when you're saying that you want to accelerate protons, I mean, you need more energy. And these GRBs that you're talking about is already the extreme energetic kind of. So, do you have an energy budget constraints when you include hadronic models?
So I think it's always like this beginning. There can be isotropic energy, so they brought them down. They bring them down by the beginning by a factor of 1,000, and then they again more or less okay within the isotropic energy. They say proton can explain the data, so they do take care of that. Yeah, not that much problem. Yeah. But yeah, in some cases you are right. When actually it can go more than the isotropic energy than the proton models are.
So do you have a jet optic angle estimate like where you already know the BV? So that you independently kind of constrain the energy budget, and because you know the redshift, you definitely know the energy, and if you know the angle, so you already have it. So that becomes a hard constraint for your model.
So if you see the GRBs, what I discussed SSC model once, for them we have not seen the jet break, but this board GRB, LASO actually found a jet break around 700 seconds. Based on that, the jet angle is 0.8 degree. So it's like, reducing the power by a factor of 1,000.
So you have calculated the energy for each of the GRPs from the afterglow, but the numbers are quite high, higher in the ranges. So have you calculated the efficiency? Because for 190829, I have checked that the energy inferred from afterglow is around 10 to the 52 hours, but from the prompt emission, it was around 10 to the 49 hours.
So it means kinetic energy. What you are calling is from gamma ray.
Yes.
So this is the kinetic energy, and the efficiency is not very well understood. It can have all the range possible states.
Okay, let's one more question.
Both objects gives energy up to 10 to the 54 hours per second. So what could be the possible mechanism which can produce such a gigantic energy?
So this is again collapsar of a massive star. So you have this type 1b star, highly rotating object. Okay, they are compact object rotating, and the rotation energy actually converted to the magnetic field and then channeled to the jet. So
Rotating means it's a spinning black hole kind of thing.
Yeah, it's
it's project
star. It's the star.
Project
star. It's star 1bc. Yeah.
So it's a very, very fast spinning star. and it has also a certain amount of magnetic field. But when this collapses, the magnetic field also gets that much boosted. Okay, so that powers whatever material is around. That powers those material. These are all again gospel. This is like the Bible. This is like a Bible. Okay,
up to 10 to the power of 54, the energy actually even magnetized scenario has been proposed as progenitor.
They say that very low mass black hole kind of thing, maybe 3 solar mass or so. If you dump lot of accretion there, then you can produce energy, let's say, to the power 51 or so.
No, 50, that is different.
54 is a
54 is like it is because of this fast moving jets are colliding with the slow moving matter.
So when you do beaming, it's
beaming direction 1,000 51.
Okay,
but there are
let
few GRVs which are rising up to 53, 84. There are 1 or 2 GRVs when they, even after beaming, it comes up to 53, 84.
Okay, let us thank Jagdish once again and move on to the next talk, which is by Rahul Gupta.
Okay. Hello everyone. I am Rahul. I am a PhD student at ARIES. I will be talking about the dark gamma ray bus. We have done this work in collaboration with GTC and Bose team. I would like to thank the organizer of meeting for giving the opportunity to present this work. So let me quickly go to some historical remark of the gamma ray bus discovery. So here is the first gamma ray bus which was discovered by the Bellon mission in 1967. And you can see the light curve of the first GRB. Although the temporal resolution of the instrument is not very good, but you can see that it is a very bright emission and for the very short duration of the time. And during this period, it was a quite heavy debate. They are basically galactic sources or they are coming from the extragalactic. So there was one mission called the Compton Gamma Ray Observatory. So there was an instrument on board this mission. We detected around the 2700 GRB, and you can see the localization of this GRB were distributed over the globe. So this basically gives indication to whether they might be coming from the extragalactic. So later on, there was one mission before that in 1997. We basically discovered the first counterpart of the gamma ray bus in the X-ray band. You can see here the basically a fading X-ray counterpart. And from here, basically the research in the GRB basically shifted to in a different era. So just after the X-ray counterpart discovery for this particular GRB 97028. So people are also search for the optical counterpart, and we see they basically we discovered the optical counterpart, a fading optical counterpart was discovered, and people measure the spectroscopic redshift for this source and exactly confirming they are basically extragalactic sources. So from the first discovery of the optical counterpart, there is a question like all GRB are basically accompanied with the optical counterpart. So during early phases, early observations showed that around only 20 to 30% of GRB have the optical counterpart, because during this period, the most of the telescope response time was quite late. So after a few hours, you can just follow the counterpart. So during that phase, number was quite less. But when the shift was launched, it's basically having a quick response time, and there was a many fast optical telescope from the ground. So we could basically monitor the more number of the optical counterpart in very early phases. Still, there is a huge amount of GRB where the no counterpart or no optical counterpart were discovered, around 20 to 30%. So these GRB basically there is a prompt emission, but there is a no optical counterpart. These GRB basically called is basically dark gamma ray bursts. So question arises why they are the dark. There is a several scenarios suggested in the literature. One possibility is that they are intrinsically very faint. Other scenario might be like they could be originated at a very high redshift. So GRB is basically cosmological sources. So suppose one particular GRB
originated at greater than 5. So most of the optical emission is basically observed with the live forest. So if you observe this particular GRB in the optical typical R band, you will see nothing. So for we want to detect this such high redshift sources, so we have to monitor in the near infrared basically NIR observations. So the problem is like there is not many telescope, which is basically many large telescope which capable with the NIR observation. So another scenario might be like absorption. Absorption in there are two possibility: absorption within the host, and absorption within the line of the site of between the observer with the source. So this they might also cause the basically darkness for the source. Other scenario is like optical emission and the X-ray afterglow. Basically, they have completely different origin. So, however, this absorption scenario is suggested to be the most significant one for explaining this dark GRB. So, question will either like dark gamma reverse and other optically bright gamma reverse. They have the similar property. They are having a completely different population. So here the distribution of high energy properties. With this basically red one is showing the optically bright GRB and the blue one is basically dark gamma reverse. So here the axis scale is basically the isotropic distribution of E iso energy, and here's the E peak energy, and here's the luminosity in the gamma ray band. If you see the distribution, they basically all three basically are indicating that there is no significant difference between the optically dark and bright gamma ray burst. So how about the host property of the dark gamma ray burst? So typically long GRB appear in the bluer kind of galaxy. So but how the dark gamma ray burst basically appear in the redder galaxy. Here is the distribution of the redshift as a function of color indices R minus K. You can see the bluer one is basically optically bright one, and the redder one is basically dark gamma ray burst. So you can see the color is quite redder for the basically dark gamma ray burst. So the problem is like most of the cases we don't have for the dark gamma ray burst, we don't have the optical counterpart. So we basically rely on the host property to determine the redshift and other property, because we don't have the optical counterpart. So here is the one the distribution of extension along the line of the site and host extension. So you can see the shaded region is basically corresponding when these two values were equal. So you can see the basically bluer one indicating basically optically bright, and red one is optically dark. So you can see there is a few optically basically dark GRB where the extension along the line of sight is very high. So dark GRB basically prefer a very inhomogeneous distribution of observing medium. So here is one example, GRB 150298, which basically we work in collaboration with GTC team. So it basically detected by the initially prompt emission discovered by the Fermi GBM instrument, and X-ray counterpart was discovered by the XRT. However, when we started the optical follow-up observation, we do not see any optical counterpart. But when we triggered the GTC for the near infrared search, here is basically the finding chart. You can see this circle is the XRT region. So when we trigger for the near infrared observation, so we basically detected the near infrared counterpart. It was basically fading with the time. Later on, basically we also searched for the host galaxy with the GTC, and we of course detected host galaxy within the XRT array circle. So here's the log of the observation which we perform with the GTC. So it is basically a clear indication towards the dark nature, where there is no optical emission, but there is an infrared detection. So they have compared the basically high energy property of this particular source. As a prompt emission light curve, clearly showing a very bright emission, followed by a very fainter phase. So basically two emission phases. We basically place the properties of these individual phases in different distribution of the high energy property. So we are confirming like it's basically high energy property you are consistent with the typically what we see in the case of optically bright GRB. So here is the key result of this particular work. So basically we perform the set analysis of the joint XRT and our K-band detection from the GTC. So we basically constrain the basically extrapolated the X-ray power law towards the NIR region and constrain the extension along the line of sight. And similarly, we have clear detection of the host. So we basically perform the set analysis of the host also to constrain the basically extension within the host galaxy. So if you place the, if you consider the extension from the lambda line of sight, and if you consider the extension within the host, and if you place this GRB in this region, in this figure, it was lying completely outward. So it's basically the environment of this particular GRB is demanding for a very huge amount of extension. In fact, it was the highest distinguished GRB known to date. So, okay, along with GTC, we also follow the GRB using 3.6 meter universal optical telescope. We have one advantage, like it has a unique location. It is basically located between the Canary Island and Western Australia, and it has basically a core instrument capable of deep imaging and spectroscopy. So, since from the very beginning of the afterglow era discovery, the ARIES has basically more than 2 decades of history for the GRB follow-up observations. You can see dot is here, and there is a 1.3 meter universal fast optical telescope. Here is the ILMT. So we basically trigger dot for very specific. We have very specific observation trigger criteria to trigger the dot, and we have around triggered 65 GRB after further follow-up observation of 65 GRB afterglow since cycle 2020 C2. So here is the one example of a dark burst, which basically we studied using the dot. And you can see here we taken with the Fourier CCD imager mounted on the dot, and we do not see any optical counterpart. But when we perform the set analysis, very similar one. So we noted the extension in this case is very less. So possibly in this case, high redshift might be the region for the darkness of this particular dark gamma ray burst. So we basically studied 2 cases. One where we noted that basically high extension is causing the darkness, and here is the example where high redshift might be the possible of darkness. Okay, so there is a very there is the upcoming missions basically dedicated to study gamma ray bursts like penta sources of optical counterpart, to search for optical counterpart of GRB. There is one upcoming mission SBOM is basically a synchronous. It will be there is a multi-doubling mission, and there will be a synchronous optical and ground-based telescope to monitor the prompt emission and as well as the afterglow across the EM band. So it will be quickly identifying the dark GRB, because there is a telescope on board which is basically capable to giving a very early observation of the optical counterpart, and it will be helping to probe the early universe. In fact, there is another mission is planned by ESA. So basically the thesis mission, and there is one onboard instrument. It is called basically infrared telescope IRT. It's basically specifically designed for the basically afterglow follow of the GRB in basically near infrared band. And such observation will be very, very crucial to probe the early universe, because they might be originating from the very early universe. So there is also a community developing a very large telescope like ELT and TMT, because the dark gamma ray afterglow might be the very faint. So such very larger telescope might be very helpful to probe their origin. Okay, the summary. So basically, dark gamma ray bursts consist of a significant fraction of the GRB population, and in fact, their prompt properties are very similar with those in the case of the optical bright one. So for this particular GRB, we discovered the K1 afterglow, and it was basically most just obscured gamma ray burst detected till date. In fact, there is a more synergetic observation between an IR camera and larger telescope like GTC. In fact, JWST will be playing a crucial role to further follow-up observation of such penta sources like dark gamma ray burst. So I'll be end up with my talk with this slide. Basically, where 3.6 meter dot is particularly RB 2112 day. This is quite discussed in previous talks. This was basically long GRB when we were indicating it might be coming from the collapse up. But when I started follow-up observation using 3.6 meter dot, you clearly see the indication of a kilonova emission. This was basically first case of a long burst discovered with a kilonova connection. And this was published recently last year. Yeah, thank you for your time.
Questions?
Very quick question. So as far as I gathered that the dark GRB is because of the dust absorption, right? So does, I mean, but you can see it from with the infrared, right? So does it say anything about the environment?
Yes, sir. Yeah. So basically, if you see the nature of, basically we assume that typical dark GRB happen in the radar galaxy. So they have, their environment is quite dusty. So basically, not only dust, there is another possibility. They might be originating from the high redshift. So in that case, also we can see the dark GRB.
So it's not about the galaxy, but the intervening medium.
Yeah, they might block.
Any other question?
Just continuing on that. So, for example, like in short GRBs, if you take, there is only a very small number that we have afterglows and redshift measurements and so. So, in this particular case, also, have you estimated the number density of ISM, or do you have some idea of?
Yeah, if you see in the case of dark GRB, because the modeling is quite different because there is no optical emission. We have only X-ray emission, and in some cases light emission. So, and in some cases NIR, but there is no optical. But typical number density is quite lesser. That might also cause in the basically the darkness. Because typically if the number density is quite less, so in that case, basically the luminosity might be quite low. That indicates toward the dark.
I mean, but you said you have X-ray lab.
Yeah.
And so, I mean, with the typical number values of synchrotron modeling, you should be able to estimate the number.
I did not say any dark paper which is basically modeling the afterglow, because the number is like even if there is infrared follow, there is only 1 point, 1 or 2 points, because it is quite fainter. So if you take, even if you try to take the spectra is mostly featureless, because this is very different.
So, did anybody try the spectropolarimetry observations of the dark GRB? Because if it is due to dust, probably it may show some of optical polarization.
No, there is no basic polarization. Optical, there is no optical basically detection. If there is no optical emission, so in that case,
there's no optical at all.
yeah, basically we can try like we tried for the spectroscopic observation of the host, because the host was in this case was making intermediate redshift around 2, but in host was also very faint.
Okay, could you if you take some sort of host galaxy template and you try to see if there is more infrared you are seeing something like that?
Yeah, we basically did. Even in this case, we basically perform the set modeling of the host. So from there, you can consider the AV within the host. So typically, AV value in comparison to the bright optical galaxy, bright optical GRB, it is quite higher in case of the dark one. That is one.
Okay, let's move on to the next talk, and thank Raman once again. So the next talk is by Ankul Ghosh, and he'll be speaking about the search for merger rejector emission in short-wave universes.
So hello everyone, my name is Ankul Ghosh, and today I am going to talk about the search for the late time merger rejector emission in short GRBs. So in last few talks of the GRBs, they have already covered about the prompt emission and the afterglow mechanism of the GRBs. But now here I am talking about the late time merger rejector emission or the kilonova afterglow emission for the short GRB. Yeah, it's fine. So GRBs are basically the powerhouse of energy, and it can produce the energy of 10 to the 48 to 54 arc within a blink of an eye. So you can imagine how powerful these GRBs are, and it can open up a new and extraordinary window to the universe.
The next thing is the classification scheme that has already been covered by many talks. So basically GRBs are classified into long soft and the short hard burst. So depending on the T90s and the progenitor system, they are completely different. The long GRBs are basically coming from the collapse of a massive star, whereas the short GRBs are coming from the merger of two neutron stars or the neutron star black hole pair. Here is the aftermath of the BNS merger. Basically, this is for the neutron star case. It can be possible for the neutron star black hole scenario also. Depending on the final mass after the merger and the neutron star equation of state, there can be multiple scenarios that can be possible. It can be a black hole or it can be a millisecond magnetar that can be present. So in case of the binary mass is less than 3 solar mass, you can see in between this merger and the final product black hole, there is a transient state which is known as the hypermassive neutron star or a magnetar. Now, what are the scenarios for the magnetar? So there are basically extended emission in the prompt, and also there is some X-ray plateau in the afterglow emission. Now, I'd like to explain this figure a bit. This is basically the smoking jet model. There are two energy injection channels from the central engine. First one is through the jet, and second one is through this merger ejector. So already this jet part is covered by all these talks. Now I'll be talking about this merger ejector or the kilonova ejector. Now, the neutron star merging is happening and it's a very highly neutron rich environment. So the higher order elements present in this medium capture the neutrons via rapid neutron capture process. This is also known as the R process nucleosynthesis. And finally, it goes to the higher order elements like lanthanides, and these are the very unstable elements. Finally, they do the beta decay and we get this kilonova emission. Now we can consider if the central engine is not a black hole, it's a millisecond magnetar. So the magnetar has a tendency to release its energy via spin down process. So it directly goes to this circumference ejector, and this ejector becomes mildly relativistic. Whenever this ejector interacts with the circumstellar medium, which is the ISM medium we are taking because it is far away from the central engine, that's why we are taking the ISM medium as our case. So we can get this late time merger ejector emission. Now, what are the motivation behind our study? Before our study, 3 or 4 studies has been carried out, but they are basically tried with the higher frequency regime of the VLA or ATCA. But when we tried to plot the spectra with the T deceleration and the new A, we can see that this spectrum is peaking around 600 megahertz. That is in the lower frequency regime. That's why we have chosen the GMRT band 3, band 4, and band 5, which basically average in the 325, 610, and 1.4 gigahertz band. Now we have selected some. We have selected the samples by taking some selection criteria. So we have excluded the samples from the previous studies. We have selected the redshift cutoff up to 0.5 as the signals are very weak. The low medium density from the afterglow modeling, no potential signature from the X-ray afterglow emission, or there is no presence of kilonova. So I forgot to mention it here. And the burst having southern declination or beyond minus 52 degree because the GMRT is inaccessible for that. So here you can see the potential signature of the magnetar. There are 3 potential signatures. One is the early time X-ray emission, the mid time flattening or plateau, and the late time X-ray axis. So here you can see in Rawlinson 2013 paper, they have chosen some GRBs which shows this kind of signature. So for our study, we only selected those GRBs which have these kind of peculiar X-ray features in the X-ray light curves. Now, after selection, after applying all those selection criteria, we have these 5 GRBs for our GMRT observation, and the observations were carried out in 3 different frequency regimes, you can see, and the time scale in between, time scale of the observation is 2 to 11 years since the burst. But unfortunately, we did not find any GRB, any signature of the late time merger ejector emission. So that leads to the GMRT upper limits that is also presented in this plot. And also we have plotted the fluence here. Now, what can we do basically with this upper limits? So we can do some modeling stuff. Here we basically improvise some of the things in terms of the modeling and the observation. So in observation strategy, we have taken the wider observation span than the previous ones, and we have observed using GMRT frequencies, not at the higher frequencies. In the modeling, we have taken care of the energy injection from the central engine, the dynamics of the deceleration ejector, the synchrotron frequencies, basically 3 synchrotron frequencies, the Doppler effect, and the non-relativistic transition. Finally, we get this we get this model light curve, and this is the comparison from the Fong et al. The previous model. Here you can see the deceleration time is almost similar, but the later time slope is different from the previous model. So I forgot to mention the gamma factor evolution. We have checked the gamma factor evolution for our case, but for the Fong et al. Model, the gamma factor was kept fixed. Now, here is our model. So first we have taken care of the dynamics of the ejector. We have taken care of the evolution of the bulk chlorine factor. And finally, we have improvised it into the different calculation, like the calculation of deceleration time and the deceleration radius. And the synchrotron frequencies as well as the peak synchrotron flux has been calculated from the Rybicki-Lightman standard scenarios. Finally, we get this model light curves. There are 4 different model parameters that we have varied. One is energy injection from the central engine, the number density of the ambient medium, the ejector mass, and the observed frequency. So after varying all those parameters, these are the model light curves. Here you can see there is a peak of the light curve. So it can be possible because of the 2 reasons. One can be because of the deceleration, and the second one can be the ejector is going from optically thick to thin regime. But we are dealing with some late time cases, so the optically thick to thin regime is avoided, and this peak is basically coming from the deceleration. So here is the model light curve of GRB 05, 07, 09. That is one of the cases. In GMRT 610 megahertz band, we have considered the energy 5 into 10 to the power 51 erg and 10 to the power 52 erg, and the number density is varied from 10 to the power minus 2 to 10 to the power minus 5. So by comparing those two, we can say that the number density is varying from 10 to the power minus 3 to 10 to the power minus 4, which is quite less even for the short GRBs. Now, the second parameter we tried to constrain is the maximum allowed energy for the magnetar. Here you can see the peak flux equation, which is depending on the rotational energy, number density. Epsilon B and epsilon E are the energy equipartition parameter, which is transferred to the electron and the magnetic field. So that parameters are kept constant for the simplicity of the calculation. But we have taken wide range of E rotational energy and the number density. So if we vary these 2 parameters, we will have plenty of flux values. So if the model flux is less than the 3 sigma upper limit of GMRT, then it is known as the allowed space. And if the model flux is greater than the 3 sigma upper limits of the GMRT observation, then it will be known as the forbidden space. So here you can see the energy versus number density parameter space plot for all the 5 GRBs in our sample. Here you can see this dark space is the allowed space, and the white space is nothing but the forbidden space. This vertical column defines the number density ranges from the constraint from the afterglow modeling. Here you can see the maximum energy can be calculated where this vertical column is intersecting with this allowed space. So for all of our case, the energy is varying from 2 into 10 to the power 51 erg to 2 into 10 to the power 52 erg. So the 140903 is the highest energetic scenario, whereas the 160821b is the lowest energetic scenario for our sample. GRB 061210, for which the number density constant is not available. So that's why we cannot properly constrain the maximum rotational energy of a magnetar for this particular case. So here is the summary of my talk. Basically, the spectrum peaks in the low frequency radio region. That's why we have selected the GMRT observation in 610, 325, and 1.4 gigahertz band. and the time scale is 2 to 11 years since the burst. If the emission is detected, then it could be the first ever emission from the late time merger ejecta emission or the kilonova afterglow emission. But we found no emission, which leads to put some constraint on the number density of the ambient medium as well as the maximum rotational energy of the magnetar. Now, in the future prospect, maybe with the future generation telescope like SK1 or NGVLA, so we can detect this kind of emission because the RMS sensitivity will be much higher and the angular resolution will be much better. Nowadays, Hazel et al. In 2021 for GRB 170817, you know the gravitational wave scenario for which the GRB was detected. So they got some late time detection almost after 3 years since the burst in X-rays. So they have also tried it with the 3 gigahertz VLA bands, but till now they have not detected any late time scenario in radio frequencies. So we will also try to monitor this kind of GRB in future so that we can detect this late time merger ejecta emission in future. So thank you.
Questions?
So yeah, nice one. So my question is, how do you rule out the merger remnant is a black hole? When you have considered magnetar here, but how do you rule out that it is not a black hole?
So actually, we can select both the scenarios, but for the simplicity of the, because if we consider the black hole scenario, the number of GRBs will be much higher. But here we are taking only those GRBs having this X-ray plateau kind of structure in the X-ray light curve. So in Rawlinson 2013, they have taken into consideration that these X-ray plateaus are attributed to the presence of a magnetar in the X-ray light curve. So that's why we have selected those GRBs having this X-ray plateau or the kilonova features in their optical or IR light curves. Kilonova signatures are visible. So we have selected only these GRBs, and also we have applied other 3-4 criteria so that we get this kind of, because if we deal with 50 short GRBs, that will be much longer process. But that's why we have shortlisted those GRBs.
Yeah. So my question, I mean, a follow-up is like, if you had a black hole instead of a magnetar, does it have like non-detecting?
Yeah, it can. That's a very good question. Actually, I have tried with both the scenarios. So for the black hole scenario, the energy is comparatively much lesser because magnetar is continuously injecting the energy to the ejector. So the ejector velocity will be much higher for the magnetar case, but for the black hole scenario, there is no push from the central engine. So that's why the energy and the ejector velocity will be much lesser for this case.
Okay, I think we are at the end of the conference, and also people are exhausted, I guess, by now. So thanks to all the speakers of this session on gamma burst. It was very interesting to listen to the different scenarios in all the talks. I'll hand it over to Indraneel now for a discussion on future prospect and conclusion of the conference.
So whatever starts has to end. So what started on second has to end on third. So thank you all of you for coming here in very short notice, and you had many, you were very busy and you had a lot of commitments. Still, you could manage. That's I mean I should thank you very much for that. The basic plan in most conferences we go, it's generally becomes very disconnected after first day itself. So the only thing I wanted was that if I can put people who are more interested, have common interests together, then a 3-day conference makes sense. So my first instinct was to have black holes and neutral stars. These are the two areas I work in. And I also work on jets. So the moment I work on jets, the GRB has to come in, right? So these are the 4 things I could not avoid.
Okay. So even then, you can see that we have taken 40 people and, it's a 3-day conference. It is very intense. Okay. But thanks to all of you, you have participated in a very animated and in a very, very enthusiastic manner. Thank you all of you very, very much. I mean, I couldn't thank you more than that, what you have done. Because participation is also very, essential for people to, and I could see the speakers are, really enthusiastic. Okay. Some of the speakers could not be even dragged down. Come on, it's over, down. So that was very, great. The director is not here, but thanks to him, whatever fund we asked for, he approved. Okay. So I should thank him. I should thank director staff because they actually helped me a lot. And I thank the SOC of area. Bhargav is there, Kuntal is there, but Shanto is there, Samir is there. But Anuj could not come because he fell ill. And Gulab could not come. He also had a sore throat or something, so he could not come. Dipanjan left because Dipanjan, he wanted to stay till today. But the problem was that he was already traveling for 2 conferences abroad. He came back and his parents are visiting him in Pune. So he wanted to spend one Sunday with his parents. So I could not say no to that. Santosh could not come. Santosh would be coming for a conference next week. So probably his director had some job for him, so he could not come. I really wanted Dipankar to come. Okay. Dipankar promised me that he will come, but then he said that he cannot because he had classes till Friday afternoon. Okay, so then it will be very hard for him to just come for Saturday and go back. So it would have been very good if Dipankar would have come. Of course, I invited my supervisor, and he could not come as well. So, most of the people have not seen Sunday. Okay. He's a character. Okay. So, when he is in real mood, he can give fantastic talks. Of course, he will be aggressive. He will call people names. But if you can filter those out, he can give fantastic talks. 1 or 2 talks I have seen, heard. Amazing talks. Yeah. He has a graphic memory and he can, speak like. So, of course, there are many people who, when we were students, we used to look up to them. They have retired. So those people, I could have called them, but they are now outside active research. So they would not have contributed. And last but not the least, ARIES students. Okay, this conference without Raj, I couldn't have managed. Okay.
We are on the website for Raj.
Whether it's the bag, the choice of the bag, the vendors, okay, the logo. Okay, so Raj and Sanjeet had a difference of opinion what should be the logo. So Raj had this idea that he should have the geodesic motion of the photons. And Sanjeet said that this would be awful. No, he wrote the code because essentially it was Sanjeet's pre-PhD project that was included on that in that logo. But that idea, what would the color combinations? I actually did not look into it. I just saw the final product, and going to the vendors, figuring it out. Also, sort of trying to argue with them what should be a good price and so on. It's fantastic. I couldn't have done that. Mukesh is sitting here.
Mukesh played a similar role when I hosted Redco, the second version of Redco, here a long time back in 2015. So Mukesh can relive some of his old memories through Raj. And incidentally, Raj's thesis and Mukesh's thesis are somewhat similar. He worked on the analytical part and he's doing the simulation of that. So, yeah, and Bhargav, would you like to say something?
I mean, Indrujil is very modest. I mean, he's not putting his name. I think the effort he has put to do this, I think a lot of appreciation goes to Indrujil. Big round of applause. I think it is great that he has called us here and we have had this meeting. I'm also coming for the first time to ARIES. Now I think you will have a permanent visitor to ARIES every time.
Gladly.
So I think this was a very, very enriching thing, and I can see students coming and doing simulations, which is actually very, very encouraging for the community in general. And also people are getting involved with bigger collaborations. I think that is also very, very important. I think now astronomy is becoming more like a collaborative science. It cannot be done in one office, sitting behind one computer. So I think more and more the younger generation basically adopts this and does more and more collaborative science. I think it will be better in general. So I think it's a great thing, and I think we will have more and more such things coming up at different places in India. So let's keep this thing going on. And thanks once again to all the students and Indranil and all the participants. Thank you so much.
Santo, Shobir, Stalin, where is Stalin? कहाँ भाग गया? Stalin! बाहर है तो वो सुन लेगा ना? नहीं, but there is a screen there, right?
Yeah, I mean, there is nothing more to add what is already been said. In fact, it's one of the process we can give a training to the youngers how to organize a conference and bring the interested minds together to get the best output, not only in the form of a conference is the national importance. We should be visible at the international level that India is doing something. They are contributing in some part. So this is the way we can have this very focused meeting involving 50 odd people where everyone is eager to express their scientific research work in front of the others who are really interested. So in that sense, I would thank Indra when he proposed this thing in Kodaikanal that he is going to arrange something in towards the end of this year, and I immediately appreciate we must do it, and obviously we should give a platform to all the people who are really interested in to do that. So it's very good, and because of this meeting, I could meet many people after a very long time. And some of my students who are here, I could not meet them maybe more than a decade or so. So it's a very nice opportunity for me to meet all of them. Thank you for that, and I hope this kind of meeting we should organize in, I think, if not every year, every 2 years or something like that. It would be very, very beneficial for all of us. Anyway, so I think very thanks to you. I mean, you initiated all those things.
Okay, so I'll start first, of course, thanking Indra and his team. A wonderful job, and particularly it's a very focused meeting. One thing I noticed over few such, meeting what I am attending recent days, I see a gradual improvement of the quality of presentation from the students. They're extremely smart, these students, and I find scientific quality-wise, presentation quality-wise, is really appreciating. So in that sense, I see that we are really going forward. So that's something I could see. Apart from that, organizing such a meeting, if it's like a small meeting every year, that will be very good, so that we'll be really in touch that what are the new things that we are doing. And so in that sense, that will be much more appreciating if we can do it in regular fashion. Apart from other meetings that we have, that is more of a much wider spectrum. So as you mentioned that after first day or second day, things are getting much more scattered. So we really do not attend all the lectures that we wanted to attend. So in that sense, this kind of meeting is very helpful. And thanks again for organizing ARIES. Though I'm sort of multiple times I have visited this place, but every time I find a refreshing sort of memories coming here. Thank you.
Puneet, would you like to add something? Puneet was the first one to say yes.
Okay. So, yeah, so the last time when I came, there was no ARIES. It was UPSO. It was 99 and Kargil war was going on and yeah, I'm here. So we visited. Now after 24 years, I'm here. That time Indonesia was fighting with someone. Actually, it was between IAM and IATI.
Is this common?
Yes. IAM group and IATI group.
It was started in 2099,
99 around, yeah.
99 only.
Yeah. Yeah. He was a student in Calcutta. Now he's a faculty here for a long time. So many years have been passed, and as Indranil mentioned that the people when we were students, now they have retired, and now we are among the senior people. So, and I think that in this year, as Sami mentioned, it's really true that number of students have increased in astronomy, and the quality of work, quality of presentation, everything has improved. So I think, yeah, and these collaborations also Bhargav mentioned. So of course I do not agree with him fully. The collaboration is not the only thing. So collaboration is one aspect. But independent work is also extremely important. So, and analytical work with one computer work is also very important. So one should keep on writing single author paper as well. But one should also collaborate, particularly with teams, international teams. So one should keep a balance. So in any big team, one can be very comfortable, but one loses somewhat one's identity. One has to keep that in mind. And if one wants to keep one's identity, one has to do his or her own work. And yeah. So this is one trend which is good and which is the need of the hour. Of course, doing collaboration, being part of it, I mean, big collaborations are mushrooming everywhere. So, and we cannot avoid that. We must be a part of those teams, but we must also keep our own identities. So we must think independently as well. That is also extremely important, because what I feel that from collaborations and big things, what one can do is basically propagating and advancing the thing, basic thing which is already in place, but to bringing in new basic aspects, one has to do the independent work. So we should do both. We should keep balance. And this meeting was quite successful. And I primarily thank Indranil for that. And of course, his team here, ARIES staff, and everyone. And that's all.
So I think Aruberi and Amit are going to catch the 5:30 bus. So I would have liked everyone to contribute, but for them,
some students should say something.
yes, just any criticism. Okay, by the way, whoever wants a certificate of participation, just give their names to Sanjeet. Okay, he's the other guy who actually without him and Priyesh, I couldn't have done it. No, Priyesh is there. So without them, I was absolutely in a handicap. So just give the name to Sanjeet.
So whoever wants, if they want some particular thing to be mentioned in there, they can also write it. I'll also circulate a Google Doc file where you can put all your suggestions and criticisms and whatever. Okay. So just do put it, be honest and do it. My students knows I'm very, on their face when I have to criticize them. If this is wrong. When I say that it's wrong, I just say it on their face. And for that, who are not my students are always very afraid. But that's the way it is, and I also expect the same thing with all of you. So you can always write. In that, please do write. I want to improve. Okay. So with that, Stalin, one quick word.
Yeah. I must thank Ivan and his team too for organizing such a nice meeting. So what I have seen, this kind of high energy focus meeting happened sometimes in 2005 or 6, when Professor Rao used to organize some meeting in Goa. So I had the opportunity to attend one such meeting in Goa around 2000. The number of people are hardly some 10 or maybe 15. Then I had the opportunity to come to ARIES in 2015 for the first REDCO meeting. So I had the statistics made. Second. So that was second REDCO meeting. So there also the number of people, particularly young people, around 10, 20. So then with the push of you, Indrani, Arnold, Sami, Sandra, somehow we organized the fifth REDCO in Kodaikanal. The number of people have increased roughly 10 times. Particularly women scientists have also increased. And these meetings really beneficial, whereas people have, I could see the improvement in the quality of the work, the presentation style, and the way the data were used. People are not focused on single data, they were using what? They were using data from across wavelengths. And one or two presentations I found that they have, in addition to observation, they have also used theoretical interpretations. So this is something I'm finding improvement here. And I think this tradition should continue. And let us try to improve the quality of the young researchers which are going to come up in this field. So I thank again Indran and other staff for a wonderful meeting. But I must apologize, I have to go in and out of this meeting now and then. I am sorry for this.
So Kuntal, you should close the meeting.
I would like to only thank all of you for being to be able to come all the way up to Nainital. I know it is a very difficult journey to reach here, and especially some of the struggles that some of you faced when your flights were cancelled in Delhi. But believe me, this has been one of the most enriching scientific meetings we've had in the recent times, and especially after the COVID lockdown. And I echo all of your words, and that we should certainly continue with these focus meetings in the past. And I'm sure it's been very beneficial for the students as well, and especially the ARIES students, because we saw that some of the students were attending the talks. So thank you all once again for making it here. And also a very big round of applause for Indranil and all the students who were in the LOC and who worked out all the details of this meeting so that we could have a very seamless program throughout the meeting. So thanks all of you. Okay, so the meeting is officially closed now with the goal of having another meeting shortly.
Meeting over,